Hello everyone, good morning. How's it going, guys? We have some few people here this morning. So how was the first day? Yeah, we had some packed days with a lot of interesting talks. So we're starting today with the first session, which is applied cryptography. So I think we have like 4 or 5 talks. So I will be the MC. So my name is Youssef, so I work for Linea. I was a speaker yesterday at the very same stage. Today I'm an MC. Life changed fast, right? So yeah, hope you're enjoying your time. So maybe we're gonna start with the first talk. So we have Ayush Gupta, who's a ZK steward and co-creator of also Plume Signatures, the ERC. And then we have also Sura Suigami. And they're gonna talk about ZK email. So this is one of the applications I'm most interested in, like for ZK for real lives. And the stage is yours. Thank you. Enjoy.
Sweet. Today, we'll mostly be talking about ZK email, new applications, and production-ready account recovery. I'm Ayush.
I'm Sora.
And most of this work was only made possible because of this incredible team of folks we have working with us. So huge shout out to them. So we'll start by mostly going over the basics. What is ZK email? How does it work? Then we'll dive a little bit into how you can make proofs really easily, and we'll discuss a new registry and SDK that lets you do that. And we'll try to expand the possibilities for how you think ZK email proofs can be used in reality. Finally, we'll talk about account recovery and how you can generally have email-triggered transactions on-chain. And last, we'll talk about dev tooling, all of the different ways that we've put together tools for people to build these kinds of proofs really easily into existing apps. So to start with the basics, what is ZK email? The idea is that emails are signed according to the DKIM protocol, an RSA signature of the SHA-256 of the content of the email. This is applied to every single email sent or received since 2017, usually used for spam filtration, but we prove this inside of a ZK proof and add selective disclosure and parsing. This means that we can get proofs of emails where we can get privacy, as in we can hide or reveal whatever we want. We get provenance. We can verify the data from the Web2 service's mail server directly, and it's portable. We can verify it directly on chain, on any chain that can verify these proofs. You can imagine the simplest intuition for this is something like whistleblowing. We take an email you've already received, and we redact different parts of the email, and then we prove that the email was still valid or sent by the source. But you can do much more than this. For instance, ZK P2P builds marketplaces on top of these emails. One example is a domain marketplace. The idea is that you can take any Namecheap domain that you own, and you can list it on this marketplace, and when you sell the domain to somebody, aka you transfer it to them, both of you receive a confirmation email from Namecheap automatically. If you prove that confirmation email on chain, you can then unlock escrowed money directly to pay for that domain. This is quite compelling, and the idea that you can interoperate these Web2 assets or things in the real world with things on chain is extremely compelling, and how can we get more of these? So our idea was, what if we made it really, really easy for somebody to create new proofs and update those proofs? So we'll talk a little bit about how this can be applied to general proof infrastructure in a couple of different ways. A registry that lets you reuse proofs that other people have already defined and define new ones very easily. An SDK that lets you use them very easily in your application. And finally, some inspiration around what are some apps that people are actually building with this. So one of the main problems with ZK development today is that an app developer who's trying to build something related to their email should not have to think about the nitty-gritty details of which proof system they're using and the different trade-offs on different systems. So the idea is you can abstract this all away. You just define a sort of a blueprint, like, oh, I want to prove that I was rejected from giving a Devcon talk, for instance. And then, if I define this kind of blueprint, anybody can use it without having to think of the proof system that's happening in the background. How does this work? Well, the idea is you can create new patterns very easily. For instance, after naming your pattern and uploading a sample email, we can automatically parse out the relevant information from that email to help define this new kind of pattern. For instance, we can take out the sender domain automatically, or things like the email length of the header or the body. Then we have this nice feature where, because we want to define a regex to extract specific information from within that email, we automatically throw an AI on top of that raw email data and define that regex for users. We found that historically, this has been a bit of a roadblock because having to adapt regexes to odd different kinds of email templates is often not a very intuitive task, but we're hoping this makes it super easy for anyone to define a new kind of proof with no relevant ZK or necessarily even parsing experience. And finally, it'll give you a configuration like this. This is a decent amount of text, but the main thing to take away from this is that it's only about 20 or 25 lines. This defines all of your regexes, where they occur, and who the email was sent from, and other metadata about it. But this is a full encapsulation and definition of your proof. Then in the background, we can automatically compile this to all of the proof systems that we listed. Right now we have Circom and Noir incoming, and also ZKVMs. And once it's completed, the compilation is completed, we automatically will deploy an interface that anybody can use to create this proof. We see this kind of like almost like a bit of a Vercel. You can sort of create your proof and deploy it without having to think about any of the infrastructure behind the scenes. Concretely, for instance, for the proof of Devcon rejection, you will automatically get an interface for you where you can automatically sign in with your email, and then it will fetch the relevant emails that might possibly satisfy this proof. We can filter those emails entirely client-side so that our server never sees those emails, and then let the user choose the proof they want to select to make a proof of. In this case, for instance, for GitHub, for Devcon, you can choose one of the specific Devcon rejection emails, or for GitHub, you could choose, for instance, a GitHub username email to let you prove your GitHub username. Finally, the proof can happen in the background, and you can share that proof out to whoever you want to share. And we also show you the metadata very clearly, and even let you look at the raw proof. The idea is that once we have these kinds of definitions, we can expand this even one step further. We can also kind of treat it like a bit of a GitHub, where each of these configurations can be edited and modified by other people, and you maintain a version history. So for instance, you can imagine that each of these patterns comes with versions depending on email templates as they change, or users as they want to parse different kinds of things. And if you decide, hey, I don't like this pattern, I want to replace it with a different one, say I want to take my Devcon rejection email, and instead I want to prove Devcon acceptance. I can just fork it, change that value, and recompile it. And so we see these kinds of flows that developers are very used to also being useful for general people to be able to create these new kinds of proofs. You can try this out live if you go to registry.zk.email. We've put a QR code up. You can define a new proof by logging in and then creating a new pattern or trying any of the existing ones within the interface. Note that there will probably be a decent amount of load as all the folks in the audience try this, but we will have a workshop tomorrow where we go through detailed, step by step, how exactly to do this. Now, if you want to integrate this into an actual application, again, you don't need to read the code, but just the idea that this can just be 3 or 4 lines, someone can just define, this is the kind of blueprint that I want to prove within my app. In this case, the Devcon rejection proof. They can say if they want it to be local or not, and then they can, again, you don't have to read the code, but they can just generate the proof and verify it on-chain if they want, without having to think about the proof system. We've seen people build a lot of really exciting stuff with just this primitive. For instance, folks have built proof of DocuSign or HelloSign, where you prove you signed some document with some title from somebody. You can prove you took a flight to or from somewhere and only reveal where you took it from and the destination. Someone created this proof where you can prove you're part of a Slack workspace. You can now start seeing how these things might start combining. You can build a system where you prove you're part of an organization on Slack, and then you automatically get reimbursed for your flights by proving you took them. And as people start realizing, oh, you can bolt these things together, you can build actually interesting systems on-chain where you combine different facets of ideas or identities or actions we've taken in the real world. People have also proved, for instance, you've exported your LinkedIn data, which they then sell to, for instance, OpenAI to train on. You can then prove you exported all of your OpenAI chat data and then sell it to, for instance, Anthropic. You can also prove you automatically resolved a GitHub issue and then automatically disperse contributors for their contributions. John did this fun proof where you can prove you ordered a pad thai in Thailand, where you basically show you have a grab receipt which has the word pad thai on it and a location that's in Thailand. And of course, you can prove that your proposal was rejected from Devcon. So now that we have all of these basic concepts around how you can make proofs of emails that you've received in your inbox, one might imagine that you can also make proofs directly on chain. So far, we've just talked about parts of your identity that already exist in Web 2, but emails, you can imagine, are an interesting interface to actually interact with on-chain apps directly. So concretely, how might you get this new kind of email-triggered transaction? Well, the idea is that instead of doing what we were doing earlier, where you log in with email, for instance, and you select one to make a proof of, you instead send an email to trigger a transaction on-chain. This is quite interesting because now you can have a smart contract that's directly gated just by a sent email. This primitive is quite powerful. You can build things like account recovery, for instance, where you add emails as wallet guardians directly on your existing smart accounts. Things like email signers, where you can add an email directly on your multisig and have that approve transactions, for instance, as a 2FA, or for folks who don't have EOA wallets to be able to still approve transactions. You can log in with emails. This is something folks have wanted in the ecosystem for a very long time. But the idea that you can interact with your average application or crypto app just by logging in with your email and then using that to authorize an ephemeral session key. Or an email wallet where you can receive assets directly to email addresses even if they've never signed up. But today, we'll mostly focus on, I guess to start with, exactly how we can do these kinds of smart contracts with emails. So for instance, the flow here is that users can receive some email asking them to trigger some kind of transaction. And by replying to it, they can initiate that transaction on-chain. They will receive an email kind of like this. We've moved the actual value that's getting approved to the subject, so it's easy for you to read. But the idea is that you would receive a command kind of like recover account ETH address from old owner ETH address to new owner ETH address. In reality, users would just see a simulation in their email, not this text, but we've put it here so it's easy to read. And the idea is that by replying to this email, they're effectively signing this message, which can then be used to send on-chain. Flow here is that a user will try to trigger some sort of transaction. A relayer will send them an email. When they reply to that email, action is then sent directly by the relayer on-chain as they make a ZK proof of that action. One of the cool properties of this is the idea that we have this account code for both privacy and decentralization. You can kind of see, again, we've elevated it into the subject here, but normally this would just be embedded into the body where the user doesn't have to think about it. But what is the point of this long hex string? It's not really private key or something we're necessarily exactly used to, and anyways, it's abstracted away from the user, but it is nice because this value gives us direct email address privacy on-chain. We never reveal the email address, we only ever reveal a hash of the email address and that code. We can also prove availability to the user in this email. That is, concretely, we can ensure that the access to the user's account cannot be withheld by us going malicious, because as long as they have the account code, they can still transact with that email contract. And finally, it allows for relayer decentralization. Anyone can run this kind of system, can run email servers that send out emails, receive replies, and then trigger transactions on-chain. You can imagine this can happen via email replies, as it does right now, or even directly via Google logins. The difference between these is mostly basic security. For instance, on the left side, you can show concrete simulation data to the user of what they're signing. For Google sign-in, it's more like a blind sign-in and a blind signature. But the idea is that applications can choose whatever they want based on what is most convenient for them.
Okay, so from now, among the products using email-triggered transactions, here we introduce the details of the email account recovery. So in short, using email account recovery, you can specify anywhere with an email address as a guardian for your wallet. And when you lose access to your private key, this guardian can help your account, or this guardian can help recover your account just by sending emails. And in this way, this achieves a similar UX as a bank account or a PayPal, such that user can reset password from their email account. And we also believe the combination of the email account recovery with the passkey wallet makes a super easy wallet UX. Because passkey allows users to sign transactions through the Face ID and so on. And when user loses a device, user can use email account recovery to recover user's account on the other device. So from now, we explain the details. So details of how email account recovery works. We're showing the UI of the email account recovery feature in the Clave wallet we are building now. So in the first step, the user configures recovery settings, such as Guardian information. So in the Clave UI, the user just needed to specify the Guardian's email address, like this one. So in the second step, the Guardian will accept this request. So the Guardian will receive an email like this one from the relayer. And if the Guardian can approve this request, the Guardian just needs to reply to this email. And the Guardian will finally receive a confirmation email like this one. And in this process, our Guardian actually generates ZK proof of the Guardian's email and send this email proof on-chain to register Guardian's address. And once the user loses access to the private key, we actually start the recovery process. So in this process, the wallet user puts the Guardian's email address again, and the Guardian will receive an email from the layer in the same way. And if the Guardian approves this recovery request, the Guardian will reply to this email and receives the confirmation email. And in this process, the layer similarly generates ZK proof of the Guardian's email. And in the final step, the wallet user can complete this recovery request once more than threshold number of the Guardians approves recovery requests. However, there's a time delay before completing this recovery request. And this improves the security when the Guardian's email account is hacked, because the wallet user can cancel recovery request or if the email account is hacked. So in this way, we can keep the security and the accessibility of the user's account as long as the user can access to the private key or the Guardian's email account is honest.
Sweet. So we have those account recovery deployments audited and live on mainnet for both Clave, which will roll out in the Clave wallet over the next week for passkey wallets, and also in our recovery UI for safes. But this can be larger than just a couple of wallets. The idea is that any smart wallet can integrate this into their wallet. And so we've created a bunch of dev tooling to make it really easy for anybody to use these kinds of proofs. Concretely, for instance, the recovery module is a 7579 compatible smart account standard. This means any wallet is really easy to integrate with this specific account recovery. And even if you're not 7579 compatible, it's still quite easy to add account recovery to your wallet. We have a set of very simple APIs that users can call. Again, you don't need to read all the details here, but to trigger each of these requests, you can simply hit each of those APIs, and your own wallet or your own application can trigger any of these kinds of transactions directly. And finally, installing it to any kind of wallet in a front end is also very easy. Again, you don't have to read the exact code, but just the idea that installation is just 5 lines in, for instance, the permissionless.js smart wallet creation interface. You can read more about it on our docs on the right side, and we'll have more links towards the end. If you want to define your own kinds of proofs, not account recovery, but say any of the other application ideas, you can define your own kind of pattern in Solidity directly. Here we show that you can say something like recover account ETH address to new owner ETH address. Once you've defined this kind of Solidity code, you can then hit any API that any relayer has deployed. The API request looks kind of like this. Again, the main thing here is it's just about 10 lines, and it'll automatically handle sending the emails for you, getting the response, making the ZK proof, and sending it on chain. You can see, again, these docs for how exactly to build with this dev tooling over here, and we'll have a workshop tomorrow where we go over more of it in detail. So, for instance, you can imagine this abstraction can be used to build account recovery, email signers, login, and the email wallet primitive we talked about in the beginning, but we're excited for folks to explore with these kind of email trigger transactions to build more different kinds of things. So just to quickly recap, we went over the very basics of how ZK email works and simple kinds of proofs you can make, how to make new kinds of proofs very easily and access them from a shared registry. Then, switching from making proofs of received emails to making proofs of sent emails, we went over how you can do email-triggered transactions, and then account recovery. And finally, how we've made this really easy for new folks to either directly use or integrate directly into their wallets or projects, etc. We're super excited to jam more with folks. If people want, we'll have some booths specified on the left. You can catch us there after this talk and also over the next 2 days. And if you want to learn more about how to specifically use these tools in your applications, we'll have a concrete workshop tomorrow at 1:30 p.m. where we go over how to actually integrate each of these things directly with help from the team who actually built it. Sweet. So if you want to read, see, or hear more, we recommend following our Twitter on the left side, looking at our homepage in the middle on zk.email, and if you want to view an original copy of these slides, you can scan the QR code on the rightmost side. Sweet. Thank you for coming, and we'll take some questions.
Sweet. Thank you, Ayush and Sora. That was a very interesting talk, by the way, right? Yeah, I like to see ZKPs being used for something else rather than ZK rollups, right? And it mixes both Web 2 and Web 3. So we have some time for Q&A. So how about we take the first one? So it says, what ZKP framework you are using and why?
Yeah, it's a good question. So we've used and benchmarked all of the frameworks that we kind of listed in the beginning. We have versions in CIRCOM and now Noir and also now in ZKVMs like SP1 and RISC-0. We generally, so because most of these things are happening on, for instance, mainnets, we want to make sure that there's both high security and extremely high speed. So currently we use CIRCOM on the server side and also on the client side just because it's kind of the main one that's very mainnet ready right now and also can prove extremely fast on the server side and within like 5 to 10 seconds usually for most of the proofs we're talking about. But we intend to work closer with Noir to get those client-side proofs working in Noir and closer with the ZKVMs to get much more extensible proofs on the server side.
Yeah, that makes sense. Actually, by the way, you can upvote the questions so that we can see those that you upvoted first here on the screen. So maybe, or if we take the second one, would trusted setup ceremonies ever be required? If so, when?
Yeah, so this sort of depends on the exact proof system you're using. If you're using the CIRCOM proof system we have in production right now, then yes, you'll need to do a trusted setup. However, if you use the Noir system on the client side we're moving to, or the ZKVM systems on the server side that we also have, then you won't need to do a trusted setup for that specific circuit.
Yeah, so we have 2 votes. Yeah, maybe this question. So is there any pre-requirement for an email to be ZK approved?
Not really. Any email you've sent or received can usually be ZK approved because all emails require this DKIM signature to go through spam filtration. There are some restrictions, like for instance, Hotmail is not exactly pursuant to the standards, so some things that you can't access a to email within a Hotmail email. But in general, almost every email that you send or receive can be approved.
Okay, gotcha. I think we've still got time for more questions.
Yeah.
Yeah, maybe this one, when we consider, I think we can see them also here.
I guess the top one, is there a key rotation problem? Yeah, so the public keys that the DKIM verification actually happens with are rotated every maybe 6 months to 2 years. For some folks, it never rotates. The nice thing about this is that the smart contract that holds those keys is publicly auditable. Anybody can go in and say, yep, those are the keys that my DNS is fetching as well. But yes, to relay those keys on chain, there has to be some sort of a system of oracles. In our case, we use like a specific multi-sig in which all of the, like a bunch of autonomous computers are calculating those and putting it on chain. And you can also doubly verify that with, for instance, an AVS, TLS notary, or TLS proxies to ensure that all those values are correct. The important thing here is that you can use a single public value, that DNS value, to verify private data. And that public value is auditable. So the idea is that if there was ever some fault, somebody pushed malicious keys, there are enough time locks built into the system, and also ways to stop it or ways to override those key registries for each user that we think this is not actually that big of a problem in practice.
That makes sense. Thank you for the detailed question. Answer. Yeah, So maybe what if we take this one? Since DKIM private key is for the whole domain rather than per sender, presumably the security model relies, and we don't see the question anymore.
Yeah.
I mean, I'm just repeating the question for the live stream so that people, yeah. So the origin MTA preventing sender spoofing within the domain.
Yeah, so the idea here is that yes, because you're only verifying the signature from the domain, you are trusting that that specific domain is in fact like disambiguating senders correctly. The nice thing here is that most email providers that most people use, like Gmail, Outlook, iCloud, etc., definitely have this in by default because it would be very bad if they didn't. But we have noticed that some folks don't. So for instance, we disable most .edu domains from most of these models because often they don't have very good parsing of this kind of which sender exactly in the domain sent that email. But in most cases, for instance, that you received an email from Twitter or Devcon or whatever, usually you can constrain exactly the email address that sent it, and that's usually good enough. And they're usually using something like Google Workspace, so it's usually passable.
And in the context of the email trigger transactions, while this depends on the private key of the specific email or DKIM or server like Gmail, we believe this achieves a better trade-off between the UX and the security.
Thank you. So I think we're on time. Please thank again Ayush and Sora, and please upload them for their talk. And by the way, for those who joined us just recently, so there is a QR code at every beginning of the session. If you scan it, it takes you to the Devcon passport, and then there you will find, when you scroll down, the Q&A session. You just need your Zoo Pass, and then you can ask questions, upvote them, and we see them here. So in 5 minutes, we're gonna go to the next talk. Hello again. So we have our next speaker, Philippe Laferrière. So he works for Polygon in the Maiden team, and he works on the Maiden virtual machine. So today he's going to talk about lookup arguments. So you may have heard of lookup arguments. He's going to talk about lookup, which is one of these lookup arguments, and the lessons about integrating lookup with GKR in the Maiden VM. Please welcome Philippe Laferrière. Stage is yours.
Hello. So I'm Philip, work on the Maiden VM, and today we're going to talk about our lessons from integrating LogUp GKR in the Maiden VM. It's going to be fairly high level, so I wrote a little HackMD book at bit.ly/logup-GKR, where a lot of the details that we don't cover here are in that book. So for context, LogUp GKR is a technique proposed by Shahar and Ulrich around this time last year in their paper, Improving Logarithmic Derivative Lookups Using GKR. So in this talk, we're going to first look at what LogUp is, first of all, and then how LogUp is typically proved with Starks. And then we'll look at how you do it with GKR, which is the main purpose of the talk, and then our takeaways from doing so. So really quickly, LogUp is a protocol to prove the equality of two multisets. Multiset is a set where repetition is allowed. So they're super, super useful in virtual machines. They allow you to have practically unlimited stack depth, do large number of range checks, so making sure that a given value in your trace is within some bounds. And they allow communication between different parts of the trace. So for example, in your main processor, you could have an XOR and prove that XOR somewhere else in your trace. And the multi-set check is what you would use to connect the two parts of the trace. So for example, this is a depiction of the Maiden VM trace. So a 2D grid of numbers, effectively. And in this context, a multi-set check would check that the multiset represented by the green squares is equal to the multiset represented by the blue ones. So they're basically multisets on values in your trace. Multiset checks. So we'll jump straight into the equation. Unfortunately, we don't have time to talk about why that makes sense. It's in the book, but we'll take some time and analyze it together. So LogUp is, there's 4 sets of variables of interest. The Aij and Bij are the elements in your multiset A and B respectively. And then the M, A, and the MB are the corresponding multiplicities of those elements. So for example, if you want an element to appear 5 times in your multiset, but it's only once in your trace, you could set that M to be 5, and it's going to be the exact same effect. So a multiset element is, the expression is really its multiplicity over alpha, a random value, minus Aij, the element, Aij. So we have these two terms per, or actually k of them per row, where the I for the row goes from 1 to n minus 1. The big takeaway from this is LogUp is one big sum of fractions. That's the one main thing to get from this slide, and we're going to have to prove this. So how do we do it with Starks? So that's our equation at the bottom, and we'll just use an example. So we have a main trace of 2 columns, A and B, and each column contains one of the 2 multisets. So column A contains multiset A, and column B contains multiset B. And we can visually inspect that the 2 multisets are equal. They're just a permutation of one to the next. So the algorithm to actually do that, to implement the LogUp, is to add an extra column that we'll call P, and we say it's a running sum column. So how is it built? It starts at 0, and then following our equation, if we look at the first element, it's off by 1 compared to the trace, but all the multiplicities are 1, and so we have 1 over alpha minus A1, which is the element in the multiset A, minus 1 over alpha minus A2, the element in B. And that, again, is just from our equation. Then for the next row, we initialize it with the contents of the previous row. And that means we're basically running an accumulator. And then we add the new elements. So 1 minus alpha minus A2 is added from the multiset A, and we remove 1 over alpha minus A3 from B. Same thing over again. We initialize with the previous contents, add in the new elements, and since this is the last row, all the terms cancel out, and it's equal to 0. So the boundary constraints on this column are that it must start at 0 and end at 0 if your columns, if your multisets are actually equal. But we also have to check that each row is built correctly. And that's what we do in a transition constraint. So we're going to zoom in on that. So we have P here, and the transition constraint is basically what we just did in the previous slide. So Pi plus 1, so the next row, is equal to Pi plus the new terms. So when k is equal to 1, only 2 terms. This is not quite right because the constraints must be polynomials, and fractions are not. You can't have a fraction in your polynomial, so what we need to do is simply multiply out the denominators. And so when k is equal to 1, with only 2 terms per row, we get this expression, which is a degree 3 polynomial because we're multiplying 3 variables together. But that was when k was equal to 1. When k is equal to 2, we're going to have 4 terms in that row, so we're going to be multiplying 5 elements here, so degree 5. And so as k increases, so the more terms you have in your multiset per row, the larger the degree. The trick is, in Starks, you typically have a bound on your transition constraints, on the degree of your transition constraints. And so how we deal with this is we simply make a new column. If only we can only have, let's say, 2 elements here, we'll create a new column, again, a running sum with whatever elements are left over that we were not able to do with the previous column, and so on and so forth. It could go up to hundreds. So again, the takeaway of when we prove log up with Starks is that we need a collection of running sum columns. Main takeaway. Let's see how we do it with GKR. GKR, for context, is a protocol that proves the correct evaluation of a layered circuit. So here we have a layered circuit, and so effectively the prover evaluates the circuit and then uses GKR to convince the verifier that this was done correctly. With logup, we have a specific circuit that encodes the logup relationship. So we're going to spend some time thinking about how that circuit looks like, how it's designed, really. If you recall, logup is a sum of fractions, and so over your entire trace. So this is depicted by the sum of fractions at the bottom here. And to get the next layer, we're going to merge pairs of these terms by common denominator, just like what you did in high school. So on and so forth until we get just one fraction. And really we're going to stop at 2, but for intuition, we'll say that we get just one fraction. So that's not really a circuit, but it's a simple translation to get a circuit. Basically, every node in your circuit is going to have 2 numbers corresponding to the numerator and the denominator. And then to merge 2 nodes together, we apply which we define as the sum over those pairs, is really the sum of fractions. So the denominator here, if we look at AD plus CB, that's the denominator that we got from those 2 fractions, and then BD is that was the numerator, and BD is the denominator. So then what do we do with GKR on this circuit? There's actually slight modification to the GKR protocol, but we're not going to have time to go through this. Again, that's all in the book. So at a high level, the prover evaluates this circuit and then sends the output layer to the verifier. So only 2 fractions that represent the exact same sum that was in the input layer, but really with 2 fractions. So the verifier can easily check that this is equal to 0, and we'll also check the denominators are non-zero to make sure that they're proper fractions. And then prover and verifier are going to run GKR to convince the verifier that the circuit was properly evaluated. And that translates to that the output layer really comes from the input layer. It's basically the same sum, but represented in a different set of fractions. But we're not done yet, because we know that the output layer is equivalent to the input layer. We don't know yet that the input layer was properly populated from elements of your trace. To do that, we're going to have to do this in Starks, and we're going to have to add 2 columns to our trace. We will not go into how we do that, unfortunately, because it's like very cool and like quite clever, honestly. But the long story short is that we really only need 2 columns in our trace. So if we take a step back, when we were proving logup with Starks, we ended up needing a collection of running sum columns. Again, that can go up to 100 or more. With GKR, we needed only 2 columns, but with the overhead of GKR on top of that. So then the big question that we asked before starting is, which is best? And like anything in VMs, there's no simple answer. It depends on a variety of parameters. So we just went on and did it. And so there are takeaways from doing this. Many different parameters influence which technique is best in what circumstance, depending on what you care about. We're going to focus on 3. Hash function speed, the degree of start constraints, and the size of the bus. So hash function speed, when in Starks you have to choose your hash function, and by slow or fast, we really mean for the prover on the prover's machine. How fast is it to hash 2 numbers or whatever, or however many. So the reason why the hash function speed matters in choosing one or the other is that if you recall from logup, we were adding a bunch of columns. And each column adds hashing work to the prover. And so if that hashing work is expensive because you have a slow hash function, it's gonna cost a lot to add these columns. So the green check marks means favorable to GKR, to logup GKR. And the reason is logup in Starks needed a bunch of columns. In GKR, we only needed 2. And so if we go from hundreds to 2, that's a lot less work for the prover. Of course, there's the overhead from GKR, but if we hone in on that parameter, it's very good. Degree of start constraints, same idea. So if you recall from earlier, the degree bound on your start constraints is what made us create new columns, because we were not able to pack more. We were not able to pack a bunch of fractions in a single column. So the lower the degree, the more columns you'll need. And then the same intuition comes back. The lower the degree, the more columns, the more work for the prover. And so removing all these columns when switching to GKR is favorable to GKR. Again, if your degree is higher, you're removing fewer columns, and so maybe the gain is not as good. The last parameter is the size of the bus. By size of the bus, we really mean how many fractions per row are you adding? That K from the previous equation. So here, if you have a very large bus, so meaning you're adding a bunch of fractions per row, you're going to need a lot more columns. Same intuition. So a large bus is going to mean a lot of columns when you're proving it in Starks, and a lot of prover work that you're removing when you're switching to GKR. So this is our mental model, rough mental model for when to use logup GKR and when not to use it. So in the case of MindVM, we the rollup uses a slow hash function, so that was good. That was quite favorable. But the MineVM uses quite a high degree of start constraints. We use 9. 3 is quite popular. 5 is also used. So we're pretty up there. So not very good for logup GKR. And also our bus was kind of small. We only had a few extra columns for logup. So basically, by optimizing GKR, and GKR is based on some check, and there were a lot of optimizations there to get logup GKR down to be equivalent in prover time to Starks only. But as soon as we went back to a fast hash function, we used Blake 3, logup GKR was still slower. And it seemed like maybe it would maybe even never reach like parity, because our bus is small and our degree is high. We were not the only ones to implement this. Starkware also did that. And Andrew Milson was very nice and shared with us the numbers that they got. So they have, in their experiments, they used Blake 2 as a hash function, so quite fast. But they have degree 3 constraints. So very nice for logup GKR, and a very large bus, like hundreds of columns. And they were able to get a 15% improvement. And they will say that they're still not done optimizing, so they think they can get that even higher. But it just goes to show that even though they use a hash function that's fast, they were able to make logup GKR worth it. Again, this is all prover time. The one thing that this slide doesn't talk about is proof size and verify time. Maybe the big drawback for logup GKR, I'd say, is proof size. So these extra columns that we're adding and all the nodes, the circuit nodes for logup GKR are all in the extension field. So, for example, in the MineVM, we use Goldilocks, so a roughly 64-bit field. Extension field is where we do any kind of randomness is done in the extension field, and that's roughly 128 bits. So every number is larger. And proofs kind of get very large. For traces that we can expect in the rollup, we were getting maybe 200 kilobyte sized proofs just for GKR, and typically we're able to get it maybe at 80 or 100 kilobytes. So it really blew up our proof sizes up. And we're actually trying to decrease them. So so ultimately our current takeaway is that we're not going to use it for the first version of the MineVM, but we're also looking into making some pretty drastic changes in the future. And yeah, this is the mind map we're going to use when we do that, and whether or not we want to use logup GKR. But yeah, ultimately, it was a great experience and like a very clever idea by Shahar and Ulrich. So again, like most of the details we didn't talk about. If you go to that link, most of them are there. I tried and make it approachable. Feel free to ask questions on the HackMD directly. Send me a DM on Twitter or just message me, whichever. I'm happy to have more conversations about this. And yeah, hopefully you learned something. Thank you.
Thank you, Philippe. It was an insightful talk. So again, I just remind you that there is a QR code if you want to ask questions. But we have actually a few. So maybe if we start with the first one. Do we, in practice, mix GKR and Stark for different use cases other than lookup, I guess?
Yeah, that's a really good question and something that we start to think about more. Currently, logup is the only one that I'm aware of that is being used or even tried. But it is on we are going to think about more ways that we can do this, because now we have a clear use case or rather a clear example of how it can work. And yeah, but so far I don't think so.
So the reason is like just implementation-wise, you need to try it to see how it works.
So implementation-wise, absolutely. Even just understanding, like the glue from GKR to Starks was non-trivial to understand, at least for me, because you're going from a multilinear world to a univariate world. And there's some, but I'm pretty sure that some of the insights there can be reused for other purposes.
That makes sense. Yeah, well, if we take the second question, is lookup more GKR friendly than other lookup arguments?
Yeah, another good question. I do not know any other uses of, there might be, but I do not know other lookup arguments for that use GKR. So I don't know.
And you were using like lookups before introducing GKR, so it was Stark friendly, I guess.
Right. So we use logup only when we need multiplicities, because as we saw, it makes the degree, logup makes the degree go up pretty quickly because of these denominators you have to multiply out. I mean, a constraint degree, sorry. For most of our lookup arguments in Starks, we use good old multi-set checks. We call them like vanilla multi-set checks. They're based on, they're not sums of fractions. They're really, it's not a running sum column, it's a running product, and it's slightly different. Your degree is slightly better. So unless you need to encode multiplicities explicitly, we don't use logup. But I don't know how to do that other one with GKR.
Okay, cool. We have more questions. So what hash function you are using?
Right, so the MineVM does not, you can use whichever one you want with the MineVM. We use the MineVM in the mine rollup, and for that we use hash function RPO, which is a ZK-friendly hash function. And actually, I think we're going to switch soon to RPX.
So is it also?
It's like an improvement, as I understand.
Which is also Stark friendly.
Also, yeah.
Okay. Then next question is, how fast, slow is GKR verifier in Starks?
Yeah, good question. I think it's comparable to, from what I recall, I was focusing less on GKR verifier, so I'd have to go back. It was not drastically faster or slower. It was you were getting roughly the same, maybe a bit slower.
Okay. And does it change like in terms of the size of the lookup you're proving, or?
Yes, but in the numbers that we care about, so maybe traces of 2 to the 16, okay, or we typically around that, you didn't see many differences between. Okay. It was relatively constant. Yeah.
Okay, cool. If we can just scroll down to see more questions. Yeah, Maiden Love. Yeah,
that's a good one.
That's a good one. And maybe last question, any plans for hardware acceleration for the Maiden VM?
Yeah. So we have GPU support that is maybe even in our main branch yet, or at least soon to be. But we have active GPU work being done. More long-term, we're also looking at using ZK-specific chips, but that are not on the market yet. But okay, it's already in our
ASICs. Okay.
Yeah, right.
Okay, cool. Well, or if we give a round of applause for our speaker, Philippe. Thank you very much.
Thank you.
Yeah. About folding schemes, so just some housekeeping reminders. So there's toilets on your left, and you can take pictures of whenever you want, but just turn off the flash. And if you see a sticker, no photo, so please just don't take pictures of the speaker. So our next speakers are Arnaud and Pierre, and they're gonna talk about folding schemes. So ready for the next session? I think we've got some time, right? Hello again, and welcome for those who just joined us. So I'm Yusuf, your MC, and so we have the applied cryptography session going on, and this is the third talk. So the third talk is about the folding scheme library, and the speakers are Arnaud from 0xSpark and Pierre from PSE. Please make some noise.
Hi. Yes, so I'm Pierre, working at PSE, and this is a presentation done jointly with Arnaud, who is working at 0xSpark. So we are going to walk you through the library that we have been working on with Erika as well and Carlos over the past year. So let me first introduce you a bit to the concept of IVC, which means incrementally verifiable computation. So the main entry point to understanding what is incrementally verifiable computations is that those are kind of computations that are repetitive. So, for instance, you see this little math formula states that you can obtain the result Sn when you apply a function n times on some initial state, 0. So to give you some more concrete example, you can think of it as a machine learning model which always does the same inferences on some different data points, or maybe some virtual machine with a fixed set of opcodes which does some repetitive computations, or a rollup which always batch verifies signatures again and again and again, and even the blockchain consensus, where the same consensus algorithm is applied again and again. So what are the benefits of IVC schemes that use folding? So this is where the folding schemes thing comes in. So folding schemes are used to basically realize incrementally verifiable computation. And you can see on this diagram that the idea is that at every step of the function, you will get a public input, so the little z, and a witness, so w, the little w thing. And at every time the computation is being done, you will have a new public state, Z1, and maybe if you want to redo another step of the computation, you will have a new witness, W1. So what you can see, and that's interesting, is that the F function is applied independently every time. You do not have like a big circuit where you do some kind of loop and you say from I equals 0 to I equals n, apply the F function. No, that's not how it works. Here, the F function is really applied independently every time. So you get a prover that whose memory is basically dependent on the size of the function that you are applying, not on the number of time that you are applying the function. So that makes things very interesting. So you can use folding schemes for recursion. This is some form of recursion that we have seen because we are just inputting the previous state into the next step. And folding schemes, a folding scheme is a term that has been coined in the Nova paper. So it's something different from what you can see in some Stark protocols. It's here. What we mean by folding is really just basically taking random linear combinations of witnesses. And the main intuition is that you can have a folding scheme when you are taking this kind of combination between witnesses, because you can show that if you know two satisfying witnesses, then if you take the linear combination of those, then you can obtain another satisfying witness. Also, the main workflow when you are using folding schemes to do IVC is that you will do your IVC computation, maybe for n steps. You will get an IVC proof, and this proof is not succinct, so you will want to compress it basically using something that is called a decider, and it's basically a ZK snark proof. So we just snarkify the IVC proof and obtain a more succinct proof that you can then verify wherever you want, such as on-chain. All right, so let's just take a step back and try to think a bit about what folding schemes, how folding schemes look like. So there is now what I call the folding schemes zoo. So there are a lot of different kind of folding schemes because you have a lot of different kinds of arithmetizations, you have a lot of different kinds of use cases. Some use cases use lookups, other don't. Some have a uniform computation, some have non-uniform computations. So we end up with really a bunch of different folding schemes. Some are used for Plonkish circuits, others use some specific kind of arithmetizations, that are adapted to folding. Some do many-to-one folding, so not 2-to-1, but many-to-one folding, meaning instead of folding two witnesses together, you can fold n of them together, so it's a very efficient form of folding. You have also lattice-based folding more recently, so that's interesting for the post-quantum security properties of those kind of things. And so we really end up with some kind of zoo with many different folding schemes. And even in terms of research, it's a very active area of research. So, for instance, just in April 2023, there was like 4 different kind of folding schemes proposal and way to do VMs with folding schemes. So it's a really active area of research. Recently, there was some zero-knowledge layer that was proposed for IVC proofs. So you can generate your IVC proof on a client and then make it ZK. It's very efficient. And then, for instance, send that to a server to have the server compress the proof and send the proof on chain. So those have some really interesting zero knowledge properties. We also have lattice fold, which is post-quantum ready and is a pretty efficient form of folding. And yeah, so there is really a bunch of stuff to talk about today about what's going on in this area of research. But let's talk a bit also about applications, because I think that some of you are interested to know what's happening there. So for instance, we did one experiment where we were building a Bitcoin Lite client. So the idea was just to prove that the current block hash that we have has been obtained after n blocks. And so we, for instance, run a NOVA, which is a folding scheme, on the proof of work Bitcoin algorithm for 100K blocks. And in total, that costs us $30 to verify on optimism for running such a huge, absolutely huge computation that we wouldn't do using traditional ways of zk-SNARK proving libraries that we have today. We also have zk VMs today that use folding. So there is the Nexus team, I think, that is led by Jens Gross and Daniel Marin. They use, I think, Hypernova for that. There is also the Jolt team. They published an update actually today, stating that they were interested into folding, and I think they are interested for it regarding their memory checking algorithm for their ZK VM. There is also ZK machine learning. Someone baked into Nova a billion parameter, I think, or yes, something like a billion parameter. At least it was a 512 CNN network that they baked into Nova and for which they generated a proof. And I think it amounted to something like a billion parameters model. So you have also ZK machine learning. Yes, so there is really a bunch of projects that have been building on folding schemes lately. So yeah, for that we have built Sonobe, and this is what Arnaud is going to talk about.
Hi. So yeah, so once you are interested into being able to use folding schemes for your recursive circuits, so we have this library. It's like a very experimental thing intended for research, but we are starting to now polish things. So the idea was to have this modular library where we are able to add and test new folding schemes, compare schemes like apples to apples, and also that allowed researchers to easily add their own schemes, as happened with the MOBA paper by Nethermint. They published the paper where they used Sonobe to test their new design, which they implemented on top of Sonobe. And now it was a pull request in Sonobe, so now this is merged. So now part of it is in the library. But also the idea is to make it easy for devs to use folding. The idea is that they should have minimal code to be able to then fold the circuits, this idea of plug and fold. But also allow, since we are building this on top of the ArcWorks set of library, the idea is that it's easy to switch, thanks to ArcWorks, between different curves, but then in Sonobe, also switching between different folding schemes. And also, we have some experimental, ZK circuit language, interfaces where you can use other than ArcWorks languages to define the circuit that you want to fold. And also, the third kind of pillar of Sonobe was to be able to verify on chain the folding proof, because this was something that we were not able to find in any of the other folding implementations because of the Ethereum characteristics. So yeah, as a remark, this is a very experimental and research library, and for the moment it's unoptimized. So yeah, so that's the developer experience of Sonobe. This is what you already saw. This is the idea of the folding schemes, and this is how this maps to Sonobe. It's very simple. The dev just needs to define the circuit that wants to be folded, select which folding scheme to be used. For example, Nova plus cycle fold, but then you can swap and with just changing one line of code into using Hypernova or Protogalaxy. Then also setting the final decider that generates this compressed snark proof. And then in the case that you are using the on-chain decider, you can then also generate the Solidity code, like the template that you can then deploy, and you can use this to verify the proofs on-chain. Status of the library. So far what we have fully implemented is like Nova, Hypernova, and Protogalaxy folding schemes. The three of them using cycle fold techniques. And then also for Nova, we have like the full Solidity verifier there. For Hypernova and Protogalaxy, like we have the code in Rust that generates the proofs and so on, but it's just a matter of like putting time to doing the Solidity also. Then also we started to introduce this MOVA and Nova. These are just like variants to the Nova scheme. So it's like with some tweaking and some abstractions, we can reuse most of the already existing Nova code that we have there. So it should be easy to fit them in also. And then for the front end, like how you can define the circuit that you want to fold, this is done through some interface. By default is artworks, but as an experimental thing, which is a bit slower, you can also use Circom, Noa, and NoName. But yeah, so just to give you a bit of like a sense, Nova is using this random linear combination for the folding part, which this needs to be checked inside a circuit. So then Hypernova, instead of doing this random linear combination, it linearizes the instances and then runs the sum check to prove the relation. And then Protogalaxy is, instead of random linear combination, is doing linear combinations with the Lagrange basis in one of the settings, and in the other setting is also using the sum check. But just to give you a bit of sense of that different schemes use different techniques. So one of the goals also here is like to be able to see in different use cases which one fits better and so on. So having this modularity. Then, okay, so this is how it looks like the F circuit interface. This is like the circuit that you want to actually fold. You just need to implement this. Like the first three methods are just like very simple things. And then step native and generated step constraints, those are like the logic that you want to do at each fold. Step native is what you do in Rust, like outside the circuit, and generated step constraints is where you define the logic of the circuit that you want to fold. So this is like the constraint that you are folding actually. So just by defining this interface, like if you implement it, then you can plug this into Sonove, and then Sonove takes care of like wrapping this inside the augmented function circuit and doing the IBC folding and the rest of checks and so on. So the idea is to have this very simple interface that also this is used. So when you want to include a new ZK language into being able to use Sonove, just by implementing this for the language that you want to use, you already have it. Then this is like the usual code that you need using Sonove to fold the circuit. So the main idea is that here you define which folding schemes you want to use, and also like as you see this Pedersen G1, Pedersen G2. So the G1, G2, those are like the curves that you use. We need a cycle of curves, but you can pick most of the curves that are available in artworks. And then the Pedersen G1, Pedersen G2, this is like the commitment scheme that we use in the first curve and the secondary curve of the curve cycle. And then the rest is like more or less will be the same. Like here we are doing 100 steps of this proof step, which is like the actual folding of the IBC. And at the end, you can just verify the last one. And so here you are proving like that after 100 repetitions of this computation, you obtain this final step coming from the first initial state. So that's the main idea. As you can see, I mean, it's quite simplified. And easy to, it's easy to reason, easy to have this working and so on. And then when you want to change which folding scheme you are using, it's as simple as just taking this line, and then you can say, okay, I want to use still Nova, but now I want to have, in the first curve, I will use KGG commitments, so that then I can use the final decider, the on-chain decider, that I can then send proofs to Ethereum and be verified. Or you can say, oh, you know what? I'm going to change to Hypernova. So you don't need to throw away your code. You can just replace this line, and now you are using Hypernova. Or I'm going to use Protogalaxy. So you can then, doing this like easy line, one line change, you should be able to have this. Then, when it comes to the decider, so we've been folding. We have this last IBC state with the last IBC proof. So now what we can do is like we can compress it with the decider. So we have the off-chain decider and the on-chain decider. So it's also like a similar interface. And then here is how do you use it. And one of the key things was this on-chain verification. So was one of the goals, because and we've not seen any other folding schemes libraries having this on-chain verification. So the idea is that in the original Nova, this decider, this compressing of the IBC proof, is done through 2 Spartan proofs, one on each of the curves. In our case, since we are interested in verifying inside the EVM has some kind of restrictions. Like we are limited to a single curve, the BN254, and also constrained by the gas costs. So we had to do a bit of gymnastics to fit this. So this is like a very high-level idea. So we are using CycleFold. We end up having some instances, and what we do is we combine some Groth 16 circuit that also contains some non-native arithmetic stuff, combined with the KGG commitments proof. So at the end, in Ethereum, we just verify 1 Groth 16 and 2 KGG commitments, for the case of Nova, for example. So this is very succinct and cheap in terms of gas costs. And also, yes, so you can generate the Solidity code also from the library. To wrap up, some preliminary numbers. Just as a remark, until now we've been focusing on implementing the various folding schemes, not on optimizing. So that's why now we have the Nova, Hypernova, and Proto Galaxy, all of them using CycleFold. We've not been focusing on optimization and efficiency, but it looks like the current numbers that we have when we run some preliminary benchmarks, they look promising. And the next steps will be to start profiling, optimizing, and adding benchmarks, and like stopping adding new papers that are appearing, and focus for a few months to like optimizing things and making them a bit more fast and parallelizing and so on. And then getting to a first release, because till now it's just like commit after commit, and the interface might break. So some unoptimized preliminary numbers. So each folding step, this is the recursive iteration. For a minimal circuit, it takes like 300 milliseconds. There is this overhead of the fixed cost of the 50,000 R1CS constraints. So it takes this like about 300 milliseconds on a today's laptop. Then when you want to proof off-chain the decider, currently it takes less than 1 minute. It should be much less, but it's just that we are using pairing-based snarks on both sides of the curve cycle. The idea is that this should be using Spartan at some point, and the modified version of Spartan that uses the relaxed R1CS, so then it should be also quite efficient. And then for the off-chain decider, which is one of the main contributions from Sonobe, we have this big circuit at the end that does these gymnastics and non-native arithmetic stuff to fit into the Ethereum curve. That it takes less than 3 minutes in my ThinkPad. And the gas costs are 800K of gas, mostly from Groth 16 proofs and KGG proof. Well, 1 Groth 16 and 2 KGG proof in case of Nova. The idea is that this should be reduced to less than 500 with some tricks of the hashing and of the bound link inputs and of the combinations of pairings. Yeah. So just as a wrap-up, main takeaways that you can get from this talk. First of all, folding schemes are not a tool that fits in all the use cases, but when it fits into some use case that you have something that it's like the same structure of the circuit, very repetitive and done a lot of times again and again and again, then folding presents a big speed up compared to full recursion of other approaches. And then, well, some of it is experimental, the schemes that we have, and we have the on-chain verification, and preliminary benchmarks look promising, and the next steps in the short term is to optimize and benchmark well and do memory profiling and so on. And that's it.
Cool. Gracias, Arnaud. Merci, Pierre. Yeah, so I personally actually use Sonobe, and I can tell that it is quite generic and also easy to use. So if we take some questions. So the most upvoted one is the first one. So folding schemes initially gained a lot of attention, but we haven't seen many advantages in practical implementation against stocks. Can you compare them with stocks, and what are the advantages? Quite opinionated question, right?
Yeah, so one of the perspectives that we have on folding schemes in general is that it's not this tool that fits into all use cases, like the same hammer that you can use on everything. It's very kind of specific and like specifically in Sonobe, we have this IBC model. So this, you need to model your use case to that. So it will not fit all the use cases, but for the ones that it fits, then it's substantially faster than doing full recursion with Starks. But it's not as flexible as you will have with when you are doing full recursion, like for example, taking a Plonky to circuit where inside you verify a previous Plonky to proof. This is like full recursion. And so part of your circuit is doing the full verification of the previous Stark proof. This is more expensive. This is a bit slower, but it's much more flexible and easy to manage, and from the engineering point of view also. With folding is more specific, so not for all the use cases, but when you have a use case that it fits well, it's like in 300 milliseconds you can like do each one of the recursive steps.
It makes sense. Maybe you can also do folding with stocks, which takes us to the second question. What's the status of folding for stocks?
So our team didn't really work on that. Maybe you want to. Do you have something?
So there was some paper where they were showing how to do folding of Starks bounded to a certain number of repetitions. And I think the ARC paper came last month or something like this.
I think the one was like MOVA that does stocks folding, or is it something else?
No, MOVA is like a variant of Nova.
Okay.
There are being improvements, but so far this library has been focusing on IBC with like R1 CS or CCS surrounding things, not with Starks. The same for lattice fold. I see next question regarding to lattice fold.
Yeah.
Lattice fold also requires a different so you work over the rings of polynomials and not on the like finite fields that we use in the traditional snarks. So also it will require like having first like some layer of all this like instead of the field arithmetic, the ring stuff that it's not at least in our works. So yeah, and the folding Starks, it looks promising because Starks are already fast. If we can get to a state where we can use the folding techniques. So the main idea is that with folding without Starks, we use these homomorphic commitment schemes so that you can combine commitments to some vectors or polynomials, and then this result of this linear combination of them still holds some relations. With Starks, since the commitments are not additively homomorphic, we're not there yet, but it looks like the people in the academia or behind the papers will bring some improvements.
Yeah, I think Dan Bonnet is waiting for you to implement lattice fold. So next question. Folding papers work with different arithmetization, R1CS, Plonkish, CCS. Now that you did the implementation, is it efficient for anything other than R1CS? Another open-ended question.
Is it efficient for anything other than R1CS? So there is basically lattice fold that is not using the R1CS optimization, where you can use the idea that are from the previous folding papers for a different kind of arithmetization. So there is also the question above, what's the status of folding for Starks? You can reuse the ideas that were in folding papers for another kind of I guess the AR arithmetization. So for a different kind of, for an arithmetization that is different from R1CS. So yeah, I guess that answers the question.
Yeah,
if I understand.
I think so, yeah. If we can just scroll down to see the questions, or maybe I can check them on my phone, yeah. So how does Sonobe compare to Nexus?
So first of all, Nexus is like a full company backed by VCs, and their team is amazing. Like it's a bunch of people from Stanford, and so very good team. Sonobe is like a small team, like we are like 3-4 people, and we've been doing this, but like in a more experimental, like not production focused. But so far, the benchmarks that we run, when you run the benchmarks in the same machine, for the Nova implementation, it's almost like the same. Like it's like from 300 milliseconds in Nexus Nova to 310 milliseconds in Sonobe. So it's almost the same. Hypernova in Sonobe is much slower, but because it's far from being optimized. And then we also have the Protogalaxy, but in Nexus it's not there. But so the thing is that both libraries are based on artworks. So like the maximum speed should be similar. And both are using cycle fold, which like the Microsoft Nova is not using cycle fold. So it has a different trade-offs.
So we're on time for the Q&A. So what if we thank again our speakers and give them a round of applause?
Thank you.
Yeah, so we have one more session next, so I'll be back like in a few minutes. Hello again, and welcome to those who just joined us. So we are running the Applied Cryptography track this morning at Stage 3. We had 3 wonderful talks, and we have more for you guys. So I'm excited to introduce the next speaker because he's a colleague of mine. So he works on GNARC and linear ZK EVM. So please, a round of applause for Ivo Cubias. Thank you.
Hello, good afternoon. Nice to be here. So today I'm going to talk about a bit about the optimization techniques, what we have done for making the proof recursion in linear and also in GNARC a bit more efficient. So I work on linear and I mostly work on GNARC. So GNARC is an end-to-end library written in Go for writing circuits which can be proven using SNARK proof systems. So you can write circuits, you can compile it into constraint systems, for example, R1CS, Blankish. Then you can run the trusted setup, particularly for the cross-16. You can use GNARC for proving using different optimization engines, so using CPUs, GPUs. And finally, you can use GNARC to verify the proofs. So we have the verifiers written in, for example, for the native verifier, for the mobile verifier. It's also possible to verify the proofs recursively in another SNARK. Or we can also compile a solidity verifier. So you can also verify SNARK proofs on chain on Ethereum. So let's set the stage before we start. So what we want to do, let's say we have some kind of statement, which can be a mathematical statement or a computer program. And we have some inputs. We have the secret input and the public input. So the secret input is something what only the prover knows. The public input is known to everyone. So for as an example, what can be a statement? A statement can be something very simple. For example, I know the factorization of RSA primes. So I know two factors which multiply together result in some prime. And so, for example, I can prove that I know a solution to these RSA factorization challenges. And I can obtain the challenge money, but without revealing what are the particular inputs. Because if I would reveal it, maybe someone will front run me, and they will try to get the money themselves. So what happens is that first we take the statement. We do some kind of pre-computation on that. So we get some expanded statement, and then the prover runs this program. So for example, the prover gets some kind of execution trace. The prover proves using some technique, and we get a proof. And what we want to have usually is that the proof is short. What does it mean for the proof to be short? So the proof should be short in the sense of this expanded trace. So the steps, all the intermediate results of the computations. So, and if it is shorter, then it means that we have already won. So we have some short proof of this computation. And we also want the verifier to be fast. So the verifier should run faster than running the computation itself, because otherwise, what's the point? And complexity-wise, maybe we want that the proof and verifier work it is, let's say, asymptotically faster. Maybe we want them to be, let's say, logarithmic in the size of the computation steps, or maybe a square root. Or it will be very, very nice if it will be constant size. And optionally, we would like to have zero knowledge sometimes, but in a lot of applications, it's not necessary. So let's say some of the proving schemes. So there is the sum check, where essentially, if we represent the statement as a multilinear polynomial, and then the prover shows that let's say some property of this multilinear polynomial holds, and it doesn't require some very fancy mathematics. It's essentially we just evaluate polynomials. The problem with the sum check-based approach is that the verifier needs to do the final eval. So it means that the verifier needs to evaluate this sum check multilinear polynomial at some point. Then we have GKR, which is very similar to sum check. It's just layered. It's a bit more structured. We have Starks, which are based on hash functions. So we can have some kind of polynomial constraints between different steps and different columns. We have cross-16, which is one of the first pairing-based systems. And the nice thing about the cross-16 is that the proof size is constant, and also the verifier work is constant. But it requires a lot of pre-computation. It requires per circuit trusted setup. And finally, Plonk. Plonk is nicer in the sense that it doesn't require per circuit trusted setup, so it can use the universal trusted setup. There are, of course, a lot more, but I would say in the big picture, these are some nice examples. So let's say the issue is that for the first three schemes, they are very fast, and they do not require any particular kind of assumptions. They only do finite field arithmetic and hashing, and no assumptions at all. So we just have to choose the hash function. But the proofs are not that short. So for the sum check, the proof size is logarithmic in the number of, let's say, in the number of steps. For Starks, I think it's square root. So it is shorter, but not very short. So if let's say if the statement, the input is huge, in hundreds of millions of steps, then the proofs are still big. For the last two, the issue is that the provers are slower because we use the fancy mathematics called pairings and KZG commitments. But the proofs are very, very short. So the proofs are, for example, constant number of some group elements, and the verifier work is also very short. So if we measure it concretely on a native machine, so it means that the verifier work is, for example, milliseconds. why we want the verifier work to be efficient and short is that when we go to L1, then it concretely means that we pay for less gas. So what should we do? We have fast provers, we have fast verifiers, we have slow provers, we have slow verifiers. So we can just combine like different approaches. Let's say we can combine the approaches because like one of the statements what we can prove is the verifier implementation for the fast prover. So let's say if you have some very big statement, then we'll just use fast prover first. We get some proof, which is let's say not constant, but still smaller. Then we provide this as an input to the slower prover, but because the input is already sufficiently small, then the slower prover is actually also relatively fast, so we can run it nicely. And in the end, we get a very small proof, very fast verifier, and we can post this on Ethereum, and we are done. So we get best of the both worlds. We have the fast prover, we have the fast verifier, and we do not pay a lot of money. We don't pay a lot of money for verifying the proofs. We can use the like similar, let's say, combination techniques, CK pipeline combination techniques to compute the proofs in parallel. So let's say we have, in the context of rollup, we have a lot of blocks. So we can prove actually the blocks in parallel because even the fast provers, they are slow. So they take minutes. So we can actually run, let's say, up to like 400 proof generation in parallel. And then we can aggregate everything into a single aggregate proof. And we can post that on Ethereum. So this also gives us some additional saving in posting the proofs and in finalizing the L2 on Ethereum. So to summarize a bit, what different kinds of recursive proving we have to do. We have to do the PN254 block verification in PLS 12.377. It's for the pre-compiles. Then we verify the fast proofs, the vortex proofs in PLS 12.377 block. Then for the proof aggregation, we use the PLS 12.377 block proof verification in PWS 6.761 block circuit. And finally, because Ethereum only supports the PN254 precompile, then we have to compress it back into some other curve, and for that we need to use the final approach. So what's the cost in verifying block proof? So there are the different steps. So first, we need to do some hashing to get the random challenges. We have some exponentiations where the exponent can be a variable or it can be a fixed value. We have scalar multiplications. And finally, the most complex part is computing the pairing. And pairing consists of two parts. So it consists of Miller loop and final exponentiation. And today's talk, we are focusing on the Miller loop and also final exponentiation. So, like, what can we optimize? So first, we work in elliptic curves. So what does it mean? So we have some base field. So we have coordinates which are defined over a base field. What we can think about it, essentially, they are like some integers modulo some prime number. And an elliptic curve is all of the solutions to some elliptic curve equation, y squared equals x cubed plus ax plus b. And so the elliptic curve is a solution to like this equation. So we have a lot of points. And there is also a scalar field. So let's say like if you fix a point on an elliptic curve, so like all the multipliers of it, so they if you have only a single, let's say a single group in the elliptic curve, so they generate it generates like all of the points, and the scalars they also construct a finite field. So we have two fields. We have the base field, the points, and we have the scalar field for the scalars in the elliptic curve. It's really great if we have some kind of match. So right now we are thinking that we are verifying recursively, so we are verifying a Planck proof inside a Planck circuit. So all the arithmetic in a Planck circuit happens on the scalar field, but we need to do arithmetic in the base field, in the scalar field, so like in different fields. So we have some kind of mismatch. It would be really nice if we have a match somewhere. So the scalar field corresponds to the base field of some other curve. And there are, like, sometimes we have it, but most of the times we don't. So how can we fix it? We can just use multi-precision arithmetic. So we can do it like naively as for like in library. So we just split a big value into limbs. So for example, we split it into like 64-bit limbs. So if we do it like this, then when we think about the multiplication, then we essentially have to use the school book multiplication. And the school book multiplication, the asymptotic cost of it is quadratic in the number of limbs. So it's not super beneficial, or it's not super efficient. And also consider that we are only doing the integer multiplication. We also have to do the modular reduction, so we have to do it several times. So a bit more clever approach is actually to use the polynomial representation of these multi-precision integers. So it's the same, but we look at the polynomial where the coefficients are the limbs of this multi-precision integer. And in this case, because when we are creating a Blanc proof, then like actually the prover can just hint some values. The prover can hint the result and also the quotient, and then like we can check that this polynomial is equivalent at some random point. So when we compute the pairing, so the computations in a pairing happen in different groups. So they happen in the group of the points, but it also happens in the extension fields of the base field. So we have the G2, GT for the pairing. And so what are the extension fields? So essentially extension fields are a field of polynomials where the coefficients are defined over the base field. And we also have to have like some let's say fixed modulus, which is like some irreducible modulus, which essentially defines like how we can reduce values when they are bigger than the modulus. It's a bit simpler to look at the extension field elements as vectors, and then the multiplication. Multiplication inside the extension field, it's exactly as for the multi-precision integers, and we just do the modular reduction using the given modulus. We have the same problems for the extension multiplication, is that the complexity is quadratic. So if we have high extensions, the 6th degree or 12th degree extensions, then it's just like very complex to compute. So what for optimization we can use like towers of extensions. So like instead of going to the 6th extension directly, we first go to the cubic extension, then we go to the quadratic extension, and then the multiplication becomes somewhat simpler. So as a concrete examples, let's see. Like if we consider a quadratic extension over a cubic extension, if we do a multiplication, then we need to do one, let's say, one cubic multiplication. Also for computing the result of the second limb in this 6th extension, we have to do 2 multiplications, cubic multiplications. But before we mode reduce, we can just add the polynomials, because like if you recall, then if you add polynomials, then the degree of the resulting polynomial, like, it doesn't decrease. It may actually, I'm sorry, if we add 2 polynomials, then the degree doesn't increase. It may actually like decrease if something cancels out. So there was a very nice result a year ago by Feltrod Prime, and he actually showed that when we compute the extension multiplication, then we don't have to do it like using the towers. We can do it directly. And the idea is very simple. What we have for the non-native multiplication is that essentially we don't compute the value, but the prover provides the value using a hint, and also the quotient. Then the verifier provides some kind of challenge using Fiat-Chimere usually, and then we just check that this direct extension multiplication is correct. So this should be more efficient, and we wanted to figure it out. So we found the direct extensions, and we started to write out these equations, and we started to see like how beneficial it is for that. So the previous result was only for PN254. We wanted to implement also for the other curves, so for PWS6 761 and PLS12 377. Okay, let's write it out. And so we get something like this. So it looks something simple. But the issue is right now that all of these multiplications, what we have right here, they are non-native multiplications. So, like only for the left-hand side, like we see that we have at least one. So we have like 10 or 11 non-native multiplications. And if we do the non-native multiplication in this way that we provide the result using a hint, then we have to do a lot of range checking, and this is not like that efficient. So let's try to improve this approach a bit. And so actually, we can improve it like very simply, I would say. So when instead in non-native, if instead of the multiplication, we want to evaluate something more complex, some like let's say some multivariate evaluation, where like instead of multiplication we have something let's say a times b plus c times d plus e times f and so on. So we have something more complex. Then we see that actually we don't need to compute all the intermediate results. So we only need to know what is the full result of this multivariate evaluation. And the complexity stays the same regardless if we do non-native multiplication only, or if we do this more complex multivariate evaluation. And if we implement it this way, then actually like evaluating these extension polynomials, like it becomes a lot more easier. So let's now write it out again, like in full. So we have the A, B, C, and N and P. So what we do, at least in Knark, is that we do not evaluate non-native and extension multiplications directly. We just write it down that we need to evaluate them later on, and we only provide the result using a hint. Because this allows us to share some of the computations. So for example, if we, instead of computing a Fiat-Chimera challenge for every check, we compute it over all checks. Like if we Fiat-Chimera or we hash all of the inputs, then we can share this random variable Z. We can compute all of the powers of Z. We evaluate the P of B at this one place because it is shared over all checks. We evaluate A and B. And now we check. So we replace this A part, the B part, and also the P part. And now we have like this one big thing what we need to evaluate. But this is let's say something what we can evaluate with the non-native operation, which corresponds to a single non-native multiplication. And if we count it, so on average, let's say if we amortize the P part, then we actually only have like non-native operations, and this is very efficient. So for evaluating the extension multiplication, we only need 3 non-native operations. And the main cost here is checking the range checking the hinted values. So actually doing the multiplications themselves, it's cheap, but it's just like when we work in 64-bit limbs, then we have to check them. When we look at the benchmark results, so this is the number of constraints in Plonkish. So on average, we were able to get 40% reduction. But there are like still some ideas what we have for improving the performance. So like one of the things to notice is that we don't need to actually find every quotient. We just need to like know that there is a quotient. So if we look at the random linear combination, then we can also provide a single quotient. And we can apply it also for the like different operations, and we can also apply the same technique for different curves. Thank you.
Thank you, Ivo, for the presentation. It was nice. Are you ready for some Q&A?
Yes.
So let's look at the questions. Why do you need 4 different combinations of Plonk in Plonk?
Yeah, it's a very good question. I ask it myself like many times. So we need it because we are like on one hand we are restricted to what we already have. So for example, if we want to verify a Plonk proof on Ethereum, then we can only use PN254 because this is the only precompile which is provided by Ethereum. And otherwise, if you would like compute a pairing using let's say an assembly implementation, it will be just expensive. For proof aggregation, we would need to have, let's say, a chain of, or let's say, two chain of curves, where like the scalar field of one curve corresponds to the base field of the other curve, and they don't come like that often, so we have to particularly construct them. And for example, because PN254 is already given, we cannot construct a two chain for that. So we also had like some other other way, because in linear, for example, we have to prove also like pairings. So let's say like if someone calls a pairing precompile on linear, then we have to prove it that like we have computed correctly. So we have to show PN254 precompile, but let's say the curve we are working in is PLS12377 for aggregation reasons. So it's just is what it is.
Makes sense. So next question is, can you show the benchmarks again?
Yes.
Actually, we have like a technical issue.
I'm sorry.
You can only show the questions at the end.
Yeah.
But you can take the questions offline with Ivo after his talk. So the next question, does it work inside Nova folding step?
It's a good question. Unfortunately, I cannot answer it. Probably. I think it probably would. But I do not know the techniques exactly to answer it concretely.
Next question is, how do you generate randomness in circuits?
Okay, that's a very good question, and actually, like this is one of the nice improvements what we have. So for Plonk, what we do is that we don't use vanilla Plonk. We use like a variation of Plonk, where if we want to, let's say, hash some variable inside the Plonk circuit, then we like copy this variable into this another column of of Plonk. So we have a different one more column, and then essentially we use the commitment to that column as the random value.
So we don't see the next question, but I can read it from the phone. Can you use Karatsuba for direct multiplication instead of schoolbook? I think
Yes.
it's for the extension, maybe.
Yeah, we can. And actually, like this is how we did things before, yeah.
And I believe it's going to be some more optimizations than compared to the benchmarks.
Yep.
And what if we take the next question?
There's one more.
Yeah. Can you use this technique to anything that can be expressed as polynomials? I think you explained that for multiplications.
Yeah, we can do it. So we have a plan to also use it for, let's say, elliptic curve operations, so for additions, doublings, scalar multiplications, and we also already expect for it to give like a lot of performance improvements.
And we have one final question. It says, can we use the same non-native field arithmetic mechanisms to prove SECP 256K1 operations in BN254 scalar field?
Yes, we can. So we prove SECP in PLS12377. So on linear again, we also have to prove the ECDSA precompiles, and so yeah, we can do it. We can do it fairly efficiently, I would say. And like for us, because all of the methods or all of the techniques what we use, like they are very generic, so we can use the field what we emulate and the field what we work in. So everything's generic, and it will work very well.
With respect to this question, it means it's already implemented?
Yes, so it is implemented. You can just take it as is.
Okay. So thank you again, Ivo, and can you join me uploading Ivo again?
Thank you.
Thank you. So we have one more session for which I will be the MC, and then we're going to switch MCs. So I'm going to be back in 5 minutes to introduce the next speaker. Thank you. And welcome back. And please, for those who are just joining us, have a seat. So I'm Youssef, your MC. This is my last session, then I will go probably get some food. So next talk is about Circle Starks, GPU implementation. So this one is implementation focused, and it's going to be presented by Daniel and Julian. Please, a round of applause for our speakers.
All right. Hello, I'm Daniel from Nethermind, and this is Julian from Eric's, and we're here to present Circle Stark GPU acceleration. So what is a Circle Stark? We're going to start pretty high overview. Well, this is your classic proof system. So a Circle Stark is a proof system. You have two sides, a prover and a verifier. And the prover wants to send over some proof, usually some obfuscated data of like private input and some computation to the verifier. And the verifier, sends back either accept or reject, and does so in a series of challenges. And usually in production, we don't really use the challenges in these queries. We instead replace it with some hash function. And just going over the acronym for those who are not quite familiar, zero knowledge just stands for the fact that we hide all the private input and the computation away from the verifier. The scalable stands for the fact that as the computation increases in size, the verifier and the prover run faster and faster. And one of the key things is that the verifier runs much faster than the prover. Transparent just stands for the fact that we rely on public randomness, so think hash functions. And one thing about the difference between this and ZK snarks is that ZK snarks use some trusted setup. And usually there's some data remnants that you need to take care of. And if you don't, it might nullify the system, whereas for ZK Starks, we don't actually have this. And finally, arguments of knowledge, just referencing the soundness of the computations. So this is just making sure that everything is secure within the technology that we have today. So let's talk about a matter of efficiency. For ZK Snarks, we use field sizes that are really large. These are 2 to the power of 256, and they use it because the elliptic curves that they use underneath require this for the actual security. Whereas for Starks, we don't really need to use all of this space because we are not actually using elliptic curves. We're instead working over just the field itself. And the computation size that we're usually using in production is around 2 to the power of 28. So we have a lot of we have exactly 2 to the power of 228, like as the upper bound, bits of unused space. And something to think about is that about a 4x increase in the actual field size, and you can think of field size as like a prime number, is equivalent to about a 9x increase in the actual computation size. So where do we go from here? We want to decrease the field size while also keeping in mind that the lower bound of this like 2 to the power of 28. So we need some field size that is still greater than this, but at the same time, we want to get low enough such that we keep in mind computer architecture. So 32-bit CPU arithmetic operations are very, very efficient. So if we can find something in this area, then that's very ideal. So just looking into previous primes that were used, we start with Stark field prime, which is 2 to the power of 252, and slowly we make our way down lower and lower, and until we finally get to the Mersenne 31 prime, which is what we use actually in the Circle Stark. And one thing you'll notice is that there is a +1 basically for all the primes before Mersenne 31. And this is on purpose. This is to unlock basically one of the core features or core functions that Starks use, which is a fast Fourier transform, or if you're thinking in terms of like finite fields, it's a number theoretic transform. And in order to actually use this, it requires as a generalization that the field, the prime, -1 is really easily divisible by 2 a large number of times. And with the Mersenne prime, if you see, if you subtract 1, you get 2 to the power of 31 minus 2, and this isn't really divisible by 2 other than a single time. And so what do we do? Mathematicians actually instead map this field onto coordinates of the circle, and by doing so, we gain 1 extra point. And this 1 extra point is what allows us to actually use the Mersenne 31. And that's why it's called Circle Stark, because we're using the circle as the kind of the group in order to unlock this FFT that we're using. And so the Mercen 31 is very efficient on 32-bit architecture. There's lots of optimizations that you can do to really bring this out. And as opposed to like baby Bear Prime, which we saw in the previous slide, it's the next higher field size. It's basically a 1.4x performance increase.
All right, thanks, Daniel. So some basics on GPU optimization. To be honest, GPUs are used because they can handle many simultaneous calculations, but there are also many uses for this. So we will fall in the first two categories, which are data-intensive computations and algebraic operations. There's also the original purpose for GPUs, which is point number 3. This comes with some problems. So GPUs and CPUs have different memory spaces. One cannot access the other's memory space, and copying data from one to the other is expensive. This means that we have to be efficient when working with memory in these different spaces. There's also the fact that memory accessing is not trivial. So memory accessing in GPU is best used coalesced, which means GPUs benefit from the use of consecutive memory accessing. And sometimes our algorithms are made so that memory access is complicated. This means that we have to find a balance in which we play around with our algorithm's memory access and the most efficient memory access, which is coalesced. There's also benefits to this. We wouldn't be doing this if there weren't. When we launch threads to process our data, they will run concurrently, so they'll compete to use the resources of the GPU. But the GPU can handle some threads at the same time, and this is what benefits us. So this will help our calculations be parallelized and run fast. There's also the fact that some architectures, we'll talk about CUDA here, bring you some particular optimization heuristics or optimization tools. We won't talk about them much here, but here are some of them. Consecutive memory access operations and shared registers are stuff that are like tools that are very specialized, but yeah, not much focus on them for this talk.
Just putting some notes onto the actual problems that we have. So one of the main things that we have for problems is the efficiency of data transfer, so from CPU to GPU and back and forth. And when we're working with really large computation sizes, really think 2 to the power of 28, copying back and forth anytime we want to actually offload the functionality of the prover onto the GPU comes at a very steep cost. The solution is really quite simple. We keep most of the data on the GPU to run throughout the prover time, and yeah, that's pretty straightforward. But let's look at a different problem. We have a problem of memory access. So the way just GPUs work is data that's close together, you can think about it. Accesses are very efficient, but for things that are really far across, can lead to a lot of overhead and lots of downtime. And at least for our use case, when we're doing FFTs, we have to access data from this really large set that's really far apart. And this poses a problem of all this extra overhead. There's a few solutions to this. One is the fact that we can kind of break down the data sets into smaller chunks so that the data access is a little bit more similar or nearby. And the problem with this, though, is that you introduce a little bit of overhead for actually reorganizing the data, right? Reorganizing and having copying on the device itself. Well, another solution that we can have is breaking down the functions into smaller and smaller kernels. And by doing so, you introduce the overhead of actually calling these functions. But I think more than anything, the optimizations that we're working on and that we're continuing to improve on is a combination of the three, right? We want to minimize these data transfers, we want to have efficient memory access, and we want to reorganize and break down these functions as few times as possible. And one thing to note about, I guess, other hardware that's in the ecosystem is one is FPGAs. They also work similarly to GPUs in that they work in parallel. The advantage is that they're a lot low latency. The con, however, is that there is a high developer complexity, right? So there are a few teams, but I think as we get further down the year, we'll see more and more teams actually working on this. And as for ASICs or any other ZK-related hardware, we need to manufacture these and design them way in advance. So until we actually have ZK systems kind of converge to a single point and have mass adoption, then we'll kind of have to wait and see.
Okay, so for a real-life case study of this being applied, we're going to review first a sequential algorithm, which is a component of the circle start prover. Then we're going to make it parallel, and then we're going to compare both of them to see how they fare in terms of performance. So bad chambers is the name of the game. It's a SU component we'll parallelize. This is a circle start prover. Its purpose is to calculate the inversion for a lot of numbers, okay, a lot of field elements. But since calculating the inversion for a field element is an expensive operation, we'll use something called Montgomery's trick. Okay, this Montgomery's trick is the sequential algorithm we're talking about here. So let's start with 4 field elements. I chose 4 because it's simple to explain. We calculate the accumulated products for each of these field elements, which means beta 1, beta 2, beta 3, and beta 4 are the accumulated products up to A1, A2, A3, and A4, respectively. But this is inefficient, because if we calculate it this way, programmatically, we can use that. We can see that we multiply a lot of them repeatedly. So we can rewrite this as is, right? We can rewrite this by using the previously calculated accumulated product. This is simple to see, but it's also relevant and very important, because when we want to parallelize this will be a limiting factor. Then, when we're finished, we take the biggest accumulated product and invert it using the extended Euclidean algorithm, which is this expensive operation I was talking about. And then we see this little trick to calculate the inversion of the very last element at first. So intuitively, because there's no division in field operations, we take beta 4 inverted as 1 over the product of all the numbers. This is intuitive, once again, but it helps to see how when we multiply it by the previous accumulated product, we cancel out all the numbers that we don't want and end up with 1 over A4, which is, once again, intuitively, the inversion of A4. The same thing can be done to calculate the inversion of the previous accumulated product this way, by multiplying the inversion of the whole accumulated product by A4 and getting 1 over the accumulated product from A1 to A3. And this helps us calculate the inversion of every single number we have in our list. A4 is calculated there, A3 inverted is calculated there, A2 inverted is calculated there, with the same intuition, with the same trick. And then A1 is an edge case. So yeah, it's easier to calculate. Now, this turns a potential n field inversions, right? So for an array of size n, it replaces n field inversions with 3n multiplications and 1 inversion. This is way cheaper, and we like this trade-off. Now, as I mentioned, Montgomery's trick cannot be parallelized as is, because calculating any accumulated product means you need to have the previous one. And that means, strictly sequentially, you need to calculate each one. And we'll adapt this algorithm for it. We'll parallelize it so we can compare them later. This is the adaptive trick to be able to parallelize it in GPU. We start the same way with 4 field elements, but we'll make an assumption that will help us adapt it, which is, we'll suppose the amount of field elements is the power of 2. We take those elements and multiply them by pairs, okay? Multiply them by pairs, and we have beta 1 to 2, beta 3 to 4 as the accumulated products by pairs, and beta 1 to 4 as the whole accumulated product. Now notice that this tree can be parallelized in the sense that one can calculate each node of the same level of the tree at the same time. Okay? This is useful because then we will want to send those calculations to run in parallel to the GPU. Now we take the whole thing, the whole product, and invert it with the expensive algorithm, just like before, and we decompose it, a similar intuition than before, right? We can calculate beta 1 to 2 with beta 1 to 4 inverted and beta 3 to 4 this way. Okay? It's the same as before, just that the numbers in the numerator change. A3 and A4 are in the numerator and cancel out with A3 and A4 in the denominator, and this is what we get. 1 over A1 times A2, which is intuitively the inversion of beta 1 to 2. So the tree is completed by doing the same thing in the other side and finally decomposing the accumulated product for each of the elements that we wanted to invert. And we have all the inversions here. So once again, this same tree that I showed you here can be parallelized the same way as the previous one. Now, apart from parallelizing it this way, one can optimize it further with CUDA-specific or architecture-specific optimizations. But even, even then, you can see the difference. It's ridiculous. This is compared against CPU using AVX. AVX is a technology that lets you handle single instructions with multiple data in CPU. So that's even better than CPU by itself. And the difference is still ridiculous. This is for 2 to the 24 elements to be inverted. And this is how it scales with bigger arrays. So what did we learn? GPU parallelization is very powerful. And a simple heuristic goes a long way. So a simple parallelization can handle a lot of data very quickly. This is a circle Stark prover. And we see how GPU makes the difference here in accumulated time measurements. So this is the time that it takes to run the prover up to that point. So it's accumulated. And you see that the differences are abysmal. This is in the order of milliseconds. Okay? So the GPU prover is way faster than CPU using AVX. Okay? So summary, like takeaways from the talk. What did we learn in the talk in general? First, circle Starks use smaller fields to balance security and efficiency. Harnessing GPU power is vital and easier than you think for the computation of cryptography primitives. And of course, we should keep an eye on future hardware acceleration trends because the future is in FPGAs. Okay, some due thanks. We wanted to thank the Ethereum Foundation for allowing us to be here and organizing Devcon. From Eric's, we wanted to thank Nethermind for letting us work with them. That was amazing. We appreciate it very much. And yeah, I think that's all. Thank you very much. You have some resources on Eric's QR, and you have also Nethermind socials here. I hope you appreciated the talk. I hope you learned something. And yeah, thank you so very much.
Yeah. Thank you, Daniel. Thank you, Julian. It was a nice talk. I appreciated how you kept it high level, but also low level. It was nice. Thank you. So why if we take some questions? So the first one, since modern CPU are 64 bits, why 32 bits field are more efficient?
So at least for the operations that are on that architecture, I understand that you're concerned for like 64-bit, but a lot of the actual arithmetization for the underlying functions is optimized for 32 bits. So we can work with 32 bits very efficiently.
Okay, so next question is this GPU prover open source? Works with Metal? Good question.
Yes, this GPU prover is open source. You can find it, I believe, in Nethermind's socials, probably. It's separate from like the prover itself, but yeah, the GPU implementation has its own repo. And I don't know about Metal, to be honest. I wouldn't be the one to answer that question, I'm sorry.
So the last slide you had, it has the QR code. So
yeah, oh, sorry.
yeah, we cannot go back, but
okay, yeah, and last slide, and we can put it up later. Those QR codes can be followed, in any case, at Eric's co-op and at Nethermind F.
Yeah, and also after the talk, you will find the video on the Devcon passport, so you can find that.
Oh yeah, definitely. Yeah.
So next question. Comparing M31 and the Baby Bear, which is more GPU friendly and why?
So the M31 would be much faster just because it utilizes that 32-bit kind of space more efficiently, and in the improvements that you saw over just the Baby Bear, you get about 1.4x. And it's just because it comes down to a trick that you can use with the Mersenne prime specifically, the 2 to the power of 31 minus 1. I won't get into further details, but if you want to look it up online, there is an easy way to do modular arithmetics on it.
Okay, cool. Next question is how Eric's and Nethermind involved on CircleStack and STWO.
Okay, yeah. So Eric's and Nethermind work together in the STU GPU implementation. Nethermind worked with StarkNet, and Eric's worked with Nethermind to develop the STU provers GPU implementation, and the STU provers and the STU prover uses CircleStack. So that's how it's related.
Okay. So if we can just scroll down, or maybe I can check it on my phone. Yeah. Is anyone working on WebGI2 acceleration of ZK proof generation?
I honestly don't know. That's an interesting question. We can talk about that later.
Yeah, we can take this offline then.
I'm sorry.
Can GPU be used to speed up ZK rollups finality?
I believe it can. I mean, what StarkNet has achieved is impressive, so I believe most is possible.
I think it keeps going, yeah. Is it any better if we go to even more smaller fields, example 16 bits, so the ones you presented were like 32 bits? Or?
Yeah, so we still want to keep in mind the actual size of the computation. So in production, usually we use up to 2 to the power of 28 bits. And so we don't want to get anything lower than that. And also at the same time, we want to really unlock the 32 arithmetics, yeah.
And I think for the next question, you also talked about it, but how does GPU compares to FPGA? And also you talked about ASICs for CircleStacks maybe specifically? Or?
Yeah, at least there's no FPGA for CircleStarks. That might be an interesting avenue to really look into and research. But in theory, the FPGAs should have lower latency than GPUs, so it should perform marginally faster. But since we don't really have anything on that, we can't really say for sure.
So we have time for one more question. And
I can read it, I remember it. So the next question was regarding the Montgomery trick. We swept under the rug the fact that we assumed the elements we worked with were a power of 2. Well, this is because we can work with any number of elements and then just add elements until we reach the next power of 2. Do the optimized algorithm, the optimized adaptive trick in GPU, and then discard the rest of the elements. We know how many we added. It's easy. It doesn't matter. It's a trivial thing to adapt your array to be a power of 2, so it shouldn't really matter. I believe that's what we're really referring to.
All right. So that's it for the Q&A. If you have more questions, you can find Julian and Daniel offline. Please, some round of applause for them. Thank you very much.
Thank you very much.
So this was my last session, and then I'm going to hand it over to Andy, who's going to be your next MC. Enjoy Devcon.
Welcome, welcome. Afternoon, everyone. Glad you guys are here. Want to introduce myself. I'm Andy. I will be your MC this afternoon. I work and do product and PSE. But this afternoon, I'm going to join you here until the end of the day. I hope you enjoy this track. And we have fantastic speakers, so I'm very excited. Before we start, just want to find some place to sit for the ones who are standing. I also wanted to remind you guys that there's always a QR code here on the right, and that means that if you scan it, you can ask questions to the speaker. And that's great because at the end, we have 5 minutes to have questions, and I think those are one of the most enjoyable parts of each talk. So to get started with our first speaker, his name is Ricard Borrell. And he'll be talking about leveraging high-performance computing for efficient Starks, especially analyzing the computational aspects of Starks, especially on the prover side. And with that better reasoning, please give a big round of applause to Ricard. Welcome.
Okay. Hello, everyone. Thank you for being here. I am Ricard Borrell, as he said. Thank you for the presentation. I work at Polygon. Basically, I work on developing and optimizing ZK technology. And yeah, this presentation is about leveraging high-performance computing for efficient star provers. The presentation is divided in two parts. First, I will talk about the present in terms of product, which is the ZK EVM. And I will explain a little bit the lessons learned on the development of the ZK EVM. And then I will talk about the future, which is what we are working now, which is the ZK VM, so a general purpose proving system based on Starks as well. Okay, let's go for the ZK EVM. The ZK EVM was released 2 years ago, and its prover is based on a Stark method. And well, we have a Stark, and then we have aggregation so we have a recursion process to aggregate proofs. And then with a certain frequency, we will send the proofs to L1, okay? The only thing that we need to understand about a Stark for this talk is that it basically has 2 stages or 2 phases. In the first phase, we will compute the trace. And then in the second phase, we'll take the Frey polynomial, which is kind of a summary of all the trace in a single polynomial. And we will prove the proximity to a low-degree polynomial, right? The commit phase is done in different stages. This means that the trace is filled in different stages, and this is because we need randomness for some of the stages. We need some random numbers to evaluate some of the polynomials of the trace, and this randomness is obtained from the previous stages. So the roots of the polynomials evaluated in the previous stages are committed to the transcript or are added to the transcript, and then we get randomness for the next stage that we have to evaluate. Okay, in our arithmetization of the ZK EVM, we have 1,300 more or less polynomials, and then the number of rows of the trace, which is something that we can fix, it's a parameter of the prover, let's say, it's 2 to the 25. So it's about 32 million. This is quite a lot, and it ends up posing requirements of 800 gigabytes of memory. Okay, I will talk more about this. Okay, so why we use such a big number of rows on our trace? Basically because we have a monolithic approach on the arithmetization. This means that we have a static capacity, so our trace, the capacity of our trace is determined by the number of rows. And so we fix a big number because basically we want to be able to handle any transaction that comes to the network. Okay? That's why for the most heavy loaded transactions, the ones that will need more steps, we need to have enough space to handle them. Okay? This approach has advantages, but also some disadvantages. A clear one is that, okay, when we have to close a batch because we don't have more room for new transactions, because some of the state machines of the trace are filled, then there will be some spare cells on the trace that we have to prove, but they are not being filled with real values coming from the inputs. Okay, so we have some padding effects, but also has some advantages. For instance, that we have like a constant workload that we can optimize very well. We can allocate buffers on advance, etc. So it also has some advantages related to performance. Now let's talk about timings. A proof of this huge trace for the ZK AVM takes about 6 minutes, and the cost with the GCP instance that supports AVX 512, it's only $0.46. Normalize it by the number of transactions, Ethereum transactions that we can fit within a batch, it's about $0.2 million. This would be the overhead per transaction. Okay, so it's a very low overhead, which is negligible in terms of the grand scheme of things, in terms of the cost that adds to the transaction. Moreover, OKX has done a very interesting job that it has ported the prover to GPUs, and this has decreased the latency to about 3 minutes. Okay, so and even decreasing the cost. So this is a perfect situation where we decrease the latency at the cost by using GPUs. Those are numbers given by them, and at the end we end up having $0.1 million added on the cost of the transaction. Okay, so it's really good. The speed up obtained from the CPU to the GPU, it's only, if we consider the end-to-end proof from the beginning to the end, it's 2x. Here is one of the limitations of the prover. As we have such a huge trace, at the end we will be transferring a lot of data between the host and the device during the execution of the kernels. Okay, we will be limited by the PCI Express. However, still, if we look at the real cost, at the end what matters, they are very low. So it's not something that is very relevant in the current context. If we go a little bit deeper and look into the kernel's distribution when we do a proof, it's a perfect situation or a good situation because we have that 95% of the time of the proof, it's just concentrated in 4 kernels, especially in 2, which are the entity and the Merkleization, which take 70% of the time. And then we have expressions that are linear combination of polynomial, and then the executor, which is the first phase of the trace evaluation. So it's the part of the trace evaluation that depends on the inputs. Okay, this is the initial execution of the inputs. So basically, we have to focus on these 4 kernels, basically on 2, and that's what we did. A lot of work on this on the past, before releasing the ZK EVM. The first thing you have to consider when you want to optimize the code is to understand where are the boundaries for this code. And basically, you have to do a roofline analysis. Basically, the roofline analysis shows you where is the limit depending on the arithmetic intensity of your kernel. Okay? If your kernel does a lot of operations per each field element that you upload to the cache of the CPU, it means that it will be bounded by the CPU, by the computing part of the process. And if you have a lower arithmetic intensity, you are becoming bounded by the memory transfers from the main memory to the cache of the CPU. In our case, we are basically bounded by the memory transfers for all the kernels except the hash. And this makes sense because the hash does a lot of arithmetic operations per each field element involved in the hashing. Okay? So we focused a lot on optimizing the entity. We did a lot of, basically the focus here was to minimize the L3 misses. We got, well, at the end, the result is, the performance that we get is to perform the entity on 100 polynomials of size 2 to the 23 to 1.9 seconds. This is more or less the reference. And then the Merkleization, of course, is about in the CPU is another thing. In the CPU, it's about vectorization. So taking advantage of the vector registers to do, in each clock, to try to do 4, 8 operations at the same time. And we go to a performance with Goldilocks 1, not Goldilocks 2, of 1 million hashes per second. Okay? So this is the summary of what we did more or less 2 years ago before launching the ZKVM. At some point, we arrived to the conclusion that keeping improving the prover would not have any relevant impact on the performance of all the ZKVM because the prover was not a bottleneck at all. Okay? So we were very happy with the performance that we were delivering to the application. Okay, that's a good situation. We can focus on other stuff, and that's what we are doing now. The project in which we are involved is the CISC ZKVM, which is a general purpose ZKVM. Basically, as others that are in the space, we want to prove any program that is written in a high-level language like Rust, CPP, or others. Okay? The motivation of doing this project, it's very meaningful for us because we have acquired a lot of experience, a lot of tooling, a lot of knowledge on running the ZKVM, which has been in mainnet 2 years and has been, we have struggled a lot with performance, etc. So we can take advantage of all these things that we have learned to put them in the service of this new project, which is more general and can be more impactful in general for any user. Okay, it's open. You can check the GitHub. It's not it's not everything complete to do a proof, but it's almost there. So maybe in 1-2 weeks we will be able to prove any code that comes written in Rust. Okay, now the main difference with this new proving system, so the proving system that we are doing for ZISC, it's different in many ways, but the main difference comes from the arithmetization, because now we don't have anymore a static capacity for the trace. We will have a dynamic capacity. This means that we will shape the trace depending on the inputs, okay? And it will be divided into different 8 instances. All this will be explained in the next talk, so I cannot skip the responsibility of explaining this well, but of course I encourage you to stay to understand all the implications of this, okay? On the proving time, basically you will have to prove all the instances that you have generated on the arithmetization. We call them subproofs. So we have an array of subproofs to be proven, and then of course we will have an aggregation phase on which we will aggregate all the proofs resulting for all the instances that will result on a single proof. Okay? Let's think about the computational implications of all of this. In fact, on the CPU efficiency, out of the box, you don't get anything of this. You get worse CPU time. Why? Well, basically, the GPU, the cost of one proof is proportional to the area, and this stays true even when you go to small instances. Okay, so you have proportional cost. You have divided the main trace into different subtraces, but the area is more or less the sum of the areas is more or less the same. Of course, we have eliminated the padding effects. That this is helpful, and it will reduce a little bit the overall area, but it's not a big difference. And we have added the aggregation cost. So at the end, we are kind of making the proof a little bit more costly. However, with this new granularity, there are a bunch of opportunities. And the most important one is that we can take advantage of accelerators without having this limitation of being to move data back and forth from the host to the GPU, okay, with this PCI Express limitation. So this is one very important improvement here. We will be able to exploit GPUs much more efficiently. We have other ideas that vectorizing the execution of Starks. So we can kind of run 8 Starks at the same time with trying to do every operation in a vector register containing elements of different Starks, okay? These are some kind of ideas that we are considering, but the most appealing idea for us is going to distributed computing. Basically, the idea of distributed computing is that you want to run your proof using not one single instance on the cloud, but various instances, and with this try to stronger scaling your application. Okay? You want to reduce the latency, which is one of the main focus of this project. Okay, so let's talk about distributed prover. First of all, we are very happy, or we have a very important advantage on this project, is that we have access to a supercomputer, which is called Selenius. It's part of the CC Euro organization in Netherlands. Okay, it's part of the Euro HPC, but the division in Netherlands, let's say. And we were granted of resources there to do our proofs. We kind of submitted a research project where we want to find the limits of proving a Stark. We want to see where can we go, how far can we go on the reduction of the latency. Okay, this is our goal. There it's free lunch for us. We have hundreds of thousands of CPU cores that we can link together in a proof. We won't go to at this level, but hardware is there. And we have hundreds of GPUs as well that we could link to run a proof. Okay. Nonetheless, we want to target the high-end performance available, but all that we are doing can be running on the cloud as well. So we want to reproduce at a lower scale. We want to reproduce the results on the cloud, and this is very important because the production won't be done on a supercomputer. It will be done on a cloud system like the ones that we are using today. Okay. Let's talk about the first part, filling the trace. The witness computation is the part of filling the trace that comes from the inputs. How will we do this in a distributed environment? The most naive way to do this would be, okay, I have several processes. I talk about processes and threads here. Two processes don't share memory, so are processes distributed across the network, and then the process spawn threads, okay? So you can assign one process the master role and say, okay, you will compute the trace, and then distribute the result into equal parts, and then send to the others, okay? This is a functional approach, but it's not scalable at all. So we are not parallelizing anything. We have a lot of memory requirements in the master process, and we are also adding a high communication overhead. So it's not a serious approach. Now, let's try to get rid of the communication costs. Let's do the computation of the witness redundant in every process. Okay, that's fine. We have get rid of the communication costs, but we are not accelerating because it's redundant, and we have high memory requirements in all the processes because all of them have to store all the trace. So not still there. Okay. The next strategy that we have been developing is, okay, let's minimize the trace that we generate. So we have divided the trace generation in like kind of two stages. In the first stage, we only generate what we call the minimum trace, which is the information that you require to then, in a second stage, restart the evaluation of the trace at any point. Okay? So in a second stage, we can, in parallel, recompute the trace and divide this computation, okay? So we have this first stage of computing the minimum trace, which is very fast, and then we can, from the information generated in this process, we can distribute the trace between processes. I mean, each process will have run this first step of generating the minimum trace has been run by all the processes. Then all of them know which is the actual load that have to be distributed, and then all of them take one part and then compute this part, but only this part, okay? This will scale much better. Okay, let's look at the results. The test that I am using here and in the next slides, it's a program that executes 10,000 SHA-256 hash operations. The implementation that we are generating is not complete, okay? Because, well, as I said, this project is under development. At the actual moment, at that point, we're generating instances for the main and the binaries and some multiplicity tables. But it's enough to understand the results and the potential of this, okay? Now, if we consider as a reference the emulation time, which is executing the program without generating any trace, anything, even not the minimum trace, okay? The time is 0.6 seconds for this program. This means that we are going about 80 megahertz is our speed, okay? The overhead of generating the traces ranges with one instance, with one compute node. It's about 100%, so we are doubling this time. down to 37% on bin instances, in bin computing nodes. So we are going really down. The scalability is not very good, but because we are already very fast on the execution of the trace after, because we are dividing it into threads on a single node. But at the end, and really this overhead is not so, it's very acceptable, okay? Only 37%. Okay, I will go a little bit fast because I am running out of time. Then let's talk about the distributed, how we manage the distribution of the subproofs. So we have to solve the proof for all these instances that have been generated. Here we have, we just need to, so here we have a synchronization point because all these instances have a common, share the transcript, okay? This means that this object to get the randomness for the next stage is shared between all the instances. And this poses some synchronization between the execution of all these instances. Okay, what we do is a communication stage where we share the roots that we have to put to the transcript, and then we get the same randomness in each of the proofs. Let's see the results. Scalability of this phase, generating the subproofs, it's 100% efficiency, okay? We go from 70 seconds down to 3.3 seconds. Okay, it's a little bit suspicious that we have even superlinearity. So if you see the efficiency, which is the line, it goes over 100% at some points. So this is something that is not, let's say, a little bit suspicious. The problem here is that the distributed prover even runs better in a single node because you can fix better the granularity of the threads that you are using for the subproofs. Then if we compare the base point is the distributed prover itself on one single compute node as a reference, then we get something that is more meaningful, okay? We are getting a parallel efficiency of 80%. That's good. Let's go for the distribution. The distribution, the recursion will have some communication requirements when we generate the tree because the subproofs that we are aggregating can be hosted in different processes. We have to transfer to the process that will generate the aggregation. And if we look at the parallel efficiency, really, it's not so appealing, right? It's 44%. Okay, but here the problem that we have is that when we are going down to the tree, at some point we have less aggregations to do than processes. Okay, so there are some resources that are being not used at all. Okay, so if we just release these processes to do other things, the real parallel efficiency related to the hardware that we are consuming is 88%. So it's again a very acceptable parallel performance. Now, if we look at the complete overall situation for all the proof, including the witness computation, the subproofs and the aggregation, the parallel efficiency is 78%. We go from 125 seconds down to 12.2 seconds. The recursion is taking most of the time right now. It's 65% of the proof. So this is where we have to focus to optimize the performance, to even decrease more the latency. And the most important conclusion here is that as we have a good parallel efficiency, right, it's 70%, we can increase the latency by 10x, right? We have increased the latency of the proof by 10x, while the costs have only increased 27%. So this is a very good situation to have because basically it means that you can really decrease the latency without additional costs. So that's why and this can be reproduced in the cloud because we are not, we don't rely on a very high performance network because the transferring of data that we are doing is really minimal. We are transferring proofs or we're transferring roots, which is minimal information. So just I am closing with this. So we can reduce the latency at a very low cost increase. And as future improvements, we will focus on the recursion, on some algorithms like stir and multifry. Of course, here there is not the GPU in. So with the GPU, we can even accelerate more because our performance, now our architecture can support GPUs very well because the instances are smaller. We can even reduce more the performance with the GPUs and also run on the cloud infrastructure is our next step. Okay, sorry for extending a little bit and I can take any question.
Thank you, Ricord. Yeah, round of applause. So we'll have a few questions. Reminder that great for everyone who submitted. The QR code is always in the presentation, and you can also vote them. So we're gonna start, if it's all right for you, with the first one. Could you give an intuition of how do you generate a minimum trace that can then be used to restart the trace at any point? What's the data structure like?
Yeah, at the end, the minimum trace only is kind of evaluating the columns that you require to then be able to extend the trace. And this basically is 2 columns for the main state machine, which is the ones that load data from the memory. It's kind of the A and B registers. So it's only 2 columns. From that, the rest of columns that compose the main trace can be generated from this information at a given checkpoint, okay? So that's basically it. So it's evaluating just a subset of 2 columns.
Great. So the next one voted, can we say CISC VM basically trades more aggregation costs with better concurrency architecture?
So basically, yeah, that is one way to see it. Although the aggregation costs now are huge, and we have to pay for this aggregation, of course, to have this granularity that we are interested on. But we want to reduce as much as possible it by improving the algorithms. For instance, Plonky 2 has a very fast aggregation. We can do something similar. We have the STIR approach that reduces the number of queries that you have to verify on each aggregation step. So we have a package of things that we can do to improve this part. Also, we have to really think which is the granularity that it's more suited for our hardware. So it's not. Maybe we can generate less instances if we can really exploit the hardware well, and then the recursion will have less levels, okay? So a lot of investigation, it's coming on this part because, as you saw, it's the one that it's more relevant at this point, okay?
Great. The next one is, can CISC run programs written in lower level circuit languages? Will they be faster than Rust? Will the gap ever disappear? The top one.
Well, the purpose of this is not this. The purpose of this is basically generate the inputs with a high-level language. Okay, basically Rust, C++, or any other language. So this is mainly the design point of this. Of course, you may be able to generate some arithmetization or and then use the prover as a component that can be it can be self-contained, and you may be able to use it. But the main purpose is just you generate your code with a high-level language. You don't care about anything. You will get the proof of correctness of the execution of this program from the inputs. The inputs of the proof would be the inputs of the program, the outputs of the program, and the ELF of the compilation of the program with RISC-V or any other architectures that we are also considering, like WASM or LLVM. Or
Great. And I think we got a chance with one more, quick. Just trying to be futuristic. Can you give it insights on what could probably be done in order to improve the CK EVM or VM prover in 1 or 2 orders of magnitude?
For me, it's clear that we have to go, the distribution vector is a path or a vector of improvement that we have to take. Because if you rely on more specialized and complicated hardware on a single, but relying on a single instance, on a single node, we won't accelerate. But we can take advantage of the most sophisticated node available, the most sophisticated hardware available, and compose it, and take it 2, 3, 4, whatever number can fit with a good parallel efficiency. Because we want to control all the time the costs of the proof. If you have parallel efficiency, it means the cost doesn't grow. So that's the trade-off that we really have to take into account.
Amazing. Please give a big round of applause. Thanks so much.
Thank you.
You start with the next talk in 2 minutes.
Next.
Welcome, welcome. Great talk that we had before. And this next one is also connected, as it was told by Ricard. And the title of this talk is Backup, Leveraging Start for Tailor-Proof Generation. And just a brief reminder, it allows to achieve better cost efficiency by focusing on the active parts of the execution trace, rather than just the whole entire trace. So please give a big round of applause to welcome Felicia Barceló and Hector Masip Ardevon. Welcome.
Hello. Hello. Hello everyone. I'm Hector Masip, and he's.
I'm Felicia Barceló.
We are from Polygon Labs, and today we are pleased to explain a little bit a concept, or better said, I will say a set of concepts that we have been working on during these months, which we coined as VATCOPs, okay, which stands for Variable Degree Composite Proofs. And we'll see that this set of concepts will allow any prover, specifically an star prover, to prove any kind of computation in a way that he can tailor the computation as it wants. Okay, let's start anyways with the basics. Let's say that you are posed with the problem of proving a specific computation, okay? And you normally see a computation in two different views. One view is the evolution of this computation along the time. Okay, for example, let's say that your computation is composed of 4 variables. You study the evolution of the state of these variables along the time. Okay, and then you record these state evolutions. Okay, and this is what we normally refer to an execution trace. This will be very relevant in order to prove its correctness. And then on the other side, you have what we refer to as the transition function, which is basically a set of rules that this computation has to obey. For example, you can enforce that the computation on the variable A has to start at 1 and B has to start at 7. Okay? You can also pose restrictions on the very same state. For example, you can say that A plus B is equal to D along all the states. You can also say, for example, restrictions along continuous states. For example, that C has to be always equal to A of the previous state. Okay, and so on and so forth. Basically, linguistically speaking, is a set of rules that the developer think of in order to compute a computation. Okay, then we have the process of witness computation, which is basically trying to find a set of values that satisfy such rules. And finally, and because commutations can be described in very, very different manners, we have to find a way, a language, to describe it in a common way. Okay, and this is normally referred to as arithmetization. Basically, finding the correct set of constraints that describes the transition function of the computation. Okay, now, if we will go a little bit beyond of this basic problem, let's say that we are posed with the problem of trying to arithmetize a thing like an EVM. Okay, this is far from being something trivial because in the EVM you have a lot of components. You have a storage, you have a memory, you have arithmetic operations, you have memory operations, you have a lot of things. And you have to try to arithmetize them all. You have to find the right set of constraints. Okay, and the naive solution of this problem is, okay, let's try to do it. Okay, let's try to find a set of constraints that enforces not only arithmetic operations, but also memory operations, but also input data management, and so on and so forth. Okay, and then we soon realized that trying to do it as a whole is a very, very complex problem. Okay, arithmetizing all these things are far from being something trivial. Okay, so we needed to find something else. We needed to find a new tool in order to do that. And the tool, the thing that unlocked the arithmetic of the EVM was the concept of a bus, okay, which basically allows you to break down the arithmetization in different components. Okay, so it's very natural that if your computation or your component has arithmetic operations, you have a dedicated set of constraints only ensuring the correctness of the arithmetic operations. Okay, the same happens with the memory, with the storage, and so on and so forth. Okay, and then you have all the components individually being proven, and then you need something to prove the relationships between these components. Okay, and this is the bus. Okay, with the bus, you basically, if you are, for example, in the main component and you want to perform an arithmetic operation, you basically assume, and you are giving some inputs, you basically assume that you basically assume these inputs and you throw this data to the bus. Okay, with the expectation that at some point the correct component, if you have done so for sure, will take these inputs, it will compute the output, and will give you a proof that this computation has been done correctly. Okay, so from one side, you have components throwing things to the bus. This is what we normally refer to as assuming a computation. And from the other side, you have other components taking things from the bus. Okay, taking things from the bus and trying to prove them. This is what normally we refer to as proving something. To prove, assume versus prove. Okay, this is very abstract. So let's see an example. Let's see the different ways that we have come up in order to manage the bus or to throw things to the bus. For example, you can use the bus to try to prove a permutation between those two components. Because, for example, you want to ensure that the memory operations that you are doing in the main component are exactly the same as the ones that you are proving in the memory component. You can have lookups, for example, because you maybe are doing the same arithmetic operations many times, and you want to prove it. So you will find it many repetitions of this operation in one side, but you want only to prove it once. And there are a lot of more variety of ways to throw things to the bus. For example, you have range checks, you have connections, you have whatever you need, basically. Okay, but anyways, with this, we were able to divide the optimization in many components. But the animation was more or less easy, I would say. And then you basically generate a proof of all these things, not only of the components, but also of the correctness of the bus, let's say. Okay, and you generate this proof, and what you normally will expect is that you will have a lot of traces, all of them filled with meaningful values, and then you prove it, and then basically you're proving the state transition of the EVM, which is the original objective. But then after trying it with very different inputs coming from different kind of transactions, we realized that the reality was completely different. Okay? The reality was that we had some components that were totally meaningful, were totally filled of important values, but then there were other components that were not even filled. For example, because the size of the traces has to be the same, because we are generating a proof of a whole trace, the arithmetic component was not even used in the average. Okay? And for example, if you go to the extreme case that you are designing a specialized component for special cases of special operations, for example, when you want to prove the correctness of a pairing, then we realized that this component was totally unused. Okay, so we needed some way of fixing this problem. And the way to fix it was the introduction of bad cops. Okay, now things will be completely different. Okay, we will not be, again, trying to generate a proof of the whole thing at once. And now the idea is that you could adapt the arithmetization to the size that you would like to have. For example, if you expect that for your use case, you are not using the arithmetic too much, but you still need it, you could design an arithmetization that is lower in size. Okay, the same happens with other different components. And then the idea is, instead of generating a proof of everything, we generate a proof of all the components individually. And for sure, we also need that this proof takes into account the relationships between all these components, because the relationships are still there. Okay? So from one side, aggregation, from the other side, consistency. Okay, so let's go for an example. Let's say that we have the main component and the arithmetic component, different sizes, perfectly for our needs, and we want to prove the relationship between these two. Okay, so what we normally do is we compute what we call an auxiliary trace beyond the original trace, the main and the arithmetic. Okay, then when we do an assume, we accumulate this value, along this auxiliary trace, and the same holds for the arithmetic. Okay, and at the end we end up with a value that we normally refer to as an A-group value. And beyond proving the correctness of each component, we will need to prove that the resulting value is the same in both sides, okay, achieving the fact that they are related correctly. Okay, for example, if you are with the problem of proving a lookup, and you're using, for example, the lookup protocol, okay, what we do is we are going to be accumulating the fractional sum of all these of the both sides of the auxiliary trace, okay, and at the end, for sure, you will have constraints ensuring that this accumulation hub is done correctly, and this still will be proven in the, let's say, the basic proof, and then you will need to prove outside the individual ones that the two values that you end up with are basically the same, okay, achieving the lookup check. Okay, if we go a little bit on the details of this aggregation and these constraints and these proofs, okay, in the diagram you see what is normally a circuit for aggregating two independent proofs. Okay, so the logic of this circuit is basically a copy of the verifier logic, okay, and you give it its expected inputs, for example, public inputs, the aggregation type, the proof, and so on. And what you expect that the verification of these two circuits is successful, and then you generate a proof of this statement. Okay, this is a traditional independently proven aggregation circuit. Okay, but now we are going to enlarge this logic only to deal with the dependence that this proof have underneath. Okay, we are going to be giving it the ergo values, the accumulated ergo value until this point. Then the circuits, instead of just saying if the proof is valid or not, they will also generate their ergo values, their resulting sums. That doesn't matter if you look up permutation and so on, the resulting sums. And then the circuit itself is gonna aggregate these ergo values, and then it's gonna spit out as an output not only the proof but these ergo values. Okay, and then at the end of the aggregation, the last aggregation circuit will ensure that the sum or the aggregation function, doesn't matter if it's a sum or not, matches. Okay, as in the previous example.
Okay, one of the things that we need to solve is the scalability. Okay? I was explaining before, scalability can be, you can see this in two ways. One is the scalability I produce on different machines, specialized. That means that I can solve the problem with specific machines. Okay. But it's only one type of the scalability, okay? In this scalability, I can use the number of the different machines, but the problem is that I need to add something. This is the part of the horizontal scalability. The other is related to the vertical scalability. That means if we analyze the different type of the state machines that we have, there are the typical single machine, that means that only one instance, okay? For example, the ROM that has the correct instructions that can be executed. Another are the machines that are sliced independently, that have independencies, have no constraints between the different slides that can I do. I can divide this in horizontal. I can put this in any place, not have a problem because not have relations between these machines. I prove the different binary operations, okay? But each proof is independent of the other, okay? But there are another that have some relations between these. For example, the memory or the main, because the trace, one row depends of the previous row, okay? What can you do? We put some relation between the end of the end of one stage of one instance, one segment, to the other, okay? And we need to link this in a correct way. Okay? We use our bus. How make this, okay? We use the same concept that Hector explained before. when you start a segment, you assume an initial state that you put in the bus. And when you finish, you prove that assuming this initial state, you finish with this state, and you put this inside the bus. Okay? With this, you can add any instances, any segments of the main, of the memory that you want. Okay? The only is this relation. Okay? This have a thing that we need. Okay? We rely. This start with one state and finish with this. But we need to break this relation, because really the initial state of the program cannot be the final stage of the program. For these reasons, there are global constraints that defines this relation using the bus, but in a point of view of the global constraints. That means that you define with a global constraints what is the initial state, for example, what is the PC now, the boot address, or what is the values of the registers that you want. Okay? And after, you define how needs to be finished this program in correct way. Okay? And this put inside the bus. This is a very useful instrument, because there are another problem when you use cycle machines in a security problem, that you can repeat the cycle times. And you could, if I close this cycle, that means, but I can add 2 different cycles, and this is not a correct execution of the program. How you put this in the global constraint, you only have produced one time the cycle, because you don't have any things in the bus to start to allow to start a new cycle. Okay. As a summary, the continuations is something that assumes an initial state, okay, and proves the next. It's important that this continuations is different than the other continuations that use a big numbers, or use one for all the machines. This is individual for each machine. That means that I design a machine that have relationship between the rows. I don't have problem to cut. It only to be used these continuations. The initial and final state, I have full control about this. That means I can execute, for example, 2 mains with different programs, because I can put in the global constraints the beginning and the end of the different machines. I have fully control of this initial state and final. The other thing is we have an idea to produce an air value. What is air value? When we think in the trace, we think in the rows, okay? But when we think in the state of the instance, really don't have dimensions of rows, because not change is the state at initial or the state at the end. No need to fill a row with these values, because we not spend a lot for put this. And this means that we need the air values. The air values is something that is common, is inside each instance. For example, what is the beginning PC, or what is the MPC, what is the segment ID, something like that, okay? And it's very cheaper, because notice something that applies to all the rows, okay? How these constraints, really these air values, you have a relation to directly the specific row of the constraint. For example, I say the PC must be matched this air value related to the beginning PC, the first value that is in the trace of the PC. That this is the relation how fix the values, or how constrain the values that have these air values, okay? This gives to us a tool to define a trace that as we want, not the limitations. When we can put and put the different things to the bus using the same performance bus, not using anything. It's a light way to do these continuations, okay? And the same way that we use in the main, you can use for the memory, okay? And you don't pay any cost for the other machines for the continuation, because you don't need, okay? for me, it's
Yeah, well, as you have seen, there were many concepts that we tried to fit in within a 20-minute presentation. We are using all of these to build this. You can check out the repository and see that all of this is not only theory, but it has been implemented in practice. You check it and try to understand it. And well, epic phrase at the end. Yeah, thank you very much.
Thank you so much, both, for the great presentation. So, reminder to the public that if you scan this code, you can visit the session in Meerkat, and that allows you to ask questions, vote for questions, and also collect an NFT about the session. So, yes, I think right now we only have one vote, so let's start with that one. If you were a time traveler, would you prefer better architecture for EVM to make it more CK friendly? And yeah, maybe you can expand that and be precise. What, if so?
Yeah. I mean, if you see the history, the people that designed the EVM at the beginning reject, or at least they didn't expect the world to be that GK friendly at the future. And I'm sure that they will have designed some things differently at the moment that they design the EVM. They will know the impact of these things and the use cases of GK in general. Okay, just keep in mind that when Ethereum came out, there were not even papers that make Snark or GK in general provable and, let's say, practical. Okay, so yes, for sure I will make it more GK friendly, but I will say that no one else at that time was able to predict that impact of GK in general.
One thing is important to say that all these things that we have a lot of improvement, that we break in some frontiers that we have. Related, we make the ZKVM, and we found and we learned, we have a lesson learned about this. It's important because we see what we need for make more big things.
That's the luxury of hindsight, right? The next one, thank you for the one who asked, what are the implications of Beam Chain ETH 3.0 that was discussed yesterday? I don't know if you saw it or heard it, as it relates to CK.
Yeah, so I mean, related to our talk, it's clear that at least we are using all that we have described to build a ZKVM, and it was clear from Justin talk that ZKVMs will be used in many places in Ethereum 3.0, in particular in the consensus part. So, I mean, I will not say implications of the Beam chain to GK, but the other way around, the implications of the evolution of GK to the Beam chain itself.
Great. Please, round of applause. Thanks so much. And with that, I wanted to remind we're going to take a break, for 1 hour break. So if you are into applied cryptography, please come back at 3 p.m. We'll be here. We're going to have a great set of panels and talks. So yeah, have some good lunch, food, and hope you enjoyed it. Thanks. Afternoon. Welcome everyone back. Hope you had good lunch. Hope you have a good break. So just for this new block, just introducing myself again, I am Andy. I work at product at PSE. I'll be your master of ceremony for this part until 6:30. So if you like applied cryptography, stay here. We're gonna have tons of great stuff. So just to remind quick things, remember that when a speaker is talking, there's always gonna be a QR code on the left, and that's where you can submit your questions, and you can also claim an NFT that you have attended this talk. So I recommend that you go in, submit your questions, also like questions or vote if you want one question to really be asked to the speaker, because those are the questions that are probably gonna be prioritized. So for this next session, we have Don Beaver with an amazing, great title, which is called the Supreme Ruler of the World, where we're gonna go into basic math, we'll see, to understand better more about sum check and sum calc. So please join me in giving a round of applause and welcome Don Beaver.
Thank you so much. Thank you so much for that nice introduction. I did actually go all out to try to make this the best title ever, or if not, it's at least a tribute. What I want to talk about today, just to give a level set, is zero knowledge, of course, this applied cryptography track. It's intended and directed at people who have a little bit of knowledge about cryptography, a little bit of knowledge about zero knowledge, but are basically mostly developers interested in finding out why bother doing this and what is actually going on behind the scenes. So without further ado, I'm going to talk a little bit, not too much metaphysical or mystical, but more about how do you get calculations done by powerful entities, and how do you trust that those results are actually true when they hand something to you. This is really the realm of zero knowledge. It's actually a bit broader, zero knowledge and verifiable knowledge. There's a lot of different properties that are important. They're really important to scaling things up on the blockchain, any kind of blockchain in general, and I'm sure many of you will have seen a lot of buzz around these topics as well. So what's the buzz about? How does this actually work? What is going on behind the scenes at some reasonable level? In general, I'll do a quick background. So zero-knowledge proofs or interactive proofs are ways for a computationally limited verifier, a client, to actually ask for the truth or falsity, ask for a claim to be made, and for somebody to, with a lot of power, to give them a proof that that claim is true. So, for example, some of these problems might be complicated, like, hey, I know a Sudoku solution. And, you know, a 9 by 9 is not a big deal, but n by n is actually an NP-complete problem to solve. So these are actually intensely complex problems that people work on and try to demonstrate the truth of. More practically, you might be looking at, you know, consensus algorithms and saying, hey, look, I can tell you that I checked 400,000 signatures and they all checked out. You don't need to bother. So trust me. Well, in this setting, we don't really want to just trust people. We want to actually verify what's going on. Okay? So that's the setting. The scalability argument here is that one person is going to do the work, and everybody else can just sort of check after that one person did the work. Okay, so for example, what did the consensus say? I checked a bunch of signatures, did they all pan out? What's the new state maybe on my own chain or on somebody else's chain? That's a lot of work to do. If you try to do that work inside of a contract, it's going to be very expensive. If somebody can do that work for you outside of a contract and just prove it to you in a contract, that helps you scale, because it's a much cheaper thing to check than it is to calculate. And so in general, these things help us scale with things like roll-ups, with other chains, with exchanges, and so forth. Anytime you have a big calculation that you want to land just the result of on another chain, we'll use these kind of results. So, all right. There are two kind of very closely connected problems here. In order to motivate it, I mean, really, we're going to talk about proving a calculation here, which is the middle one. We'll look at a couple tools. One is called SumCheck. It's actually kind of a very old play on words. When you're sending a message from A to B, you do a checksum to make sure it wasn't actually munged in the middle. SumCheck is a way of getting a calculation from A to B and making sure the calculation wasn't messed up, that the result that you get is really true. Related to this is something I'm calling SumCalc, which is how do you delegate a problem to somebody else and get them to calculate it for you. You're a contract on chain, you ask somebody off chain to do the calculation. So very related math behind it. And we'll go into a little bit of the math and see what helps us scale these different algorithms. Okay, so what's really happening here, what is the supreme ruler? I'll get to it more in a second. It is basically a trick that helps us look at very, very large calculations, essentially exponential size calculations, and use like a moderate amount of checking to see that whether they're true or false. All right, you can scale this down a little bit. You can say maybe I have a human scale n-step calculation, and I have a very, very tiny verifier that only uses logarithmically many steps. I won't get too far into the weeds about the complexity of the theory, but really, if you want to think about it concretely, you got a million-step calculation somewhere, and it takes you maybe 20 sort of questions of this prover to actually make sure that the prover is behaving and the claim is actually a true claim. All right, so that's where we're going to go. We're trying to get to this industrial applications of ZK so we can scale up things on blockchains. All right, so brief interlude from our sponsor. This talk is brought to you by the number 2. Okay, so the number 2 is going to appear a lot of different times today. Let me just give a quick outline of many different things that we'll see sort of a duality in. We'll look at a ruler. We'll see where does that ruler become a supreme ruler. We'll look at checking and delegating, and they're very related, and the tools that work in one will work in the other. We'll look at small scale and big scale. Look at slow computing, like on-chain, swift computing, off-chain. What I just said, gas-powered computing versus CPU computing. The aim of this talk, just to level set, is to, in the days of like, hey, what was HTTPS? I want to know what TLS is. Should I use it? What's it going to do to my performance, et cetera? What's all the buzz about? That's the level here. I'm not diving too far into the crypto. I hope the cryptography. Keep me honest if I do. This is a talk about, hey, if you're a ZK-VK verifiable knowledge adopter, what's a little bit of the math that goes behind it? What is kind of the RSA flavor of that? Is it not a talk about how to become a ZK EVM developer, for example? It's how to use these tools and what actually gets us to the scaling. We're going to try really hard to stick to non-mood math. I'm going to talk a little bit about how you start with lines and turn them into something that is a multilinear. This is the real essence of the math behind most of this, and I'll do some geometry for that. And take us from an ancient kind of Jurassic age of checking things into what the modern age of really practically checking things is and how that looks. So, all right, Jurassic, as I said, a long time ago, 35 years ago. Let's start, okay, with sort of an everyday ruler. Now, I'm also a dad in addition to being a researcher, so we're not talking about rulers that command the universe, although the origin of this word is pretty much the same. Rulers are things that help us do things like command more of the world. So if you have a couple of points from second grade, you learn how to actually like draw a line between them. Okay, so you draw a line out. Sorry for people in the back if you can't see that, but you can actually extrapolate and get new points from it. So normal ruler does things like that. What else does a ruler do? The second thing, ruler aligns things. Okay, it's really important, you know, if you want to make sure that everybody is in line or that all your data is in line, that you have a straight edge to actually line things up. So this is a tool that helps you detect if something is out of line. This is actually the basic mathematical idea behind most of or a lot of the verifiable knowledge protocols, is actually just looking at lines and seeing whether things that are claimed actually line up. So I'll get into more of this in a minute. That's just kind of the geometric backing for all of this, for what's going on. Okay, so we start with kind of a basic ruler, and we're going to get to something that is in larger dimensions, kind of this sort of hypercube-ish looking thing that is I'm calling a supreme ruler. It is a larger scale version of a ruler. Okay, so let's rewind a little just to set the scene, to remember kind of high school math a little bit here. If you start with a table and you want to turn it into a line, make a linear extension of entries in a table, here's where we go with it. Okay, this is just to refresh memory. Okay, you have some inputs, maybe a 1-bit input. It's either 0 or it's 1. You want to draw a line through it, the geometry that we just saw a moment ago. Okay, so here's what you do. You draw the line. Okay, it's nice if you have a calculator to do it. But the technical part of this, and we won't go too much deeper than this, is that the nice trick to doing this, it's a little bit of high school math as well, is we can use two really nice helper functions. Is x equal to 0? The is x equal to 0 function is just 1 minus x on 1-bit inputs. Okay, I'll let that sit there for a second. 1 minus x tells you yes or no, is x 0. And likewise, you know, this is hopefully relatively simple high school math at this point. Is x equal to 1? Is this equal to 1 function? Okay, we're going to use these, okay, in building up what the extension is. And there's a reason I'm going through the basics. We'll grow it out in just a second. If you say, this is basically a short program here to say, hey, if x is 0, output 3. If x is 1, output 7. Okay, so these are kind of one-hot functions. They're only going to be non-zero in certain cases. And so this is how you interpolate a line. Pretty straightforward. Okay, add them up, you get a linear equation. And that's really what we just saw. So that's the algebra side of it. Okay, so this part, hopefully, is straightforward. I'm going to jump into cryptographic motivations for this, kind of related problems that are related to zero knowledge. Zero knowledge is a claim that you want to prove. There are also things like delegation, which is I start with some input here, 0, 1, 1, 0, and I want to ask the cloud to actually help me calculate some function of that. Okay, so, all right, the key thing here is that the cloud is not supposed to learn what you're trying to compute. It might be your tax return, it might be private inference, that sort of thing. So it's a very related to zero knowledge problem. It has the same mathematical solutions to it, but it turns out to be a little bit easier to address and to find where these tools work. Okay, so you send a message, it's a little garbled, you get a message back from the cloud, and from that you're able to kind of figure out what you were really interested in the first place. Okay, here's a sort of silly way of doing it for like a line. If your function was like a line, not very complicated function to compute, but you could say, hey, server, tell me, you know, what was f of 5 up here? Hey, server, tell me what is like f of 4. And then you'd go home and you say thank you, and you draw a line, and then the server would have no idea what you were really interested in. Were you interested in computing f of 0? Were you interested in computing f of 1? But the point here is that you can actually do it. Okay, so that's a trick with one server. Now, to some degree, it's sort of like, why bother doing this? It's a lot of work for nothing at all. You might as well just done this at home in the first place. But we're going to grow this, and it turns out that if you grow it in a certain way using this multi-dimensional ruler, you actually can delegate the query to a server privately. And likewise, the same tool works for ZK as well. Okay, so the shape of what we're going to do is we're going to look at things that are like, hey, points on a line, and you know, if you start with setting 2 of these points on the line, you will determine the values of all the other points on the line. Okay, We'll expand to higher dimensions, set 4 points on a Boolean value square here, 0, 1, 0, et cetera, 0, 0, 1, 1, et cetera. Grow that from there, and we'll go to larger dimensions. And it turns out that at larger dimensions, we actually get some payoff in this. And that's where the compression comes in. That's where scaling comes in. The cost of going to large dimensions, actually, there's a trade-off that works really nicely there. Okay. So I said a little bit about going back in time. Let me try to set the motivation here a little bit to generalize from like the one server case to a multiple server case. Okay, there was some nice work in the 80s done on this that said for one server you could actually do calculations like this, but they were kind of very limited calculations. It got generalized a little bit later on to saying, what could you do if I have a tax return and I want to ask, Amazon and Microsoft and Google to help me with it, but I don't want to reveal the tax return. So you get answers back from each of them, and then you're like, okay, I know what the result of my tax return is. I owe $5 or whatever in this case. Okay, so geometrically, we take the case that was like before, except now we have different servers giving us answers. So in just a linear case, we might go, hey, Alexa, tell me what is f of 4. Hey, Siri, tell me what is f of 5. And now, having gotten those answers back to maybe some very complicated calculations, we can extrapolate ourselves to the places that we're really interested in, which might be something like if we were trying to find f of 1. Okay, so you're asking for something on a line, and you're getting answers back for this calculation, and then you're able to figure out what it is you wanted to calculate. Okay, so it's all drawing a line, like I said. I will take a very brief detour here. This is not that important, but it actually is part of the trick. If you want to look at this later, that's fine, but there's a lot of polynomials going into this, so I don't really want to spend too much time on this. But if you secretly share, you can actually go, for those of you who know multi-party computation and secret sharing, you can actually scale this up to many, many other parties. And then you're not just interpolating a line, you're interpolating something that is of degree n to get your answer out. Okay, but that's as much as I want to say on that, because that's like maybe a little too much into the weeds on polynomials. Okay, here's the core trick. This is what happens and gets scaled up in zero knowledge. It happens in delegation. You actually go out and ask for these cloud servers to calculate a sum of a huge number of things, 2 to the n things. Now, the cloud is fine to do that for some moderate n. You, as the client, are not bothering to do all that work. You'll get some answers back after all that work is done in the cloud, and locally, you don't really have to do very much. Locally, as the weak client, you're really just doing some kind of like drawing lines, interpolating a small polynomial over here. Size n kind of calculation. The servers, the clouds, these guys are doing 2 to the n calculations. So there's a big scale difference here. You're getting a lot of work from provers, a lot of work from delegates. The flavor of this, the compression that happens in all of this, that powers all of this, is that the weak person, the one who has just gas on a chain, is doing a map reduce of size n, adding up n things, compared to work that's being done off-chain or by complicated servers that's on the order of 2 to the n. So here, let's, the kind of cool thing here is that you can delegate really complicated answers. And using this supreme ruler in a sense. Okay, so I will skip through a little bit of the history in the interest of time. This stuff got discovered back, well, I missed a punchline here. This stuff got discovered back in 1989, most of this, and it's now being implemented on chains. Other kind of important things happened there, and it's kind of relevant, is that this was the kind of the era of swift computing, if you like. This is where we could speed things up by an exponential factor. Sorry about that. Said dad jokes here. We are here now doing things like sum check. You'll see things like, hey, I can do exponential calculation off-chain and get things checked in normal linear time on-chain. That's really what's going on here. There's a kind of a very strong relationship between the delegation and the cube. Okay, I won't go into the details of this. This is a little bit. It starts to look like category of endofunctors kind of explanation of the math that's in here. Instead, I said no moon math. Trying to be honest about that. back in the day, this was the interesting thing about this theoretical development, that you could take hypercubes and then squash them into like linear calculations. I'll say how in just 1 second, but it kind of missed the mark. You know, nobody wanted to do the moon math in 1989. The New York Times said, wow, there's a lot of research going on here. You know, what's interesting? Well, we're not going to publish the moon math in the New York Times. We'll just say what's interesting about it. So the reason I'm talking about this here is that, well, in 2024, it's kind of the same thing. You don't need to know all the moon math necessarily, but there's a lot of hype around ZK. And it's kind of nice to get, and what I want to do in the next couple of minutes is just to go into the details of that. You know, with that, if you, the really fascinating thing that is not completely moon math is that, hey, with only 20 questions, you can pin down a calculation of 1,000,000 steps. Okay, that's the magic. Okay, so I'll try to do the magic quickly. It looks a lot like the beginning where we had the high school math. We'll go from 1-bit inputs to 2-bit inputs, just to start. And so here's some random, you know, table that you might want to compute. This is maybe a machine learning algorithm output or something like that. Okay, well, we do the same thing. It's a program. It's a program that is a switch case statement. If xy is 0, 0, output 5. If xy is 0, 1, output 9, et cetera, et cetera. The interesting thing here is that, well, what do these equality checkers look like? Well, if you want to check if x is 0 and y is 0, you use this function, which is 1 minus x times 1 minus y. Okay, that's the one hot function that is only going to appear in my lookup once under this condition. And when you look at this, this is a term that has this is a function that has 4 terms in it. It's kind of exponential already. It's got 4 monomials, but it is linear in x. There's no like x squared or anything like that. It's linear in y. There's no y squared or anything like that. The largest degree that you see here is 2, kind of the xy that's in there. So it's very low degree. All right. Generalize this. You can do this at home. It's, you know, you get a interpolated result here. If you look at the wall of LaTeX, you know, this actually expresses what really the bottom line is that when you try to do this interpolation, you get 2 to the n monomials. So you can actually express something that's really, really complicated. But the maximum degree in this is only a degree n. So it actually turns out to be easy for verifiers to check because of that low degreenness. You're only just kind of looking at that low degree polynomials. You're only looking at lines. But the servers or the provers are doing intensely busy calculations in this. Okay, so picture, hopefully worth a few thousand words. Starting with 2 values, we looked at 2 points on a line, and these 2 points actually really constrained all of the other values on the line. And it means if you do one of these shell games, let me pick a few of these points on the line and see if they are consistent, you only need to ask for 1 or 2 probes on this. Step the dimension up a little bit, and you've got 4 values. Okay, for 2-bit input, 2-bit x and y. How many probes do I need here? I need kind of maybe 2 or 3 probes. Okay. This is where the scaling actually happens. It's that when you try to encode a function with 8 values using this multilinear trick here, I don't need to do 8 probes. I don't need to do the whole thing. I need to do just maybe 2, 3, or 4 probes to actually get this to work. Okay, that's kind of where the math comes together. It's what happens in the zero knowledge. It's what happens in the delegation and so forth. Okay, and in general, you know, sorry for the universe. I have to apologize that we can't draw, you know, 2 to the n values up here, but when you're trying to scale this up, you get a huge blow up in the power of the checking. And to be concrete again, if you have like 2 to the 20th values, you now only need to ask sort of 20-ish questions. It's a real explosion in scale. So that's the flavor of like the basic trick that happens in a lot of zero knowledge. So that when you're actually asking asking to verify something on chain, this is why you can get away with something that's very, very small. Okay. So let me just finish with this last slide or two. ZK VMs, what are they doing? In general, a typical pattern is you run a program for 1,000,000 steps. You write all the values of the trace of that program on a hypercube. That's 20-dimensional hypercube. You can do this. This is it's a computer, easy for a computer to do. You've got your million entry table that says all of the steps of the calculation. And so the flavor of this is to then build a proof around that. And because of this like dimension relationship here, you only need to ask like 20 questions instead of asking, you know, a million, instead of inspecting everything everywhere. So that's really the magic of it. Okay, so if you really want to do ZK VMs, there's a lot more, you know, of Moon math here that I'm skipping completely. If you feel nerd sniped, feel free to go look at it. We're not getting into any of that. The reason why these things are hard is that there's more stuff to it than just that trick. But this trick is the core of why the compression works, of why compressing a million steps down to a 20-step probe is feasible at all. Okay, so that's it. Quick summary is history. You can look at this later if you want, but the real interesting things here is that we started the era of kind of swift sound computing 35 years ago, if you like. We move forward now, and we're finally going from an era that was purely theoretical to an era where it's all applied. And we're now industrializing this. We're building programs that can take a million-step calculation and check to make sure that actually is valid. Okay? Picture, million is what you get for the cost of 20, and that's it. Thank you guys so much.
Thank you, Don Beaver. Indeed, a great presentation with that jokes included, and hypercubes and multilinear and multidimension. So remember that we have this QR code where you can input your questions, and the questions that were more voted are more likely to be answered. So to start with the first one, is there any value to asking more than 20 questions? Is it a higher level of security or certainty?
Yeah, no, this is a perfect question. I wish I had planted it. There's a really subtle nuance in this. The 20 relates to the dimensionality. And it is not that asking one question or two questions is worse or asking 40 is better. If you think about a line, to determine a line, you need two questions. Asking 4 questions on a line isn't helping a lot. So really what you want to do here is to ask the 20 questions for a 20-dimensional thing, and then maybe take another shot at it. You might have a chance of cheating the first time with 20 questions. Next, we'll do another 20 questions, and we'll set the whole thing up again. So the going from 1 to 20, you really need to get to at least the 20 to start off with. Yeah.
Great question.
Great question. Yeah, thank you.
Awesome. All right. Any other ones you can input? If not, please join me. Thanks so much. And yeah, big round of applause. Amazing, great. Thanks for the short break. Hope you're rested. We have the next speaker, Alexander Belling. He's going to talk to us about Wizard, which is a new framework in order to build newer proven systems, CK proven systems, and it's been used in Linea. And it says like we can build our own PIOP in less than 15 minutes. So we'll see if we are able to see and do that in this talk. So welcome, Alexander. Some applause, please.
So hello, everybody. So today I'm going to present to you the tech we developed to develop the proof system of Linea. So Linea actually uses many different proof systems for many different use cases. It is a complex system. What I'm going to present to you is the main one that we use for proving the execution, so concretely proving EVM execution. So I should present myself. I'm Alexandre. I've been working in this space for 7 years now and been focused on cryptography for 5 years now. I've been working on Linea since the beginning, and doing research on Rollup even before that. So yeah, just to talk a little bit about myself. Okay, so I'd like to involve the audience a little bit. Who knows what ZK EVM is? All right, so that's a good half, a good third. So a ZK EVM layer is a layer 2 solution, whose purpose is to help Ethereum scalability. So the idea is instead of sending transactions on the Ethereum mainnet, you send them to a third party, Linea. Linea runs an Ethereum virtual machine, will process the transaction. It will be processed separately from the mainnet. So the contracts that are deployed on mainnet are not necessarily the same as the ones that are deployed on Linea. The states are separated. But but we can bridge between the two. I'm not going to describe much more how we bridge between Ethereum and Linear. But what is important to remember here is that we basically bundle the execution of many transactions and submit one proof at the end. We give you one number. Every finalization finalizes on average 65,000 transactions at once. And since we are using snark proof systems, meaning they have a very short verifier time, which is mostly independent from how many transactions are executed, that's how we get scalability. Verifying the final proof, which is a Plonk proof, takes a few milliseconds, but it's for 65,000 transactions. So that's why it's much cheaper, and that's how ZK VMs can achieve a much lower gas price. All right. So maybe a few words on ZKP and snarks. ZKPs, I mean, usually we say ZKP, but most of the time what we use in production are ZK argument of knowledge. And in order for a protocol to be a ZK argument of knowledge, it needs three properties. You need zero knowledge. Zero knowledge means that the proof does not reveal more than what it should reveal. You need to have completeness, meaning that if you want to prove something that is true, you should always be capable of generating the proof. Meaning, for instance, if you want to know that you prove the square root of some number, it should work for every number and not just your favorite, just one number. And the most important one is knowledge soundness, or essentially computational knowledge soundness. It is how you say that you know, that you prove that you know what you're proving you know. And so, as I mentioned earlier, we are building a ZK VM, but really the ZK is it's not about zero knowledge or hiding things. It's really about proving that we know valid execution traces. We'll explain more on that later. But especially, we need more properties. We want the verification to be succinct, to be small, and we want also the protocol to be non-interactive. It should be a single proof, a single message, and from that, we should be capable of verifying a proof. Okay, so let's apply all that to the EVM. The Ethereum virtual machine is a state machine on which we can execute code, and a transaction in the VM is like an instruction from the user of that virtual machine. It has a lot, it is specialized for running smart contracts. It has a lot of features and a lot that interact in a complex way between each other. And not every computation that are easy to do on the EVM are necessarily easy to prove. So for instance, I'm thinking about the Ketchak hash function that every smart contract uses all the time, like it's free. It's really not free to prove. And so if we want to solve that problem, so of course we need to deal with the inherent complexity of the EVM, but we also need a proof system that is flexible enough to solve all the problems that we need to solve to execute the EVM. So concretely, in order to prove the EVM, we have traces of execution that are instantiated by polynomials. We call them colon in our framework. And it could be summed up as a collection of errors that communicate with each other by sub-argument. And there are many different sub-arguments that are possible to use. We can have lookups. We can have projection queries. We also support variants of lookups that we call conditional lookup or fractional lookups. And so in order to make this work, we need a proof system that is really flexible and can deal with all the polymorphism that is inherent to proving linear arithmetization. Okay, so in order to do that, we designed the wizard framework, which is the main gateway between describing the constraints to represent the EVM and actually proving things. It has a very neat particularity is that in the wizard framework, you write protocols in an ideal model, and you don't have to worry about how you're going to commit to things or which argument you're going to use. You just say what you want, and then you have a list of techniques like a menu, which you apply to that protocol statement, and it will create for you a proof system as complicated as you need it to be. And so that's perfect for us. It turns out that this is how in academia they describe complex protocol. Like if you take, for example, the Gross 16 proof system, if you had a look at the paper before, you would see that they say, okay, so this is the constraint system at the beginning, then we do something that is called QAP, and then we do something that is called NILP, and then it continues, and at the end you have a concrete proof system, which is a Gross 16 proof system, but that does not translate into the implementation. People just take the final protocol at the end that you apply after every step of compilation of Gross 16, and there is a Gross 16 implementation. So what we do is that we actually implement every possible step, so that those steps can be reused for other proof systems, and we don't have to really mentally work out the whole protocol. In the case of Linear, it would just be impossible. And on top of that, we made it in such a way that if anybody wants to add their own compilers or do their own tweak or add their own type of constraints, the framework will allow that without changing the core of it. All right, so as I mentioned earlier, the proof system, the protocol that you are going to construct, you have to describe it in an ideal model. And this ideal model involves what we call the wizard oracle. The wizard oracle is, from the point of view of the protocol designer, a trusted third party. It knows everything, it remembers everything, it does computation for free, it is always honest. It's like something you really, if it existed in reality, we would not need cryptography. So that does not mean that what we build will not be secure. It just means that the oracle will concretely be instantiated by something else in the future as we compile the protocol. So the protocol can also be described in a multi-round fashion. I mentioned at the beginning that we need non-interactivity, but the protocol sorts this out using the Fiat-Shamir trick. It puts some limitation. It means that the verifier can only send random challenges to the prover, but that's a common limitation that every protocol have nowadays. It's very uncommon to be in a contrary situation. And so essentially, the prover can use the oracle by sending large message to it, and the oracle will just remember and notify the verifier that, hey, the prover did this part of the work. You can ask questions. So the verifier can ask questions, and the oracle responds to the question without needing to do any computation. It's like a godlike entity, and it is always honest. So you don't have to worry about him lying. So as I mentioned, the prover, the verifier, and the oracle can send messages to each other. And here comes the first primitive of the framework, which is what we call colons. So colons can be of any sort. We have what we call committed colon. Committed colon means it is sent to the oracle. And basically being sent to the oracle means that the prover cannot change its mind about what was sent to the oracle. You can only send something once to the oracle, otherwise you're cheating. And the protocol will always ensure that. But on top of that, we have what we call pre-computed colons. So pre-computed colons they can be of two types. They can be sent to the verifier or sent to the oracle, and they are known beforehand. So that's something that is part of the protocol description, actually. They always have the same values. You can think, for instance, the Planck circuit description, which is instantiated by several polynomials. We are going to see how we can implement Planck in 10 minutes. So I'm just putting myself forward a little bit. You need those colons to, as part of the proving keys, and they describe the Planck circuits. And on top of that, you can send proofs, and proofs means a message that is sent directly to the verifier. And there are other types. Actually, we have 8 types of different variants of colons type. So colons also have a predefined size. It can be 1. It has be a power of 2. It's due to a limitation, a current limitation in the framework. And they have a round assignment. And the round number is essentially describing at which round of interaction the colon is instantiated by the prover. So that's for the main part. And then, as I said, so for some colons that are sent to the oracle, or for some groups of colons that are sent to the oracle, the verifier can ask questions about these colons to the oracle. So that's what we call queries. It's the common term used in academia. If you know about Fries, they do random position opening queries, so that's what they mean when they mean query. In polynomial IOP protocols, there would be univariate openings. So in our framework, query stands for, at the same time, constraints. So there would be questions that have a yes or no answer, like, is this value the square of this other value? The answer can always be yes or no. Most of the time, it is thought of as a constraint. And here we describe it as a query. And so we also have open questions that are like polynomial opening, position opening. And so these have expect a response from the oracle that is other than yes or no. So we support many different types of query. It can be lookups, it can be univariate evaluation, it can be inner product between several colons. So essentially, most of the folklore is there. And we implemented it because we needed it for the concrete implementation of Vortex and linear arithmetization. All right. So as I said, once you have a protocol description, the only thing you need to do is to describe how you want to go from this description in an ideal world with ideal oracle into a concrete protocol that is secure in the standard model. So here is the base description that allows us to go from wizard IOP to polynomial IOP at the end. But in practice, this would not be sufficient. We would also need a polynomial commitment to turn this into a concrete protocol. So in this part of the code does not describe how we do the polynomial commitment, but how we go up to this point. Okay, so now let's get onto a practical example. So here is the Plonk constraints description. So we have a set of colons. Q's are describing a Plonk circuit. XA, XB, XC are describing the witness. And also, usually we add another colon on the right that is for the public inputs, and that we are going to use. On top of that, Plonk has some copy constraints, which can be instantiated by a permutation argument, which I'm going to show you how to do. Okay, so let's implement Plonk. So as I mentioned, we need to define our protocol, then we can compile it, and after we can run it, so running the prover and verifying it. We can also automatically recurse it, but we are not going to cover that today. All right. Okay, so first of all, defining the protocol. This is done by specifying a function, so the whole framework is in Go. Most of the prover stack of Linea is using GNAR, and the Linea's prover is also implemented in Go, as it is also relying on GNAR's implementation. So the define function has this simple signature, and the builder is an object that is going to store everything we said to declare an entity in the protocol, so either queries, colons, or so on. And we can also specify checks to be done by the verifier, so let's go into there. Okay, so here are the colons description. So you can recognize the Plonk colon that we saw at the beginning. So the Q's colon are for the circuit description. They should be the same no matter what we try to prove, so they go into pre-computed. The XXBXC are commitment. They have to be sent to the oracle, and PI, for the public input, is inserted as a proof object because it has to be revealed to the prover. So it's a bit counterintuitive that we call that proof, but proof means a message sent to the prover. It means it is part of the proof. even if it's a nonsense from an academia perspective. And also a number of public inputs, because the PI is, colon is larger than the actual number of public inputs, is because every colon should have the same size. So, and also the value of the queues should be known beforehand, of course, because that's the circuit description. Okay, so now we can declare the queries. So on your right, you have a global constraint, which is an arithmetic expression that has to vanish on all the rows of every column that is touching. We can recognize the equation of the Planck gate constraint at the beginning. And we have a fixed permutation, which is instantiated by some forced permutation that has to make the concatenation of XA, XB, XC invariant. And that's how Planck proves the copy constraints. Then finally, we need to add a verifier check. This is to ensure that the PI that is sent to the verifier is well formed and that it should be padded on the right with zeros. Okay. So now, once we have that, we can compile that into an actual protocol. So here I added the part that converts the PIOP into a concrete protocol, because I added the vortex.compile, vortex being the polynomial commitment that we use. And now we just have to run it. So the only thing we need to specify is how concretely we are going to assign our columns, because this is the only thing that is unknown at this stage after reading the protocol description. So yeah, we just provide it and we assign it. It's 4 lines of code. And so yeah, now so we have something that allows us to write Planck constraints manually. But I don't know if you have tried writing a Planck circuit by hand, but this is really difficult. And it turns out that Gnarks offers a very nice front end to write circuits. So let's just write a wrapper of what we just wrote using Gnarks so that we can use a Gnarks circuit description. So I did the implementation. It was a bit longer than 100 lines, but it was essentially a few automated stuff. Okay, so let's do a circuit. So let's use Fibonacci as a use case. So my circuit, you have 2 values, U0, U1 as input, and you want to have the 50th number of the Fibonacci sequence generated by U0 and U1. U0 and U1 being public parameters. So on your right, you have the circuit writing in Gnarks, so you can see that it's fairly easy and much simpler than writing a circuit by hand. And then we just have to run it, and that's it. You just create your proof function that is explaining how to assign the column. You run wizard.proof, and it's going to generate a proof for you using vertex as a polynomial commitment, and you can verify that in 1 line. All right. I have 6 seconds for the future improvement. So we want to add more queries, and we think we can also remove the necessity for rounds to specify rounds in the protocol, as it should be inferred automatically. Right, that's it. You can check out the code here. Yeah.
Amazing, Alexandre. Thanks so much for the great introduction of Wizard. So reminder that if you scan the QR code, you will attend the session and you can ask questions and you can also claim an NFT. So, and you can also vote. So if you have a question that you really want it to be answered, vote for them. So let's start with the top one. Does Wizard support lookup tables? And can it be used to implement local tables based on CKVMs?
Absolutely. So the way you would do it is, for instance, say, so what you can do, first of all, if you want to do range checks, so that's a big use case for lookup table, you already have a range query. So you just take 1 column and you say, I have this query that just enforces the whole column to be within bound, and that's all you do. A second way, if you want to do more complicated range checks like XOR, for instance, then you would have to specify 3 columns for your XOR. 1 column for the left side, the right side, and 1 for the result. And in this column, you put all the possibilities. So maybe say for 8 bits to 8 bits, you would have 2 to the 16 possibility. So you write down all of that in your table, and then you create a lookup constraints between this table and a triplet of columns for which you want to enforce a XOR constraint. And you can also add conditional lookups. So you can have a fourth column that say that contains zeros or one, and that activate the XOR constraints or not.
Great, thanks for the answer. The next question is, can you create different custom gates? And at which instance do you decide which row corresponds to each kind of gate?
So when you generate a global constraint, this is essentially what is your custom gate, then it's going to apply over everything. But the wizard framework is more abstract than this. Essentially, there is a general technique to do it, which is to say that you add a selectors column that says which constraint is going to apply for each, and you have a sum product of your constraints custom gates expression multiplied by an indicative that asks whether this constraint is active here or not, and you would merge everything into a single global constraint in the end. So yes, you could implement custom gates. Actually, that's what they do all the time when they specify the EVM.
Great. The next question is about recursion. So is recursion something that would be implemented in Wizard, or would it be separately like a commitment?
So there is separate where you can do recursion. So we do it inside of the wizard at the same time and outside. The first way, we have a compilation step that is called self-recursion that usually goes just after Vortex, that takes a Vortex proof and re-arithmetize it. And we can do proofs of that again, and we repeat, and we can shrink the proof. That's because Vortex, as a single polynomial commitment, has a square root verifier time, but applying log-log-n application of self-recursion, you get constant size proof.
Great. And the last question that we have in the queue, at least for now, is that it's great that you can define an ideal protocol programmatically, and it seems that that does make it easy. Does that make it easy or possible to support automated formal verification, or you see proofs of security?
So I'm not too sure what it would entail exactly to formally verify. So we could formally verify like the standard set of compilers that we have. I think this is at least a necessity, but then there is a protocol description. It should be formally verified. This, I don't know how to do it. I don't know, and I can't tell you how to make it easy. But that would be a great use case. I agree.
Yeah, it would be great maybe after have that conversation. And I think with that, we cover all the questions. So thank you, Alexandre. Thank you for everyone for the questions. Some applause. Thanks so much.
Thank you.
We'll be back in 4 minutes with the next talk, so stay tuned. Welcome back. You have a seat because we have a next great presentation. So this next presentation by Leo Young, we're going to talk about zk-EVM prover optimizations. And we're going to go through different techniques applied on the Linea zk-EVM and bottlenecks and different innovations and explorations. So I won't tell anymore, I won't get ahead. But remember that there's a QR code. You can submit your questions while the presentation is going. And you can also vote for the questions that you like the most. So please welcome Leo.
Hello. It's first time I'm wearing this microphone. I feel like I'm a K-pop star now. Anyway, yeah, so really nice to meet you. I'm Leo Jung. I'm a senior research engineer at Linea. And today I'm going to talk about how to optimize zk-EVM provers. So this is the outline of today's talk. I will talk about the motivation and also the introduction of this talk. I will share how to optimize zk-EVM provers based on our more than 1 year of our optimization experience. And then we'll conclude the talk. So first time, so this is the initial challenge and problems we had. So Linea launched our mainnet last year, August, and we were so happy. So we were kind of dancing all the time. But we realized that prover was really slow. So we were like, what's going on here? And we were spending a lot of money for provers. So we thought it's a huge problem, and we decided to optimize it. So what we did is for more than 1 year, we spent a lot of time and effort optimizing prover in production. So that picture, that's actually me fixing and optimizing prover in production. So your prover is running mainnet, and you need to fix it. That's what I did. But luckily, we were able to reduce the prover runtime by almost 75%, which is good. So today, that's the main content that I'm going to share today. First of all, let's talk about why it's important to optimize zk-EVM prover. The first thing is, of course, money. This is one of the biggest cost contributors in zk rollups. And prover optimization directly means you can reduce the operating cost of your zk project, so which is very important. The second, the performance impact. So when you optimize zk prover, that means you have less runtime of your prover, which also means you have faster verification and finalization. And in that way, you can improve your TPS, right? And your users will be happy. And lastly, you can also improve your scalability by optimizing zk prover, because you can support more transactions, which means you can handle more complex proofs as well. So let me share some common bottlenecks here. So most zk-EVM provers and projects, they have really high complexity. So inherently, I mean, zk-EVMs are very complex because we want to kind of simulate EVMs, right? And we want to provide the full compatibility. So every project has their own design, their architecture, so it's really hard to optimize. But all the projects, they're something in common. They have high resource consumptions, right? So CPU and memory, they're using a lot of CPU and memory, and also because to support large-scale cryptographic calculations. So we have these things in common. So the common bottlenecks is you have CPU usage and parallelization issues, probably. And then you will have memory overhead a lot. And you will have I/O bottlenecks because you are dealing with a huge amount of data. So this talk, I will talk about what we will cover and what will not be covered. So first time, we will not cover Linea-specific optimizations because, you know, if I share that kind of information, you can't apply that to your project. So I'm not going to talk about detailed cryptographic theory behind our project or zk-EVM. And also, I will not share about hardware accelerated optimizations. And then we'll focus on CPU optimizations. So here, I will cover some quick wins and strategies. So you can just pick up and apply to your project in a week or 2 weeks, or sometimes maybe on the flight going back to your home, you can actually apply that easily. And then we'll share mostly on CPU and memory optimizations without any significant changes on your architecture or on your code. So that was the intro. I will share about the problems right now and how to actually optimize it. The first thing you have to do is you need to know your code, right? So there's a really famous quote in this programming world, which is premature optimization is really bad. Let's just don't do that. Because, sometimes you want to optimize your code because, it feels fun. So you just optimize it. And because you think it's going to be the bottleneck, but most cases it's not. So before you actually start optimizing your code, you need to find out the problems first. And the most common way or easiest way to do that is using CPU and memory profiling. So most languages, they have kind of built-in profiling tools so that you can visualize your CPU or memory usage, and you can understand your code there. In our case, we are using Golang. We are based in, so we used that tool, the profiling tool, to visualize our program. So this is the CPU and memory profiling we actually had. This is the whole life cycle of our prover. So I know what you are thinking right now. You're like, oh no, I'm gonna just sleep for 20 minutes, wake me up in 20 minutes. But don't worry, yeah. We spent a lot of time, and then we kind of categorized them for you, and we'll share that quickly today. So here you can see many holes or sparse areas, which is white colored. So here, the green color means you are using CPU very extensively, so you're good. But the white color, that means something is wrong. So mostly, it means CPU is underutilized. So you find out which part is not being used fully, and then you go into the code, and you look at the code, and you can fix it. And on top of that, we have memory usage patterns. And the main goal of memory usage or memory optimization is to reduce the memory peaks. So first time, I will talk about CPU, and then we'll move to memory. So you have many different CPU issues, but mostly it's going to be two cases. The first one is poor parallelization, and then the second one is CPU underutilization. The first pattern, when you look at this graph, here you have CPU number 1 to maybe CPU number 100. And we are using only 5 CPUs actively, and the others are just doing nothing. So we realized in many cases we have these issues. So we had to add more parallelization to improve that. The second one is you are actually using 100 CPUs, but between some runtimes, you are waiting for something. So that means you are underutilizing your CPU. The first thing, so how to improve parallelization. It is a common methodology that you can apply to your program. So first thing is you just draw your modules like a graph on the left, and then you also draw your dependencies like that. And then on the right side, you can have those Lego blocks, and then you can find out some better execution scenarios. For example, in our case, so this was the issue right now, right? And this module actually was about reading the setup for the prover, and especially proven key. We were reading this from the disk. And originally on the left side, that V5 had issues of parallelization. So we changed these blocks on the left to the right. So we moved that V5 to the early stage of our prover lifecycle, so that the total runtime of T2 became smaller than T1. The other common issue is CPU underutilization. So this has actually many causes, so many root issues. So the first one could be poor parallelization. Second one, synchronization issues and lockup issues. And sometimes you have some blocking I/O operations when you're using disk or a network. So in our case, we had this issue in FFT, and we had synchronization issue in our data structure, so we had to slightly change our data structure so the CPUs are not waiting for other data. So after optimizing GPU, so we changed our CPU usage pattern from left side to the right side. So we got one OK cat is happy. So we got one OK cat for CPU optimization, but we need one more for memory optimization. So let's move to memory optimization. Actually, more than CPU, memory optimization is more important because in general, in most cloud systems or cloud services, memory is more expensive than CPU. For example, you can see that our peak memory usage was 700 gigabytes. And then so we have to use some machine with 970 gigabytes, right? Which is very expensive. But when we can move from this one to the other one with 380 gigabytes, we can save a lot of money. But we can get more cores. So our plan was to reduce our CPU peak memory to maybe somewhere between somewhere around 380 gigabytes. So the goal is flatten memory usage and memory peak. That's the most important one when you are working on memory optimization. So the first thing we did is using memory pooling. So it means sometimes you have many data structures in your prover, and some data structures are being used hundreds of times or thousands of times. And when you just allocate that data structure every time when you need that, you will allocate that memory, and also sometimes the garbage collector will spend some time to return that memory to the system. So instead of doing that, you just set up this large memory pool for your data structure, and you just allocate that and use it. And when you don't use it, you're not using it anymore, you just return it to the pool, and you keep doing this. So you only allocate once, and you just use it, and you just return it only once. So by using this one, we reduced our memory peak to 450 gigabytes. But still not enough. So we use this mem limit. Most languages, they support this feature. So it's a soft limit of memory peak. So the language, for you, they trigger garbage collection when the memory usage hits this memory limit. So in our case, when you see it here, inside red circle, we have many memory peaks, but that's exactly around 370 gigabytes. So your language or runtime will just run garbage collection, so it will not go up above like 370 gigabytes here. So finally, we were able to move to the smaller machine, but with more cores and cheaper machine. But we found out we are spending too much time in these specific areas because of garbage collection. So we thought maybe we need to do something more. So garbage collection is something that in many garbage collected languages, they just do it for you, right? So it's very convenient, but it's really hard to predict when this will happen. So what if it happens during a very critical tasks or areas of your code? This will be a huge problem. For example, in our code here, so we are doing some FFT inverse function over there, and it's very CPU intensive and memory intensive. So we realized that every time when this part is running, the language runtime try to actually run garbage collection randomly. And because it is really critical in terms of CPU usage and memory usage, it slowed down the whole program a lot. So we realized let's manually garbage collect before entering that critical areas. So we decide to run manual garbage collection before these critical tasks so that we have less context switching overhead inside or during these critical areas, and it actually reduce the runtime a lot. So if you have these kind of issues, you can just manually run garbage collection before those areas, and you will get a lot of improvement. Lastly, so we felt everything's okay, looks good, but sometimes when you have really large input data, you will see sometimes out of memory issue, right? Because we have a very specific size of physical memory, it's not easy to solve that. So sometimes you need to move to a larger machine, very expensive machine with a larger memory, and then you have to run that. But we find out this solution. It's called the ZRAM. It's an in-memory swap feature. And most Linux systems have this feature, and you can just turn it on and turn it off. We all know the swap space in storage or disk, right? But it's slow, so in production it's almost hard, it's impossible to use it. But this feature is an in-memory swap. So this one, if you don't have enough memory, this will compress your data inside your memory and will just store that within your memory. So, for example, over there, we have like 740 gigabytes of memory, physical memory. But I set up like 1.5 terabyte of swap space. So you can actually have a lot more memory and a kind of fast swap space in your system. So we are actively using this for massive integration tests with terabytes of memory usage. So finally, we got two happy OK cats. And I will share quickly one more optimization things. So one thing is data compression. So we realized that the transaction data has really high compression ratio. So if your I/O or network is the bottleneck, you can just compress it. And for example, our case, 40 gigabyte of trace could be 2 gigabyte of trace. And zeroization is a kind of time you spend on initializing your data. So because we are dealing with very large data set and very large data structure, sometimes time taken for initializing your data is a lot. So you might need to auto zeroization supported by your language, or use optimized library or low-level libraries for zeroization. So let's conclude the talk. So result, we were so happy, yeah. And then we reduced like EVM proof of runtime by 75%, which is good. And we saved a lot of operating cost. And not only saving the operating cost, we reinvented that into our prover system. So we increased the finality speed and also higher TPS. And ironically, we were able to understand what we did and what we built and what we are doing, which is, I think, most important one. And some lessons we learned: please do not pre-optimize your code unless you fully understand your code. So I strongly recommend that make optimizations only based on your measurement. And instead of doing this with a kind of a local view, you need someone to have a global view so that you can set priorities for optimizations. Our future work includes distributed GKVM prover, so different modules running on different machines. That means we can use some smaller machines to save cost. And then we are thinking about also how do we accelerate provers. We think optimization is never a one-time task, so please measure, analyze, optimize, and repeat. Thank you.
Amazing. Great presentation, Leo. All right. So remember, you can always ask more questions and vote for the questions that you want it to be answered. So let's start with the first one. How could a FIRT okay, this is spicy. How could a FIRT challenge benchmark over same machines and input be organized among CK-L2s? So how to benchmark up against different systems.
I think it's really hard. Yeah, I think because I explained that in the maybe introduction, because every team or every project has different architecture, different models, based on different cryptography. So I think this is just a good research area. I mean, it hasn't been solved yet. So yeah, it's hard. At least maybe GPU-based, CPU-based, or some specific cryptography-based. It could be benchmarked, but in general, it's really hard. Yeah.
Mm-hmm. Yeah, agreed. Would you recommend on-prem prover or cloud prover?
Right now, I think I think you better start from the cloud-based, yeah, because
Cloud-based.
Especially on the early stage, or especially when you are a small project.
Makes sense. If the memory compresses well, then couldn't you instead use more efficient data structures in Linea?
Sorry.
Is the top one. If the memory compresses well, then couldn't you instead use more efficient data structures in Linea?
Yeah, actually, yeah, that's true. We are trying to optimize our data structure as well. Right now, we don't actually compress a data structure in production because to avoid some side effects. But after optimizing a lot and we have too many transactions or too much transactions, I think, yeah, we need to come up with better data structure.
Yeah, as you say, it never ends, right?
Yeah.
Always optimizing. I've read that the finality of Linea is around 8 to 32 hours. Will these improvements allow these to be reduced? And if so, how low can it go?
Actually, the finality time includes many different factors, actually. Not only the prover itself, but number of transactions or service layer agreement or something like that. So it's not only, it doesn't depend on solely on the prover optimization, actually. It's more than that, so.
Yeah, agreed. Have you had examples in where an attempted optimization actually backfire in an unpredictable way?
Yeah, that's true. So I think that mem limit stuff is actually one of them. Without mem limit, the soft memory limit stuff, because that automatically triggering garbage collection for you. We didn't have any issues in global constraints part, but after applying that, we actually got a lot of garbage collection calls within global constraints, and maybe the runtime increased a lot by that. And that was actually a huge issue. And we finally found out and I fixed it.
Great. Has Linea CKVM thought about switching to CKVM to further improve performance?
I have no idea on this talk, in this question, so yeah, maybe I'll skip it.
Yeah, let's skip it. Remember, you can always find the speaker after these questions.
We can discuss about it.
Discuss it, and yeah. What are some trade-offs that Linea made in contrast with other CK EVMs?
Well, let's say I saw many projects based on GPU or FPGA and hardware accelerated, and we thought starting with the simplest design and architecture is the best one, and especially for so that any small project or researchers, they can just simply run our product and then share ideas to be more decentralized. So for a while, we think we're going to keep this design choice, and we'll continuously work on optimization of CPU-based CKVMs and stuff.
Great. And I think we have time for one more. Besides those techniques, did Linea explore hardware acceleration?
Yeah, this question, we are still thinking about it actually, but maybe at least for a while, until everything's stabilized enough, researched enough, we will keep working on CPU-based.
Great. I think with that, we finished. Please give a round of applause. Thank you, Leo. We'll be back in a few minutes. There's more talks and great information. So yeah, stay tuned. right, all right. We have a good break. We're coming to the next talk this afternoon. It's titled Top Opcode Offenders in the ZK EVM. And I think it's very relevant, especially as we're thinking about all the changes that we can add to layer 1 and basically how that affects layer 2s and ZK projects. So we have Carlos Matallana here next. He will be having this conversation. Again, remember, you can scan the QR code if you're just joining. If you scan the QR code, you can join the Q&A, you can submit questions, and you can also vote for the questions that you like the most. So please, with some applause, please welcome Carlos.
Carlos Matallana, work at Polygon, and today I will be talking about the top code offenders in the ZKVM. In order to explain that, basically I will do at the very beginning some introductions about what are the ZK counters, what are the types of the ZK counters available, and how many ZK counters do we have available on the ZKVM. The second point will be in the analysis of the offenders. You will see that there are some straightforward offenders on the ZKVM, so there is no correlation between the gas consumed on Ethereum and the ZK counters consumed on the ZKVM. But I will go more into the details. There are some opcodes that are quite straightforward, but when we analyze, in this case I will analyze a Uniswap swap, we will see which is the worst opcodes that performs very bad in terms of ratio between gas and ZK counters. So for that purpose, I will analyze a Uniswap swap trace. And in the third point, I will basically explain it, what are the next steps, how, I would say, how we can optimize those opcodes in order to have a better ratio between the gas and the ZK counters wasted. And also I will explain two different approaches about how those opcodes could be priced on the ZKVM. Okay, so let's start. What are the ZK counters? You can imagine the ZK counters, if you can imagine the gas on Ethereum in order to measure some computational cost, execution cost, you can imagine the ZK counters exactly the same as the gas, but on the ZKVM, okay? Basically, in the ZKVM, we have, in Ethereum, we have a unit, which is a block. In the ZKVM, we have a unit of proving, which is a batch. So there is some relation over there. And another difference between Ethereum and the ZKVM, it's like on Ethereum, we have one single dimensional resource, which is the gas, but on the ZKVM side, we have the ZK counters and we have multiple of them. Okay, so basically this table summarizes what I have just said. On Ethereum, we have a unit, which is a block. The ZKVM is a batch. The batch consumes some gas. It has some limitation on the gas, and the gas basically reflects the computational resources that you are wasting when you execute an opcode. This is basically a single dimensional gas. On the ZKVM side, we have a batch, which is our unit of proving. We have the ZK counters. We have several of them, so it's kind of multidimensional. And basically, they reflect the proof computational cost. Okay. Well, this is basically a piece of code. This is in ZK assembly. Basically, this is the ZK ROM. We implement the EVM in this ZK assembly language, which implements the EVM in a ZK assembly language. And basically, those are all the ZK counters and all these values. Quite difficult to read it, so in order to understand it better, we have, as I mentioned, in the ZKVM, we have a unit, which is the batch, and this batch has several ZK counters. What are those ZK counters? Basically, we have the steps. You can imagine the steps. Sometimes I have heard about kind of the, you can change the word, and instead of saying steps, you can say kind of cycles. We have the arithmetic state machine in order to do multiplications. Well, also we use the state machine in order to prove divisions by doing multiplications. We have the binary state machine in order to do additions, subtractions, and bitwise operations, basically. We have the memory aligned state machine. Basically, when you read a slot on the ZKVM, two different slots, and you want to join all the bytes together, we use that state machine. We have the KICAC state machine, which is obvious, in order to do KICAC hashing. We have the padding Poseidon state machine and the Poseidon state machine. Again, quite straightforward to do Poseidon hashing. And when we want to do a linear Poseidon, which is a concatenation of Poseidons in order to hash a long array of bytes, we need to use the padding Poseidon state machine. And the very last one is the SHA-256 state machine, which also do hashing, of course. So it is very important to say that each state machine has its own capacity. So as you may see on this slide, we have a lot of steps because I would say the computational cost of a step is quite low. It's just one, I would say, one hit, one row when we go through the program, through the ZKVM ROM. But for example, on the KICAC, you can see that there are way less resources over there. Why is that? Because basically it's more complex. So it uses more resources. So it has less capacity, basically. One thing that is very important also to mention is that in a batch, we have all those ZK resources. None of those ZK resources can be overflow. If any of those ZK resources is overflowed, it means that the proof could not be generated, basically. The prover could not generate that proof. So we need to be very aware of that. Okay, so let's do some kind of analysis on the, I would say, top code offenders on the ZKVM. And as I mentioned, there are super straightforward opcodes that consumes ZK counters very directly, and clearly there are offenders on the ZKVM. What I mean when I say offenders, it means that those opcodes consumes some gas, and this gas is basically not reflected on the ZK counters that they consume. So there is a misalignment over there. The most straightforward one, and of course you may heard about, in every ZKVM, if you do a loop of KICACs, then you are wasting a lot of ZK resources, but you pay quite cheap gas. So for example, the first code is the KICAC. The second code is the code copy and call data copy. In this case, I would say that all opcodes that has some kind of dynamic gas pricing, given the memory expansion, we need to do some computations on the ZKVM. That, of course, it calls some arithmetizations, binary, and steps. And also, when we do some kind of copy region between contexts, one context to another context, it will basically waste a lot of steps as well. The third one, also, I think it's very clear, the example, it's the external coder copy opcode. In this case, we are just, this opcode basically just copy some bytes of a bytecode into a memory region. Okay, that's it. What you need to do inside the ZKVM? You need to provide the full bytecode. You need to hash it with the linear Poseidon. You need to check that that hash matches the one that you need to read on the state tree. So now you know that the full bytecode is correct. And you need to go to the exactly byte or number of bytes that you want to copy into your memory region, take that byte, and then copy to the memory region. So there is a lot of things to do on the ZKVM, but the cost of this code is not that much. And of course, the clear offenders are the precompiled smart contracts. You know, there are specific functions on Ethereum, like issue recover, pairings, modular exponentiation, and so on. And there is a very huge misalignment between the precompiled smart contract gas pricing and the ZK counter resourcing consuming on the ZKVM. Okay, those opcodes I would say that are very clear, that are offenders, but I wanted to analyze deeper, not the clear opcodes, but the standard opcodes, standard transactions on the EVM. In this case, basically, here, this table, well, before going to the table, all these numbers belong, there are some assumptions. The first assumption is that here I'm showing data of one batch that has only one block, and this block has n transactions, okay? And these transactions are always the same type. So you can imagine a block in the ZKVM with just Ether transfers, with just ERC20 token transfers, and just with Uniswap swaps. So let's go for the first one, the Ethereum transfer. We can fill up to more or less 2,000 transactions inside a batch, and we can see that the top ZK counter, the more limiting ZK counter, is the arithmetic. Why? Because we are basically checking the signature inside the ZKVM, so we are doing a lot of EC recover. The EC recover uses a lot of arithmetic state machines. If we go to the next two ones, the ERC20 token and the Uniswap swap, what we can see is that, okay, we can fit less transactions because you have some execution to do. And we can see that the top opcoded ZK counter offender are basically the steps. Either in the ERC20 token and the Uniswap swap. Regarding the Uniswap swap, it gets even worse. I mean, you hit the top, the limit of steps, and the other state machines remain at half capacity, even less. Given those numbers, we're going to get into the details of what are the opcodes in a Uniswap swap trace that consumes more steps. Okay, so yes, what are the opcodes that consume more steps in a Uniswap swap? So, in a Uniswap, if you analyze a trace of the Uniswap swap, you will find that push 1, push 2, mstore, pop, and push 20 are the most used opcodes. If you join all the steps consumed by all the appearance of that opcodes on the book trace, you will find that the push 1 opcode will weigh around 12,000 steps. And it appears, in the Uniswap swap, it appears 658 times. So same for push 2, mstore, pop, and push 20. So basically, these opcodes are the ones that consumes the most steps on a Uniswap swap. But let's go again into the details. Inside these opcodes, is the user paying the correct gas price? I mean, is the user paying the correct gas price in order because the opcode is consuming 12,000 steps? So here's the question, yes or no? So let's go to analyze a little bit. And here, basically, what I did here is comparing the gas of an opcode versus the steps that opcode consumed on the ZKVM. So basically, we can get some kind of a ratio between gas and steps. Here we can say that by far, the worst opcode is the code copy, because it costs just 15 gas, and it consumes 1,000 steps. So the ratio is, I would say, quite bad. The second one is the mstore. Here I highlight it in green, because it's one of the opcodes that has more appearance also on a Uniswap swap trace. So clearly, if we want to increase the efficiency of a batch in the ZKVM, clearly we need to optimize. We need to get better ratio in the mstore, for example, opcode. Third one is the call data copy, then push 32, and then call data load. If we want to get rid of those top opcode offenders, what we should do is repricing them or optimize them in order to get a better ratio, basically. On the other side, what are the best opcodes? What are the ones that basically the user is paying, I would say, fairly about the ZK counters that it consumes on the ZKVM? So here we have, for example, the one, jump conditional, external code size, or log3. Of course, log3 as a store and this kind of opcodes, the ratio is very, 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 very low, because basically you are paying that you are storing some data on the receipt tree or on the state tree. Okay, so now the question is how to price those opcodes accordingly to the ZK counters that they are consuming, basically. Okay, and the most straightforward approach, which is the one that we are following right now, is an static approach. You can see you can imagine the batch as a monolithic batch. So we have all the resources available, and think that regardless of the transactions that are executed on that batch has a price. That's it. In this case, $0.01. So the sequencer basically pays for the batches that it posts to layer 1. And the verifier, when the verifier verifies those batches that are posted to layer 1, it receives the fees. That's it. Super simple. So the user, I would say that the user does not care about that, only the sequencer. And of course, this price is split among all the transactions in a batch. But then we can use, the next iteration, I would say, we can use kind of a dynamic approach. The dynamic approach is very similar to the gas limit on Ethereum. So imagine that we introduce here a new concept, which is kind of the ZK gas and ZK gas limit. So the sequencer does not pay for a full batch, but the batch is dynamic. So it means that basically the prover can decide the amount of the state machines that it needs to prove, basically. We can achieve that via the BAT cops. And basically here the sequencer just sets a ZK gas limit, very similar to the gas limit, which is the ZK gas that the sequencer is willing to pay for a batch. And then when the verifier verifies the proof, it's subtracting gas for the gas limit. And if it runs out, it will be kind of an out of gas, but out of gas limit. So the batch is kind of invalid. Then the next step is, okay, let's analyze properly in the language, in the compiler, why those opcodes are performing so bad. And let's try to optimize them. Let's try to iterate, let's try to add more instructions in order for those opcodes to have a better ratio. Let's try to improve the constraints, the pill, in order for those opcodes to have a better ratio and not to be offenders on the ZKVM. If you want to know more about that, tomorrow we will do a workshop at 3 p.m. on Classroom C. It is called Optimize ZKVM Throughput Series 2. We did one on Brussels, which won the Series 1. Was a lot of people over there. So we're going to explain some optimizations that we did on the ZK assembly side and on the compiler in order to optimize those top opcode offenders. Okay, thank you.
Amazing. Great talk, Carlos. Muchas gracias. All right. So remember, you can post your questions on the QR code. We're going to start to hit the first one, the top one. What happens if the sequencer has a bug and it creates a batch that overflows the counters and then it gets committed to Ethereum?
Yes, inside the, good question. Inside the ROM, it can happen two things. So inside the ROM, if the sequencer has a bug and commits a batch that overflows the counter, we have a program, as I mentioned, which is the ROM, which is an EVM implementation. But inside the ZKVM ROM, we control the counters that are wasted. If you overflow the counters, then the prover can prove the batch, but it's an invalid batch. I want to say invalid batch, it means that the old state root is equal to the new state root. So there is no state transition function over there. The issue is when you have a bug, the sequencer and in the ROM. Then you end up in a situation when you cannot prove the batch.
Amazing, thanks. The next one is, how much does EOF help eliminate or reduce the top offender opcodes?
Just read once this EIP. I would say that we need to analyze deeper what will be the top of offenders given the change of the bytecode and EOF, basically.
Yep.
It's very difficult to answer.
yeah, no, I agree. It's common, but it's, yeah, it just requires a lot of work and, research. Do you still need counters if your proving system supports continuations?
You need counters, but I would say that those counters will not overflow since you can continue the proving execution into another batch. So this will mean that basically any Ethereum transaction will be provable. But still, if you are just doing a loop of keycats, imagine that you're doing a very large loop of keycats and it consumes 7 batches. That Ethereum transaction needs to pay the 7 batches. So we need to be aware on the proving system that it's compute 7 batches. I mean, thanks to the continuation, we will be able to prove it. You need to pay for it.
Yep, makes sense. So next is around gas costs. Would multidimensional EIP 1559 be useful?
I would say I was in some meetings discussing about this multidimensional gas pricing, and it could be done, but it's not easy to modify the whole, I mean, adding kind of a new transactions with new fields in order to sign this gas that it does not reflect the computation, which is the gas, but gas layer 2, or ZK gas, whatever you want to call it, that basically reflects the ZK counters or proving computation. You need to change libraries, you need to change UX, UI, MetaMask. This is not easy to achieve.
A lot of work.
A lot of work.
All right. How do opcodes limit work with forced transactions, and would it be valid reason to exclude transactions?
I mean, forced transactions at the very beginning is just regular transactions, but you just bypass the sequencer, and it works exactly the same that a standard transaction. If a forced transactions overflows the batch, which can be, and as I mentioned before in the first question, the batch will be invalid, and that's it. So at the very end, you are kind of, you want to force your transactions, but you are not achieving to execute your transactions because the batch is invalid. So, and every time, of course, that a user posts a forced transaction into layer 1, the user needs to pay for it because you are bypassing the sequencer.
Right, right. The next one is, are there any steps that smart contract developers can already take now to reduce the usage of those offending opcodes?
It's very difficult. You would need to go into assembly code, otherwise Solidity just put the opcodes most beneficial for execution, not to take into account the proving system. So I would say it's very difficult.
Yeah, I guess it would require like, yeah, architecting the compilers and doing a whole bunch of like changes, and then
yes, again, yeah,
yeah, really deep knowledge of that. Are there any? This is the last one. Are there any concerns with the resulting divergence with L1 fees in terms of user experience?
I mean, we are achieving a stage, actually, that the difference. I mean, these proving costs are every time that are cheaper, and cheaper. So I would not expect a lot of divergence between layer 1 fees, but still the ZKVM has some mechanism in order to port layer 1 fees into layer 2. It's the EIP 1559 in the base fee, so it can reflect the data availability cost on layer 1. So yeah, this is just a technique, but there are several ones.
Yeah, but I guess like there's a lot of improvements still in the backlog to keep improving layer 2s instead of like, yeah. It's a lot of work. And I think with that, we complete all the questions. Thank you so much, Carlos. Thank you. It's been a pleasure.
Thanks.
All right, folks. So we still have 3 more sessions in this afternoon, evening. We'll be back in 7 minutes. So take a break, come back, stretch, or yeah, just stay here. So we enjoy applied cryptography. Thanks. Hello, hello. So we're back for the next talk. Grab some seat, take a look at what we're going to talk about now. So in this talk, we're going to talk about how the bridge is not going to break your contracts. And it's a look about what's coming, what's changing, but also what's remaining. Our speaker, Adrian Croix, is going to be our next speaker. So give a big round of applause, please.
Thank you. Hello, everyone. Yeah, the Verge is not going to break our contracts. That's good, right? So I work for OpenZeppelin, and at OpenZeppelin we provide all kinds of services to the community that obviously includes the open source smart contract libraries, but also audits and so on. And we do that because we want to provide a good context, a good ground for developers maybe like you to build the next $1 trillion economy that is going to be powered by smart contracts. And so in doing so, we want to understand what's the environment you'll be working with, how the EVM works, how the blockchain works, and share that knowledge with you through these talks and also through the best practices that we apply to our contracts. And yeah, just a few days, maybe weeks ago, I don't remember, we released the last version of the smart contract library, the version 5.1 that's been in the making for quite a while. And to me personally, it's a big milestone because it's the first time that we put knowledge of upcoming blockchain change like the Verge into the design of the contract. We adopt a proactive approach so that the contract you deploy today may be more efficient in a few months. So what is the Verge and how is it going to affect dev? So I was told to not talk of the merge too much, but to rather mention the transition to a more stateless Ethereum with stateless clients. The Verge being one of the approaches for that transition. And what the Verge does and how it can achieve better statelessness, a stateless client, is by changing the storage layout to be more friendly to ZK proving. So right now what we have on Ethereum is a storage layout where we have a Patricia Merkle tree that is divided in two sections. And the top section is basically the entire world of accounts. And under accounts, some accounts don't have storage, and that's done, but some accounts do have storage. And then you have to go further down and do the account storage tree. And that's how it works. And when you want to prove some storage, you have to prove a Merkle proof that goes all the way from the bottom to the top. And that's kind of long, that's kind of expensive, that's impractical if you want to build a stateless client. So what the Verge does is propose to change this storage layout to use a Merkle tree that contains all the data of all the accounts in a different pattern. And basically, there are still somehow two sections. There is a main tree that are the first 32 bytes of this Pedersen hash that is computed using the address of the account and the offset being like the position in the storage that we already have. And then that gives you an extension, and an extension contains 256 values. And then you use the last byte of your position, of your offset, to know where you're in the extension. That means that an extension is owned by a single account, but then all these extensions of all these accounts are in the same Merkle tree. And this is a radically different vision from the previous slide, because in the previous slide, all slots were identical. Slot 1 and slot 20 were basically the same object, and warming one up was required when you wanted to read or write to it, and the same was true for the other slot. And all slots were identical in the sense that you would have to warm them up individually. But with the Verge, what you're warming up, and by warming up in the case of the Verge, we don't really, what we mean is put in the proof, so in the commitment. I don't remember the name, it will come back. But what we do is we put this complete extension and we prove it. And this completely changed the paradigm, because if you want to access two different slots, if they are in the same extension, you only pay once. So it's way more efficient to access storage that is close to one another, which was not the case before the Verge, which is not the case today. And so this is a rough timeline. We go from Devcon that we passed to Pectra that is coming soonish with a lot of great features. You may have heard about it during Devcon, to hopefully the Verge. This is changing. There may be Fusaka before. I'm sorry for that. But yeah, I'm really looking forward to this, as I hope many of you also are. And this will impact our contract, as we see. Like, it will impact them in the sense that the gas cost will be measured differently, and that has an impact. So that's why what I want to dive into today. And disclaimer, this is work in progress. The verge is not definitely final. And those are the best numbers I could come up with the help of Guillaume from the guest team, from the EF. But those are possibly not the final number, but it's still a good idea. So let's dive into this first graph. There are going to be a few of these, so please make sure we all understand what the color means. Here we're representing the gas prices of frequently done operation on tokens such as ERC20, 725, and 1155. And we have two types of operation. There are the simple transfers that are in blue, and there are the transfer from, so transferring someone else's token using a permission, that are in green. And in both cases, you have like a light blue, a light green, and a dark blue, a dark green. The lighter colors are the costs that apply today. The darker colors are the costs that apply after the verge. And this color scheme, we will keep it. Like lighter is now, darker is after the verge. And what we see here is that basically for all classical transfer operation on tokens, it's going to be more expensive. That's the bottom line. But not by a lot. So it will still continue to work unless you're crazy enough to hard-code gas prices somewhere in Europe, but like it could continue to work. But like ERC 721 is going to be affected a lot. The reason it's more affected than the other is like when you do a transfer from or a transfer in ERC 721, you are checking two types of approval because you can approve one token and you can approve an operator. And those two checks are two slots that are being warmed up and they are not in the same location, so there are two extensions. So the price, the over cost of warming an extension is significantly more visible in the case of ERC 721. And then let's look at other contracts that are quite interesting. There are the governance contracts. I love governance. And here we are looking at Open Zeppelin contracts in blue and Compound Governor Bravo in green. And we're looking at the different operations that are done in the life cycle of a governor proposal, which is you propose, you cast a vote, you queue, and then you execute. Here in the execute, we execute something small so that the actual cost of the execution is hidden. What we only look is the cost of the governor part. One thing that is quite interesting that we see is that for Governor Open Zeppelin, the price doesn't change that radically. The execute is a bit more expensive, but otherwise it stays pretty similar. And there is a good reason for that, is that in our Governor, we don't use storage that much. We try to reduce it to a minimum. On the other hand, Compound uses a lot of storage because when you propose, you store the proposal to the chain, and then you refer to that proposal stored on chain through its identifier. And what's good with Compound Bravo is that the proposal is stored in a structure that is very sequential. So it turns out to be very efficient in the context of the verge because like most of the proposal will be in the same extension. So you are actually saving a lot of cost by warming up the entire extension rather than warming up many, many slots. And that's why the verge is actually reducing the cost of the execution on Compound, at least in the proposed part. So the idea that the verge is going to make all contracts more expensive is wrong. Some contracts can be made cheaper with the verge, and it all comes down to how the contracts are designed and what the practices of the developers are. This is something I wanted to measure. It's the cost of trading tokens on Uniswap. So the x-axis is the number of hops. Like the very leftmost points are just trading token A for token B, and the rightmost point, it's trading token A for token B, for token C, for token D, all the way to like token G or something like that. And so it's scaled basically linearly. And in blue, you have Compound V2. In green, you have Compound V2, sorry, Uniswap V2. In green, you have Uniswap V3. And what we see is that Uniswap V2 is a bit less expensive than Uniswap V3 today because there is less logic with the narrowed down position and the capital efficiency. And that will greatly, like this additional storage will greatly be visible in Uniswap V3. So it's likely that Uniswap V3 is still the better choice after the transition to Verkle because it's just way more capital efficient and the gas you pay will be saved elsewhere because of like you will have better prices on your token. But something that interests me a lot is Uniswap V4 because Uniswap V4, and unfortunately, I was not able to run it in Verkle. We can go on that later on. But Uniswap V4 doesn't use that much storage, at least not on the token side, because of the singleton design, there is no token transfer for the intermediary token. It's just like the first token and the last token that are being transferred, and the rest is just handled internally by the singleton contract. So I'm curious, I'm sorry I could not get those numbers, but whenever I get them, I'll make sure to share them everywhere I can, like on social media, because I want to see how Uniswap v4 does in Verkle. I'm expecting it to do pretty good. Maybe I'll be proven wrong, but maybe there is a very strong case for Uniswap v4 here. And again, I think that using transient storage and doing the way Uniswap v4 does it is probably like the kind of good design that we may want to do right now because they are good, but also in the long run because they will be more Verkle friendly. So smart contract design for a Verkle EVM, what you can do now. So it's pretty simple, like you want to avoid storage and you want to pack your storage together. And that's something I did for my last talk that was at HCC, is taking ERC 721, the token, and try to put stuff together. In particular, we discussed the fact that there is a token approval, an operator approval, an owner, and a balance. And the thing is that the owner and the token approval are both mappings that go from unit 256, which is a token ID, to an address in both cases. And rather than have two mapping, let's have a single mapping with a structure. And so when you load this structure, you are likely that it falls in the same extension. In some cases, it will not because of randomness of cache, but usually it should. And so these are changes that you can apply today. The reason we don't do it is because on the main contract is because it would break our storage layout, and that has an impact on our upgradable contract. But we could technically do it today. And like when you run them on the test network of Verkle, and again, the slide will be available online, so the links here, you will be able to click on them to look at all the witnesses. But you can see that on the left, it's the traditional ERC 721, and on the right, it's the one that is packed. And you see that you have two S loads that are significantly cheaper. Those were pretty old numbers, so I'm not sure the gas prices would be fully correct here. But the idea that the witness is smaller because of the packing, that remains valid. And so this is measured with today's number. You have ERC 721 from the main repo on the left and the packed version that is just my edit on the right that we don't ship yet. And you see that the prices of running these two versions today on Cancun is basically the same. Like it's marginally different. That's experimental error. But after transition to a Verge node, like you see that the ERC 721 packed really greatly reduces the overcost of like warming up the extension by about a third. Like we move from 3 extensions to 2 extensions somehow. So that's basically what we expected. So there are design decisions that you can make today that may not impact the optimization of your code right now, but that may have consequences in a few months, a few years, if we do this transition to the Verge for having a more stateless Ethereum. So the conclusion is the Verge is not going to break your contract. You're safe. At worst, it will be a bit more expensive, but most systems should be able to work with that seamlessly. But it will affect the cost, and you can make decent decisions today to improve that eventual future. And the decision you have to make are try to avoid storage, and that's a general set of rules, like avoid storage if you can. And if you cannot avoid storage, try to use contiguous storage. So use arrays instead of mapping. If you are writing a compiler, you can do a lot of work here, like in the arrays, or in Solidity and Viper, the lengths of an array are stored at the pre-image of the array, and then the value are stored at the hash of that pre-image. You could decide to put the length at the first slot of like the image, and not store anything at the pre-image. You would just shift your array by 1 and put the length at the same location as the first item. And it's likely that when you access low item in your array, like it's one less extension you have to load, so that may be an optimization. I've discussed that at length in my previous ETHCC talk, so if you are able and you are interested, have a look at it. Again, the link to the slide will be at the end. And yeah, like we do have some Verkle-friendly design choices, like in ERC 7201, and hopefully like the compiler will take care of all of that at some point, but for now it's not the case. And it will be breaking the storage pattern, so I'm not sure, I mean, something Solidity has never done before. So yeah, if you are inventing a new language, take that into account. Okay, thank you, and link to the slides. And if you just type share.adriencourbois.com, then it's indexed, you can get it from here.
Amazing. Great job, Adrian. All right, so we're going to get started with the questions. Remember, you can scan the QR code. You can send your questions. Thank you for the person who just did. You can also vote for the questions so they, get answered first. So thanks for the great presentation. So let's start with the first one. A little off topic. Do you also evaluate contract designs that optimize for EOF?
Not yet, but EOF is certainly something that is coming and likely sooner than Vertical. So we definitely, we care a lot about EOF. We want to make sure that it's not going to break our contract. We hope that we are able to ship the same contracts that work with EOF. It's unclear whether we are going to be able to do that or not. Maybe Solidity will have a major update anyway. But like we worry about EOF. I just don't have any final result to give you today.
Great question. Yes, keep sending the questions. Does OpenZeppelin has an array lib that stores the length in the first slot?
No, we don't have that kind of low-level libraries, not yet at least. So far, we've tried to always work with the Solidity layout and not modify it. But other people are doing it, and maybe we'll do that in the future. Why not? That's a good idea. We will have to discuss it.
Yeah. I think that you also mentioned a call to the compiler teams to just like start thinking about all these changes. So if there's anyone here to listen or said to a friend, I think that'll be useful. When do you expect that compilers, very relevant, Solidity and Viper optimize for verticals?
That's a very good question. I really don't know, and I'm not very optimistic. One particular reason is that Solidity never broke their storage representation, and that would mean breaking something they've never broken since 2015, 2016. So definitely not in version 0.8. Probably not. I expect Solidity 0.9 will probably be EOF or something like that. My expectation is that Solidity is moving to a completely different design of the compiler with standard libraries, and the compiler will be smaller. And maybe that's when, like the standard library, maybe OpenZeppelin. I mean, I'm counting that OpenZeppelin builds such standard library if Solidity ever relies on them, and that will be our job to do this kind of optimization. So yeah.
Great answer. All right, sorry, let me mark that. Okay, let me ask this question. Does it make sense to implement a set of addresses like 721 approvals with an array instead of mapping, maybe for a unit set or as a cache?
It really depends on the length of the mapping and how you access it. So not as a general rule, no. Maybe in some particular cases, yes. And that's what I want to encourage you to measure and to, like maybe next year at DevConnect, you give a talk about that.
Great. How does code chunking cost affect dApps?
I'm not sure I understand what code chunking costs, so maybe we can discuss that after outside and you can give me more detail because I cannot provide an answer right now, sorry.
Yeah, no, that's fair. It seems like 20% more expensive transactions is a big deal, even if it's 10K. Any idea why?
Well, I mean, when you look at small transaction, yes, plus 10K, it's 20%. Yes, it may or may not be a big deal. I mean, it really depends on the gas prices, because like plus 20% if vertical means that like we have better stateless client and we have a lot of crazy things and we have better L2s and things like that, maybe having a bit more cost on L1 is acceptable. And any idea why? So why it's more expensive? So why is loading and extension so expensive? I did not explain why. The reason loading and expansion is so expensive is because you have to do a person hash of your account address with the first 31 bytes of the asset. And a person hash is complicated to compute, way more complex than a cache. And so the node have to account for that complexity when they execute the transaction. That's why they are going to make you pay a lot for that. That's also why we have extension. We don't want you to pay. I mean, the core devs don't want us to pay this person hash for each slot we access. So they give us 256 bytes slots extensions.
Great answer. I think there's no more questions. So Adrian, thank you so much. Please give him a round of applause. Great. So our next talk is going to be at 5:30, so we still have like 10 minutes. So take a break, come back. We're going to still have a lot of great stuff on developer experience, and I'll see you in a bit. afternoon, everyone. Thank you for staying with us and for the break. Great, so we're back. Developer experience, I think we're all thinking about what could we be receiving and talking about this next one. So Chris Cashwork, he's gonna talk about cheat calls EAP and how this could be a good way to standardize a bit how these different implementations are done in different systems. Remember, there's a QR code. You can submit your questions there. And with that, I leave you with Chris. Welcome.
Hi, I'm Chris Kaczor, and this is Cheat Codes Ethereum Improvement Proposal, an attempt to standardize an interface of Ethereum development nodes. So let me begin by painting a picture of a landscape of Ethereum nodes. So on one end, we have production nodes. So this is your Geth, your Ref, your Erigon, stuff like this. So these nodes are all about strictly, hopefully, strictly following consensus rules of Ethereum. They're about being good citizens in the, between different nodes. So, mining blocks, verifying blocks, gossiping blocks in the peer-to-peer network, stuff like this. And they are totally not about giving developers any control over the state because they need to strictly follow consensus rules. On the other end, we have test environments. These are not really full nodes. They are more focused only on executing EVM code. But so this is Foundry, this is Hard Hat, and these solutions are all about giving control to the developers. So here, while you develop your smart contract, you can easily, I don't know, deal ERC20 tokens or Ethereum or Ethereum native currency. You can warp time. You can do things like this, and this is very useful to put put your smart contract in a desired state. So you can test complex scenarios. And somewhere in the middle we have the development nodes. So these are tools like Anvil, part of Foundry, like Hard Hat node, like Tenderly or BuildBear. So these development nodes are, on one hand, they are like almost proper Ethereum nodes. So you can ask them about blocks, about logs, and so on and so forth. They implement most of the standard JSON RPC interface. But on the other hand, they also give developers some control over their state. So they have these special JSON RPC methods that allow developers to control them. So let's dive into these development nodes because this is what my presentation is focused on. And turns out they're very useful. So first of all, they support forking. So instead of creating pure empty instance of a node, usually you fork it from some other node, most likely a mainnet node, maybe on a particular block. Another aspect is that they can be both local or running in the cloud. So a good example, basically development nodes shine for all sorts of integration testing when you need to test both your smart contracts and your off-chain system. So for example, in Spark, we simulate every governance spell. We simulate it on a Tenderly fork running in the cloud, and we paste a GitHub comment on a PR with a spell pointing to the UI with this network connected to. So a reviewer of the spell can easily visually inspect the impact of the spell on the UI. Also, we have a lot of end-to-end tests written for our front end using development nodes. And also, we have complex systems balancing liquidity between multiple chains. And guess what? We're also running multiple instances of development development nodes running together and acting as a, like, layer 1 and layer 2s. And as I mentioned, development nodes give developers control over their state with these special JSON RPC methods. And let's talk about them. So, basically every more complex testing scenario requires developers to basically bypass regular consensus rules. So one of the methods, so let me present some of these special JSON RPC calls. So for example, EVM set next block timestamp allows developers to control the timestamp of a next not yet mined block. You can imagine that this is pretty useful when you need to assert that, I don't know, some exact amount of interests was calculated correctly. Then we have EVM revert, which enables us to revert to previously created snapshot. So it's like a dump of a state at of the blockchain at a particular moment. Then we have set ERC20 token balance, which does what you expect it to do. Or does it? And there's Anvil mine for mining new blocks. And there are many other methods, like really God knows how many, because they are not documented properly. And as you can see, like some of them have different prefixes, but the most important thing is that all of these methods have compatibility issues. For example, EVM set next block timestamp, on some of the implementation, it will actually mine a new block right away, which makes writing deterministic tests impossible. EVM revert, in some of the implementation, it allows you to revert to a snapshot only once, and then the snapshot is like destroyed. Tenderly set ERC20 token balance only exists in like Tenderly and BuildBear. So if you relied on this behavior to mint arbitrary ERC20 tokens and you want to, I don't know, switch to Anvil, guess what? You need to write your own implementation somehow. Anvil mine works great, but only some of the development nodes actually have like a proper mempool, and some others just like automatically mine transactions as they come. So all of these incompatibilities reduce the speed of development and make like basically simple things hard. And this is why we created Cheatco's Ethereum improvement proposal. It's a standard to be implemented by all these development nodes, by Anvil, Tenderly, BuildBear, and Hardhat. Of course, we're talking with the team to make it happen. But basic idea is that it's like Foundry cheat codes, but for JSON RPC. So this is why it was named Cheatco's EIP. It's all about like reducing lock-in in a particular node implementation and increasing the interoperability. So imagine that you develop a dApp, and you don't develop a dApp specifically for Alchemy or for, I don't know, Infura, right? Like you can switch RPCs without any issues. Guess what? When you're writing these testing scenarios, like the integration tests, you develop it for a particular node right now. And you can think that this is not a huge problem, but turns out that it is, because often you want to switch from local instance to a instance running in the cloud, because, I don't know, you want to have a shareable link with something for everybody. Or you want to use a superior debugging tools that are only available in one of the environments, right? The Cheatco's EIP is of course like a list of cheat codes that we want these nodes to implement, but it's also a testing suite to verify the conformance to this spec. All of these cheat codes share common prefix called cheat underscore. And just to give you a little bit of taste, like they touch things like time management, mining control, snapshots, impersonation, balance and storage management, and some other areas. So now let me walk you through some of the cheat codes. So time management. As I already mentioned, like this is very useful to be able to calculate interests deterministically and so on. So we have two cheat codes here. Cheat increase time, which mines a new block with a particular timestamp, with a timestamp increased by a particular number of seconds. But I think more useful is cheat set next block timestamp, which doesn't mine a new block, but once the new block is mined, it's gonna have like an exact timestamp. And guess what? Like this is properly specified, and we have proper tests to catch all these mistakes that happened in some of the implementations. Then we have mining control. So in cheat codes, we have proper mempool. And first of all, you can just mine empty blocks with cheat mine. But I think the more interesting is cheat mining mode, which enables you to set one of few mining modes. Like, for example, the default is auto. So basically, as transactions come, the new blocks will be mined. But you can set it to manual to basically stop block production, and you will be required to use cheat mine to mine new blocks, and all the transactions that are going to send are going to be inserted into mempool. And there's also like interval mining, so something that we're used to when dealing with mainnet. And speaking about mempool, we have control how the block production chooses transactions from the mempool. It could be random, it could be like, you know, highest fee first, or first in, first out. And also we have control of dropping the transactions from the mempool. So all of these methods allow you to test complex block submission systems where you can simulate reorgs, you can simulate dropped transactions from the mempool, and so on and so forth. Then we have a bunch of cheat codes regarding snapshots. So cheat snapshot creates a snapshot, and then we have cheat revert snapshot, which reverts to the previously created snapshot. And of course, we make sure that you can revert to a given snapshot multiple times. Impersonation is quite important because often you want to impersonate an account that you don't hold a private key of. So for example, imagine that you want to push a Oracle update, but obviously you won't have a private key to of the Oracle. So you can impersonate an account of an owner of the Oracle and push an update. And if you're familiar with the previous implementation, you were able to either impersonate a single account or sometimes impersonate all of them at once. So we opt into just impersonating every account automatically. So this is what cheat impersonate all accounts does. And you have control either you use impersonation or not, because your client library, if you provide a private key, they're gonna automatically use if send raw transaction. So you send a signed transaction to the node. And if you don't have a private key, just an address, the libraries are going to use if send transaction, which contains all the information about the transaction, and node actually like signs it or just pretends that that they are signed. We also created a meta cheat code for inspecting the current state of the node. So by calling cheat info, you get a bunch of this basic information about the state of different cheat codes, like, you know, what's the mining mode, what's the state of impersonation, and so on and so forth. And also it returns you a cheat code spec version. So this is to future-proof this proposal when there will be probably more proposals extending it. Now let's talk about balance and storage management, because this is one of the most important things that you will likely do on development nodes. So cheat set balance enables us to set a balance of a native token, but cheat set ERC20 token balance does the same for arbitrary ERC20 tokens. And this is best effort implementation, because ERC20 token standard doesn't talk about how to mine tokens and so on. So you cannot do it in every single case, but we can actually come up with an approach that works most of the times, and I'm going to talk about it in a second. Finally, we have cheat set storage head, which enables us to set a particular storage slot of a particular account. So how does setting a particular ERC20 token balance could work? So with cheat set storage add, we can set arbitrary storage slot. The problem is that we don't know which storage slot holds a value, holds the balance of a particular account. So just a reminder, EVM storage is like a huge uint256 to uint256 map scoped for each contract. And Solidity storage layout says more or less that each property gets an index, and if the property is a mapping, then to find a storage slot, you actually take an index and you take the value of the key, the key, and you hash them, and this is your storage slot. So we can actually set arbitrary storage, arbitrary ERC20 token balances by tracing the balance of call for a particular account first, and then we can basically, iterate over touched storage slots and change them until we find the one that holds a proper balance. And this is actually how Forge STD deal cheat code works under the hood. So this implementation is pretty good. It works with most ERC20 token implementations. And if you're doing something very custom, you probably want to come up with your own mock for a given contract or something like this. So what's the state of this EIP? So it's in pre-draft state, meaning that it's submitted to Ethereum magicians, but it's not yet submitted to the EIP repository. There are 3 contributors, 2 contributors other than me, so special thanks for Piotr Szlachciak and Emmanuel Antony for helping me with this proposal. And all the teams of developing the nodes are already familiar with the spec, and we're talking with them, and even today we had a pretty good discussion, tweaking some of the behavior. And here's a QR code for the 2 Ethereum Magicians forum, and you're all invited to contribute, comment, and so on. And also, I'm more than aware that pushing standards in the industry is not necessarily easy thing to do, and there's this obligatory KXCD comic strip saying like, oh, there are 14 competing standards. It's ridiculous. We need to create another one that is universal. And guess what? There are 15 competing standards now. So luckily, in this case, we don't have any competing standards. It's just something that wasn't standardized ever. So I hope we'll have a better time doing that. But I'm also aware that it can take some time for teams to implement it. And there's this alternative client-side approach where we can emulate and try to smooth out some rough edges on the client side. So this would be best effort implementation. Some of the things won't work because it's just impossible to do it client side. But we can document actually what's possible, what's not. We can warn users about incompatibilities. And actually, one of the more complex cheat codes like set ERC20 token balance, actually, it can be implemented client-side because you can trace any call using access lists. So it's possible to implement such thing, for example, client side. And we actually have internally a prototype of this approach, and you know, it's something that might help with transitioning for the full proposal. And that would be it. Thank you, guys. And here's a QR code to the spec again. And as I said, you're all invited to contribute, and I can't wait to hear your comments and opinions. Thank you.
Chris, great job. Great presentation. Thanks so much. So with that, remember, you can scan the QR code. You can submit your questions. Yeah, I see some hearts. Someone is loving the questions and the presentation. And you can also vote for the questions that you like the most. So let's start with the top one. When impersonating, what does EC Recover do? I'm thinking about use case like permit to.
Yes, so this is something that we decided not to tackle yet. This is a known problem, like it also doesn't work right now. What my suggestion is that if you need a signature, most likely the address of the account that you need a signature of is somewhere in the EVM storage of the contract. So what you can do is you can override the storage slot with an address of a you know that you know the private key of. So this way you just bypass this problem and you don't use impersonation at all. You just set storage slot.
Great. The next one is, can we have a cheat mining mode where timestamps do not increase automatically at all?
Timestamps of the blocks, right? Yeah, I think it might be a good idea because actually it's a problem that they are picked automatically, and yeah, I agree. This might be a good idea to just, I don't know, crash instead of mine a new block, and then you would need to set the timestamp of a block explicitly before. So yeah, I definitely think it makes definitely sense. So thanks for this comment.
And whoever did it, or if you guys have other ideas, please find Chris after the talk. I think he will appreciate that. What about the get storage range, or even the get all storage of a contract? Helpful to match the state against an expected snapshot after every action, test action.
Yes, this is great question because iterating over storage slots is like a particularly difficult problem to deal with. So this is like a first version of the spec, and I expect there will be more. And maybe this is one of the problems that can be tackled in the future. One of the like guiding principles of writing EIPs is to keep them focused. So I explicitly wanted not to deal with too many problems at once, but I think like this would be an interesting challenge to tackle. And some of the nodes like Aragon have some special methods to iterate over the storage slots.
Right, but yeah, scope creep is a real issue on engineering. Okay, wouldn't impersonate all hide bugs about misuse of certain private keys?
Yes, so I don't think so. In my experience, like it's much useful to use impersonate all than worrying about, oh, did I impersonate the particular account or not? As I said, like this should be dealt private client side, right? Like if you don't want to impersonate an account, you shouldn't have private key of this account lying somewhere in the client library. This is my current view on this thing. I was also thinking about that maybe it's a little bit too much, but talk to me. I'm open to any suggestions, and like Ethereum Magicians is like, I guess, the perfect place to leave such comments. Or you can talk to me here.
Yeah, we need more and more reviewers, more ideas. All right, can we have a cheat restart node to clean up state and cheat revert state to recover state?
Yeah, so Anvil, I think, has something along these lines. The problem the problem why it's not currently part of the spec is that the spec has to be like universal and has to work with the nodes running in the cloud as well as like running locally, and this doesn't really make sense for the ones running in the cloud. Like I think Anvil calls it EVM or Anvil reset. So it's possible to do. I'm just not sure if it should be part of the standard, right?
Yeah. I think that was the last one. Again, wanted to thank you. Great presentation, great questions, and please give a round of applause. Thank you, Chris.
Thank you.
All right. Do not leave. In 5 minutes, 6 minutes, we're going to have our last presentation of the day, developer experience, and that seems like also very exciting, Hard Hat 3 preview. So 5 minutes, and we'll be back. Thanks. Good evening. Welcome. Good to see you all. I'm glad you stayed for our last talk of the day, which is about Hard Hat 3 preview. And Patricio Palladino is going to talk with us about all the challenges, the changes, the upcoming features. I think it's going to be a great talk. I hope you stay put. Remember, there's a QR code on the screen on your right where you can submit your questions and vote for the questions that you wanted to be answered the most. So with that, I will leave you with Patricio. Please give a big round of applause.
Okay, these are the slides. Hey everyone, thanks for being here. My name is Patricio. I'm the co-founder and CTO of Nomic Foundation, which is a non-profit dedicated to Ethereum developers like you. At Nomic, what we do is building open source infrastructure and tooling for the Ethereum community. And the most well-known of our tools is Hard Hat. And during this presentation, what I'm going to talk about is Hard Hat v3 or Hard Hat 3, the new version of Hard Hat, which is still in development because it's a whole overhaul of Hard Hat with tons of changes. But first, let's take a look at Hard Hat 2 for a second, especially its limitations and why we decided to rewrite it. The first one and main one is that Ethereum changed a ton during the lifetime of Hard Hat. We started working on it almost 7 years ago, about 2018. And back then, Ethereum was a single chain, a way more simple ecosystem. There was mainnet and a few testnets. Those testnets aren't even alive nowadays. And the applications were simpler, right? There wasn't even stablecoins back then. Now, applications are larger, and Ethereum turned to be a single chain into an ever-increasing ecosystem of different chains, each of them with a slightly different behavior. Another problem that we have in Hard Hat 2, or HAT, is that we brought everything in JavaScript, including our network simulator, and that had several performance issues. We also focus a ton on the Node.js ecosystem, because we envision building a platform for others to be able to customize and extend their own setups. But that focus on JavaScript only also meant that you could only write tests in JavaScript or TypeScript. And the final limitation is that as when we designed Hard Hat, there was only one chain, mainnet. We designed it in a way where for every single Hard Hat process, there is a single chain, a single network connection. You just import Hard Hat. You have your network connected there. Most of the time, it's going to be simulated by us. And all the boilerplate, all of your libraries, all your plugins get configured for you, but it's a single chain. As soon as you want to work with multiple chains, you hit this limitation and you start making workarounds. We created RPCs for switching the hard forks or forking other networks. People use different configurations and things like that. So Hard Hat 3, we rewrote it from scratch to circumvent these limitations and offer more functionality. And how does it look? Well, it looks a bit like this. It's a bit like Hard Hat. It's still Hard Hat, but Hard Hat from the future or more technical Hard Hat. But at the end, it's just a Hard Hat, right? Like, it feels and looks like Hard Hat. So, as I mentioned, it's a complete revamp of the product. The scope is massive. Hard Hat grew during these 6-7 years. It has tons and tons of plugins and functionality, and I can't cover everything here. I'm only going to focus on this list of things, which are the network simulator that we rewrote in Rust, the Solidity test support that it's added in Hard Hat 3, our deployment solution, and how to ergonomically work with multiple networks so that you don't have to do those workarounds that I just described. And finally, how we correctly simulate obstacle chains. The first thing, as I mentioned, is that we rewrote our simulator in Rust, and we ship it just as an NPM package. Nobody or some people notice this, but in Hard Hat 2, we are already running every simulation in Rust, and that led to significant performance improvements. For some people, that is even 10 times faster in real-world scenarios. It's not just benchmarks, but they just got a new version of Hardhat, and without noticing, their tests were 10 times faster. 10 times faster. And you just don't have to notice that. The TS interface is still the same. It's just at the core, it's Rust. It's a project that we call EDR from Ethereum Development Runtime. And if you want to learn more about that project, someone from our team is going to give you a presentation about it tomorrow. The other big change that comes along with EDR is that now that our runtime is written in Rust and we can run things quickly, we decided to add support for Solidity test. If we did that previously with our previous infra, that was probably going to be more challenging and slower. So we added support thanks to EDR. It's also written in Rust. It's Foundry compatible, which means that it's mostly a drop-in replacement. All of the features that you would expect, like fuzzing, invariant testing, force STD, whatever you would normally use in Foundry, you can still use it in Hardhat 4, but under the hood, it's going to be run using Hardhat. The other point that I want to explain here is our solution for deployments called Hardhat Ignition, which is also available in Hardhat v2 if you want to try it out now. And it's basically a declarative deployment solution. And by that I mean that what you do in Hardhat Ignition is describing your end goal, how the system should look like in production, and Ignition will do everything it needs to do to take your system there. It looks a bit like this. Instead of focusing on transaction and execution of a deployment, you don't write a script, but rather define a module, an Ignition module. You can think of a module as a JavaScript module, Rust module, Python module, like a programming language module where you define certain things, certain entities, and you export some of them, the ones that are going to be interested by other modules. In this case, modules in Ignition are futures, are not transactions or anything execution-wise. Instead, as I mentioned, they describe the intent of the user to perform something on-chain. In this case, in this example, we have two contact deployment futures. Basically, what we are telling there using an API is to Ignition is that it needs to deploy a contact called parent with the first and single argument P, and a contact called child with a C as its name, I guess. And finally, there's an extra, a different kind of feature that it's something like, once the parent is deployed, please call add child with the child address as its single argument. But this is, as I mentioned again, or I will mention this again once more, this is just your intention. Here, when you do this, there's nothing being run. There's no transaction. Those addresses don't exist yet. It's Ignition that will deploy them later. And given that it's just a static description of what you want to do, that gives Ignition a ton of freedom to do whatever it needs to do to get there. It will analyze the graph of futures that you define in your modules and automatically detects how to or batch them and come up with a plan so that they can be run in parallel as long as they are safe to run in parallel. That leads to faster deployments, but that same feature or that same capability of it being static and Ignition taking the whole control of execution allows us to do things that are much more, I guess, smarter or better for you. If you are running a deployment script and it fails for any reason, let's say that your network fails, you forgot to fund your account or something like that, Ignition can detect that and recover. And how do you recover from those kind of errors? Well, normally if you were writing a script, you would probably modify the script. Maybe add an if or comment out part of it, just so that it only continues running the things that are missing. In Ignition, it's not like that. You just rerun it, and Ignition will automatically compare its local state with the network state. It will validate that they are in sync and decide how to continue. That allows us to handle a ton of errors. Just to name a few, things like gas price spikes, we can map transactions. If a transaction is dropped from the mempool and disappear, we just resend it. If there is a problem with nonce management, we detect that. Those kind of things we can do just because we aren't giving control of the user to the control of the execution to the user, but keep it to Ignition and doing it ourselves. Then, while Ignition has more features, the only other one that I will talk about here is that modules like the one I showed here can also be evolved and iterated. Let's say that I deploy this system, everything goes right, I get traction, maybe I need to add another contact, another child, I guess. And that's common, right? Successful software always evolves, always requires changes. Maybe in smart contracts, that means adding a new smart contract or running an upgrade if your system is upgradable. And to do that in Ignition, all you need to do is modify your module, rerun it again, the same module, the same command, and it will detect if they are compatible, complain if they aren't, but if they are, it will diff the state and only run the things that needs to be run to get it to the new version. And finally, the only big feature of Hardhat v3 that I want to touch is its new multi-chain support, which is a fairly complex one, so I'll explain it bit by bit. There are many things happening here. I'll use these 2 lines of code to explain them. First, as I mentioned, in Hardhat 2, when you just import Hardhat, you get a single connection to a single network, right? And that brings a ton of problems. In Hardhat 3, that's different. We gave full control to the user about network connections, and instead of exposing a already, I guess, prepared connection for you, we instead give you access to what we call a network manager object, which has a connect method, and that method takes a network config name by parameter, and it allows you to connect to whatever you want. In this case, mainnet would be one of the networks that is configured in our config, but it could be any other network, right? And it could also be an EDR-powered network. You can create many network connections to simulated networks and create many simulations, and all of them are going to be independent. Then, while you do that, the plugin system that has been rewrote in Hardhat 3, it's going to initialize all the usual libraries and helpers and things that Hardhat does for each of those networks. So here, this VM is connected to the network connection mainnet, but not to any other one that you create. And you can, doing that, you can create anything that you want and avoid any kind of workaround like switching networks or having multiple config files or things that people used to do in V2. At the same time, we introduce a new concept. As you can see, connect takes a second param. That concept, we call it chain type. And as the name says, it's the type of chain that you are connecting to. I guess you could explain it like if you were to take all the different EVM networks, some of them will behave very similar to each other, like OpStack networks behave close to each other, maybe with some smaller param differences. L2 behaves similar to Sepolia. RB2 may have different deployments, and so on and so forth. Each of those, we call them chain types, and what you do by providing a chain type while you connect is 2 things. First, you inform the connection or the plugin mechanism that those libraries and helpers that you are using and you install should be aware of that chain type, which can mean that they include differences in the JSON RPC, how they interact with the JSON RPC, or they may even, like in the case of VM here, they may even install extensions to their API. If you ever use VM with OpStack, you may know that you can add special op-specific actions, and this will be done automatically, both at runtime and at type level. So if you were to use opvm to run an op-specific thing, like estimating L1 gas, and you just switch the chain type to L1, it will stop compiling, it will give you a type level error, so that it will lead to a very smooth developer experience, while at the same time automatically initializing it for you when you are when you're using the right chain type. Now, that's not the only thing that the chain type does. If you're connecting to an EDR network and you use a chain type, you will also inform EDR that it should be running on a different mode. EDR in Hardhat 2 only simulates mainnet, but in Hardhat 3 it simulates different chain types. Right now we only simulate three different chain types. L1, which is focused on mainnet, Sepolia, and Holesky, or something like that. We have Optimism, mostly focused on OpStack. Mostly right now, mostly op mainnet and op Sepolia. And we have another one that is called generic. It's for every other network that we haven't fully supported yet, which is kind of a base common denominator. And what EDR will do when you provide a chain type is change its behavior to actually behave as close as possible to the real network. And what does that mean? It means a ton of things. It depends on the network, right? But it could mean JSON RPC changes. Sometimes an object has extra fields, or some fields are removed. Some chain types have extra JSON RPC methods. Maybe some of them have extra opcodes. Optimism, I think, has 1 or 2 opcodes. They have extra pre-compiles, pre-deploy contracts, different gas cost, all of those things. We want EDR to be very precise at simulating, because otherwise what we end up doing is just using L1 or tooling designed for L1, testing against L1 and deploying to different networks that behave slightly different, and just hope for the best. And those things sometimes go wrong, and that has already happened. So the idea here, combining all these features, will lead to you being able to handle multi-chain workflows while very smoothly, while also having very precise simulation of those chains. Finally, the project status. I want to mention how the project is going. As the title suggests, this is just a preview. This is not ready to be used. It's not in production. We have an internal alpha. It's not ready. It's pretty rough. We are doing some demos with some teams. Unfortunately, we can't do it with everyone. But if you're interested and you see us around, you meet us somewhere, just let us know, or just get in touch through the internet, I guess. But in a few months, we'll make that alpha public. Finally, if you want to know more about what we do at Nomic, we have a few extra presentations. If you scan the QR code on the left, you can see a list of our presentations. Tomorrow, I'll give a keynote explaining the high-level technical vision of Nomic Foundation. Somebody else from our team will give a presentation about how EDR implements these chain types and simulates different L2s. And on Friday, we have a presentation about Slang, our Solidity compiler as an API, and in particular, some cool APIs that it offers to do code analysis for Solidity, like imagine CSS for Solidity code, something like that. And if you enjoy what we do and you like to work with us, scan the other QR code and you'll get info about our show openings. That's it. Thanks, everyone.
Amazing, Patricio. I'm already very excited. Great presentation, great features.
Thank you.
So, all right. Remember, you can scan the QR code. You can send love. There's already a lot of hearts. And you can vote for the questions that you want most. I think we're going to, hopefully, I think we can have, there's a lot of questions. So let's start right now. What's the killer feature over Foundry?
Yeah, so I think there are a ton of different features. I think developer experience is a hard topic because there is a ton of smaller pain points that you need to fix to have a great a great development experience, and sometimes there is not a single killer feature. Well, I do think that the multi-chain support that I mentioned is great. I think that's something fairly unique. I haven't entered into other more advanced things that Hardhat 3 does way better over Hardhat 2, but eventually we'll release more information.
Great. How does Ignition handles proxy upgrades?
Yeah, so proxy upgrades for Ignition are just other features. A proxy upgrade is just a call, so you can encode the call. You can also create reusable functions, like any function. A module is just code, so you can create a function that would be run this upgrade. And it takes other futures and returns a future or something like that. We have examples of that on our website.
Great, great answer. Next, is VM the future of Hardhat, or do you plan to support both VM and Ether.js equally moving forward?
Both, or yes, I guess would be this answer. I think that the default experience will be VM. As we saw, it's more advanced, especially for L2s. It brings better support for certain L2s. That's great. It's also way more advanced with TypeScript, but moving forward, we'll support both. And we'll even support both. We'll even provide a smooth transition for people that use Ethers in V2 to use Ethers in V3 and to use both in V3. Yeah.
Great. Next one is about deployed state managed. How is the deployment state managed? For example, if multiple devs are working in the same project, but the state is local, there may be conflicts.
Yeah, so the state is local. We think that it's just another artifact that you should version and share. Just treat it as if it were code. It's just code. Yeah.
Okay. All right. Next one. Will Hardhat 3 provide full traces of failing tests like Foundry does?
Yes. And it will also provide other features that Hardhat V2 does, like recognizing common error scenarios. Like in Hardhat V2, if you, I don't know, send a transaction to a method that it's with value to a method that it's not payable, and things like that, Hardhat detects them, gives it a clear error message saying, hey, you are sending funds to a non-payable thing, and things like that. Those will also be supported in Solidity test too. Oh, maybe I didn't mention this, but the chain types thing, the ability of precisely simulating a different chain, that will also be available in Solidity test. How it will look like exactly, we are still exploring it. It may look exactly the same, but just a flag at the command line, or it may be more present through the Solidity testing framework.
Great, great answer. So why not build in public since the beginning of V3? I think people really want to get their hands on it.
Oh, it's on GitHub. It's a branch called V Next. It's just that it's not ready for production. Yeah, just clone it, build it. Just don't complain if it breaks too often.
Yeah, it's still very alpha.
Yeah.
It's expected to. All right, Ignition question. It doesn't let you poll the state of the contract in the middle of the deployment. Isn't it a great limitation?
I'm not sure if I understand this question. I guess if it means if you can read a contract, yes, you can read it. It's just another feature. I didn't show it here, but just as you do call, which would be a write operation, you can have a feature for a read operation, and it's just a feature.
Right. When launch of Hardhat V3 timelines?
It will be early next year. Exactly when, we don't know. Yeah.
Great. Can Ignition module be used as a fixture in tests?
Yes, they can be used as fixture in tests, both with VM and Ethers.
All right, all right, all right. Will Hardhat provide better debugging like Symbiotic by runtime verification experience, or better experience than Foundry, and how? Or how?
Well, we'll focus very strongly on debugging after our release. How exactly? It's fairly complex. We have 15 seconds, but we'll integrate EDR and our compiler to be able to provide better debugger experience. And that's part of what I will talk in my keynote tomorrow, so feel free to go there.
Don't miss it. Is multi-chain support compatible with awesome plugins that already exist like Hard Hat Deploy? If not, how hard is it to it's going to be migrate?
Yeah, so every plugin, if there's plugin authors here, you may hate me, but every plugin will have to go through a pre-mechanical migration. Plugins are easier, in my opinion, to build in Hard Hat v3, but it's not automatic. You have to migrate them.
Right, right. Are you thinking about smart contract mocking support?
Yeah, so for Solidity test, they are supported. As I mentioned, Solidity test is a drop-in replacement of Foundry, just with EDR at its core. And for JavaScript test, we would like to see smoke return, but we'll have to, I guess, chat with the team, and we'll see in the future.
Right. Does Hard Hat Ignition supports Open Zeppelin's upgrades plugin?
No, not yet. It's something that we'd love to see happening, and I've been chatting a bit with some of them. That some of them may be here, but we'll eventually get there.
All right. There are 7 more questions, but we are over time, so let's take maybe 2 more. Ignition is like Terraform for is Ignition like Terraform for contracts?
I guess you could say yes, or somewhat. It's a big inspiration.
Nice, nice. And what is the difference in supported chains like EDRP versus general chain support? What difference or lack of features can we expect with the generalized chains?
Well, the generalized chain or generic chain doesn't have any extension. It's more like it's the base common denominator of EVM. It's even less strict than mainnet. When you run on L1 mode, we are strict about simulating mainnet as closely as possible. With generic, it would be closer to what Hard Hat 2 does. It doesn't have any extension that any L2 has, and it's a bit more, I guess, forgiving.
Right. There are more questions, but we're sadly run out of time. So if you want to catch Patricio later after the talk, I think he'll be available. Otherwise, online as well. Please give a great round of applause to Patricio. Great talk. We're all very excited. With that, we complete the day. Please remember to pick up any litter or things to clean up after yourselves. We will start tomorrow at the same time. I think we had great applied cryptography, user experience, developer experience, and core protocol talks. So please come back tomorrow, enjoy all this great knowledge, and see you soon. So hope you have a good one.
you.